Hi, I'm Abhinav. I've been a part of Value Lab for 2 years.
Hi, I'm Angelica Dias.
Hi, I'm Saurabh Rajput and I'm a 2016-17 batch student.
Hello everyone, this is Akshita Ramesh, member of
At SIES, as a college which stands for academic excellence, we constantly cater to the talents of the students. We believe that every child, every student who walks into the portal of the college comes with a lot of hope and promises, as well as with a lot of hidden talents. This is a forum which allows you to kindle as well as unlearn a lot of things which will allow you to reach your potential to the highest.
This song is for those who see their students through the This song is for the world. Call our home forever. We will know that you have made it.
Hi, I'm Abhinav. I've been a part of Value Lab for 2 years.
Hi, I'm Angelica Dias.
Hi, I'm Saurabh Rajput and I'm a 2016-17 batch student.
Hello everyone, this is Akshita Ramesh, member of
At SIES, as a college which stands for academic excellence, we constantly cater to the talents of the students. We believe that every child, every student who walks into the portal of the college comes with a lot of hope and promises, as well as with a lot of hidden talents. This is a forum which allows you to kindle as well as unlearn a lot of things which will allow you to reach your potential to the highest.
Good morning, everybody.
Good morning, sir.
This song is for those who see their students through the tough times in their lives. For that we say thank you. You have made a difference. You have shaped our minds. You have changed the world, one child at a time. You have always been there in everything you do. I hope that you're as proud of me as I am proud of you. This song is for those who heard the silent cries, who stepped in to wipe the tears from the children's eyes. For those who gave us a safe place to grow, a place for us to call our home. Forever we will know that you have made us.
Hi, I'm Abhinav. I've been a part of Value Lab for 2 years.
Hi, I'm Angelica Dias.
Hi, I'm Saurabh Rajput and I'm a 2016-17 batch student.
Hello, everyone. This is Akshita Ramesh, member of Value.
At SIES, as a college which stands for academic excellence, we constantly cater to the talents of the students. We believe that every child, every student who walks into the portal of the college comes with a lot of hope and promises, as well as with a lot of hidden talents. This is a forum which allows you to kindle as well as unlearn a lot of things which will allow you to reach your potential to the highest.
This song is for those who see their students through the tough times in their lives. For that we say thank you. It's for those who see their students. Forever we will know that you have made a This song is for those who place for us to call our home. Forever we will know that you have made a This song is for those who see their students through the tough times in their lives. For that we say thank you. You have made a difference. You have shaped our minds. You have changed the world. One child.
Okay. Just a minute.
Hi, I'm Abhinav. I've been a part of Value Lab for 2 years.
Hi, I'm Angelica Dias.
Hi, I'm Saurabh Rajput and I'm a 2016-17 batch student.
Hello everyone, this is Akshita Ramesh, member.
SIES is a college which stands for academic excellence. We constantly cater to the talents of the students. We believe that every child, every student who walks into the portal of the college comes with a lot of hope and promises as well as with a lot of hidden talents. This is a forum which allows you to kindle as well as unlearn a lot of things which will allow you to reach your potential to the highest.
A very good morning and warm welcome to each and everyone to Pratibha P National Webinar on Frontiers of Physics. It is said that knowledge is fire and we should let others light their candles with it. Fortunately today we have with us few torch bearers who would not only let us light our candles but would also pave the way for better understanding of our subject physics. To invoke the presence of Almighty, I request our MSc Part 2 student, Ms. Mridula Iyengar, to recite the prayer song.
Thank you, ma'am. स्वरवीणा मृदुपाणि वनरुहलोचनराणि सुरुचिरबम्बरवेणि सुरनुतकल्याणि निरुपम शुभगुणलोला निरतजया प्रदशीला वरदा प्रियरङ्गनायकी वाञ्छितफलदायक सरसीज जननी जय जय जय.
Thank you, Mridula. I request the head of physics department and the vice principal of SIES College, Mr. Vinod Menon, to welcome the gathering and share with us the inspiration behind the Pratibha P national webinar on the frontiers of physics. So please.
Good morning. Good morning, everybody. Warm welcome to all of you. This is the second webinar we are conducting in this calendar year. We had one webinar series in the month of May, and this is the second one we are doing it. The motive behind this webinar is to introduce scientists, researchers working in the advanced series of physics to our students. So last time which was meant only for our students, SIE students. This time we have opened up for all Mumbai University students and also other students from other parts of the country. Our response is very good. So I'm very happy that many will be joining this webinar, because it is going to be conducted by the eminent scientists. They are working teachers from scientists from the PIF or IIT or Institute of Science. Okay. Now this particular webinar is dedicated to our former HOD, late Pratibha P. Popularly known as Pi Madam. So Pi Madam joined in SIS in 1981 as a postgraduate in theoretical physics from Mysore University. She used to handle theoretical physics lectures like electrodynamics, relativity, her career. Later on, she developed a keen interest in electronics or programming, computer programming, high-level languages like VHDL, ARM processor, etc. She was so popular that she was not popular not only with our students, she was popular with other students from other colleges also, because she used to go as examiner, she used to give guest lectures in various colleges, even the teachers and students from other colleges. So everybody used to know her. She was very, very popular because of her ability to impart knowledge and also being a very, very human nature. Now, as a teacher, how can I describe Pi Madam? I can describe in one word. She is the ideal teacher you can think of. Most ideal teacher. So her knowledge, dedication, and love for teaching is unparalleled. I have never seen anybody who is totally dedicated to teaching. And as a human being, she was the most lovable person. Personally, for me, she was like my elder sister. She used to help me. She has helped me in all stages of my professional life. And I am sure that everyone who knows her will have the same feeling about her. For everybody, she is part of their life. That is how she used to be like that. And it is very difficult to describe her in few words or in short time like this, because she is such a wonderful human being. It's very difficult for me to describe her completely. Yes, her smiling face and hearty laugh can never be forgotten. And I really appreciate her family members are here, daughters are here, her husband is Mr. Pai is there. It was such an unexpected loss for all of us, not just for family members, for everybody. In fact, this has been a very difficult year for us, not just due to the pandemic and restriction. We lost two most endearing colleagues in the department, Swapnil Javkar and Pai Madam. Even after her retirement, she was very actively interested in teaching, involved in the teaching. She used to interact with students, he used to interact with the staff members, and for each and everything, all the staff members used to go to her for her advice or counsel. So, and in fact, it's a big loss for us. We miss her on day-to-day basis, I can say that. And I thank my colleagues for arranging this webinar in her memory. Madam, wherever you are, you will be happy to see this program arranged for students community, because you have always dedicated your life for students. For you, your students are everything. Students, the college, SIES, that's everything for her. We will be missing you on day-to-day basis. We are still missing every day, even when you are arranging all these programs. At every step, you used to remember Pi Madam, because we used to ask her, okay, madam, this is what we have to do, all that. It was a big loss for us. Thank you, everybody. I hope you will enjoy this. This webinar will be very useful to all the students. Thanks once again, Devi.
Thank you for sharing this emotional feeling. Now, I would like to request the principal of SIES College, Dr. Rama Chandra, to inaugurate the event and address the graduates. Ma'am, please.
Good morning, respected members of Pratibha family, Mr. Khan. I guess the speakers for the day, and seekers, and a very warm welcome in the virtual world of the webinar memory for 2 to 3 decades. What can be offered her? The only way of
It seems your voice is not audible.
Probably, I think if you switch off the video, probably I think, madam, if you please switch off the video, maybe it will be audible.
Can you hear me now?
Yes, ma'am. Yes,
Okay.
ma'am. Yes.
Should I start from beginning, or was it okay earlier? I can't hear you, Vinod.
Yeah, it's okay, madam. You can continue. Yes.
So, Ms. Pratibha Pai was a pioneer not only in the field of physics, and the department had enormous love and affection, which Vinod shared just now, but her contribution to the institute itself is exceedingly, we remember her for that. As her commitment, her sincerity, her dedication to the institute and every department and every kind of new activities that we have taken up, there has been always a kind of a strength and support that we all get it from Pratibha Pai. And therefore, it's not only the department that lost it, but even after her retirement, she's been remembered at every bit of a document that we pick it up from the college. We go back in memory of her, how she would have written it, how she would have documented it. A great teacher, a wonderful academician, a great administrator, and to her today we dedicate, and therefore I inaugurate this webinar in memory of her. Appreciate all the efforts put by the physics department, because this is the best way we can remember a stalwart in the field of physics. This webinar, titled as a Frontiers in Physics, is getting across, as Vinod said rightly, to the students, for the students, by great stalwarts whom otherwise we would have thought it very difficult to get them in one platform. We have a host of great minds coming together today. Dr. Sujit Manna, Dr. Pratap Roy Chowdhury, Dr. Tanmoy Das, Dr. Anju Datta, all coming from various respectful, dignified institutes. We are indeed honored by your very presence, and I'm sure the students and seekers of knowledge and budding scientists, budding physicists who have gathered today will have exposure to the insight that these speakers will be sharing with you all. Science is basically a very rigorous phenomena, and therefore, unless a host of knowledge that has been read, experienced by these stalwarts, these scientists, which the normal students may take years and years to understand them, you may get it just in an hour or so. I request all the students who have gathered today, the researchers who have gathered today, to make the best use of your time in the presence of these scientists in the virtual world. But I'm sure your questions, your doubts, and your curiosity to know more shall be definitely satiated. From our college, this is a humble effort. We have put it across through the Department of Physics, and I'm sure there are many more such webinars which will be coming through. With this, I wish a very good best of luck and best wishes to all of you all. And I once again welcome my family members and the scientists who will be joining one after the other for the day-long webinar that we have. I also keep it open. The college shall welcome you all when the pandemic is over. Whenever we all visit Mumbai, please, our college is open for you all to come and interact with our teachers. With this few words, I inaugurate the webinar today, and I welcome all of you for a wonderful session ahead. Thank you.
Thank you for your kind words, ma'am. Now I would like to request the convener of the event, Dr. Vishal Dev Ashok, to share his thoughts about today's webinar. Sir?
Yeah, am I audible? Yes. Welcome you all to August gathering on the third Saturday of July. 2021 has been particularly a difficult year for our physics department when we lost two of our beloved faculty members. One is Swapnal Javkar and another one is Pratibha P, to whom this webinar is dedicated. Pai ma'am became a part of this college on 20th of June 1981, when most of us were not even born, and was associated with the department even after her superannuation at the end of 2017. She had been mentoring her juniors and has been a driving force for various activities in our department. She had the ability to multitask effectively and effortlessly and grasp complex ideas very quickly, and somehow broke it down into small, easy pieces, making accessible to the dumbest of dumb of us, which would earn her popularity among students and respect among faculties. Her research ability was unparalleled. This can be known from the fact that she happened to learn a completely new advanced hardware programming language just before her retirement, and became the go-to person for any queries or any doubts. She had the data about the college at the back of her head. We used to call her five-man army for her zealous and vivaciousness, which, while dealing with complex situations at the drop of a hat. She would promote young faculties to participate and conduct workshops and seminars. Her persona can be truly summarized by quoting something in Sanskrit. Pardon my pronunciation. It's prasanna vadanam saubhagyadam bhagyatam bhatabhyam abhayapradam aniganay nana viday bhushitam, meaning the one with a smiling face who brings good luck, and the one who protects her fellow being is bestowed with various ornations. We find ourselves very fortunate to have known her and worked under her tutelage. As she would have said, never waste a crisis. And also, if you don't understand something, listen to it from the horse's mouth. In this spirit, here we try to bring together a set of young and dynamic stalwarts in the field of research to a common platform for the students to interact with, to learn from, and understand the process of development in science. We have 4 speakers for today, 2 in the morning session and 2 in the afternoon post lunch session. Dr. Sujit Manna will start the first talk, which will be from Sujit Manna from IIT Delhi. Will be talking about the use of
This song is for those
scanning tunneling microscopy in identifying various properties and manipulating at atomic level. Then Professor Pratibha Roy Chaudhary from TIFR Mumbai will speak about mapping using AFM again, atomic force microscopy again, an interesting phenomena of circulating supercurrent called quantum vortex, which locks the magnetic field on the surface of a two-dimensional superconductor. 2D type 2 superconductor. In the post-lunch session, we will have a theoretical physicist from IISc Bangalore, Dr. Tanmay Das, who will speak on the interesting development of the physics behind superconductivity, followed by an experimental physicist, Dr. Anuja Datta from IISc Kolkata, who will be talking about finding alternate sources of harnessing micro sources of energies to counter the energy crisis that our planet is expected to run into. With this, I would like to throw this session open. We will join after 10 minutes. Every talk will be followed by a question and answer session. Okay, students are requested to post questions on the Telegram group or in the YouTube chat, which will be posted to the speaker. And we strongly encourage you to ask questions, as millions of people saw the apple fall, but only Newton asked why. And we knew the relation between the falling apple and the moon. And no question is foolish. It's only how a person understands it. I mean, as long as it is understandable, the question is never this thing. So I hope you find today's webinar fruitful. Please note that the feedback form will be shared after each session. Okay. Thank you. We will meet after a short break of 10 minutes. Okay.
Thank you, Vishal sir. Thank you for describing Pi Ma'am to all of us in such an efficient way and walking us through today's event. As sir rightly pointed out, the first session will start at 9:30, and we would like to share with you all few videos made by our students as a tribute to the memory of our beloved Pi Ma'am. Thank you and enjoy the webinar.
This song is for those who see their students through the tough times in their lives. For that we say thank you. You have made a difference. You have shaped our minds. You have changed the world, one child at a time. You have always been there in everything you do. I hope that you're as proud of me as I am proud of you. This song is for those who heard the the silent cries? Who stepped in to wipe the tears from the children's eyes? For those who gave us a safe place to grow, a place for us to call our home. Forever we will know that you have made a
How will you do it? You can hack it. You can find out. YouTube में चल रहा है और पीछे यूट्यूब में भी विषय की बात कर रहे हैं हो गया यूट्यूब में भी वो वहाँ पे है
This song is for those who see their students through the tough times in their lives. For that we say thank you. You have made a difference. You have shaped our minds. You have changed the world, one child at a time. You have always been there in everything you do. I hope that you're as proud of me as I am proud of you. This song is for those who heard the silent cries, who stepped in to wipe the tears from the children's eyes. For those who gave us a safe place to grow, a place for us to call our home. Forever we will know that you have made a
Okay, welcome back to the session. The first session will be carried out by Dr. Sujit Manna of IIT Delhi. He did his MSc from Jadavpur University in 2006. His PhD from IACS, Indian Association for the Cultivation of Science, in 2011, and went on to do his postdoctoral duties in Max Planck Halle between 2011 and 11 to 14, and then went to International Nano Center Hamburg in 2014, between 2014 and 16. He joined, yes, my video. Okay. And he joined IIT in 2019, before which he was doing his postdoctoral at MIT between 16 and 19. He is an expert in scanning tunneling microscopy. His research interest is in topological superconductors, surface sciences, and scanning tunneling microscopy itself. The topic that he will be covering is sensing and manipulation of individual atom using STM. Over to you, Sujit.
Okay, good morning everyone, and thank you Vishal for your kind long introductions. It's really overwhelming. I hope everyone could see my slide I just shared. Can you confirm, Vishal, please, that you can see my slide? I have a first slide which is blank. Okay, very good. Yeah. So once again, good morning. I see there is already so many participants. Early morning, 9:30. It's good. So yeah, as Vishal said, I'm Sujit. I actually is working in IIT Delhi, and today I'm going to talk about very basic things about scanning tile microscope, what is good for, and how you can do a good science with that. So basically, as Vishal said, I have spent a couple of years working with this scanning tile microscope and the spectroscopy, and the principal goal of my research to build understanding of very important quantum mechanical phenomena in the atomic scale. Particularly last decade or so, I've been working on a versatile quantum materials, and was studying the emerging electronic, magnetic, and their prosthetic properties in a strongly correlated electron systems where charge, spin, orbital, and lattice degrees of freedom are very much intertwined. And one of the techniques that I'm going to discuss today is really a real space technique which can address all these degrees of freedom simultaneously in real space. And this is very unique tools. These are tools for also the nano walls and real space imaging techniques I'm going to talk about. Just to give you overview about my research, so I actually work on wide versatile materials using those powerful microscopes. This microscope works in a very special environment, mainly at low temperature under ultra high vacuum environment. And we have studied wide variety material last couple of years, and starting from magnetic multi-layers to some topological materials and ultra thin superconductors, some materials with a large charge density wave, also some 2D material like graphene and some metal chalcogenide. We have also have work on some of the Heusler compound, ultra thin film, and very recently I've been also working on some kind of topological superconducting compound. This, if I time permit, I'll talk about a little bit about this. So essentially, that today's talk is about this basic understanding about how we can sense and manipulate of individual atom using scanning tile microscope in real space. So this is actually a cartoon image of how this is our probe. This is actually eyepiece of a microscope that usually people, you know that optical microscope you all know in the biology lab or the chemistry labs. So in this microscope, scanning tile microscope, my peak, which is a probe, is a kind of eyepiece, which will be actually is so efficient that it could probes its individual atoms and also their spin moment. And I'm going to talk about that how we can understand that and what kind of actually how we can address the fundamental quantum mechanical open problem using this microscope. So just to give you a brief outline, so I'll give you in just a a little bit motivations about the importance or why we are interested to study the materials in atomic scale. And then I will talk about in very details about how this microscope work. And this microscope has also, this canine microscope has another beautiful characteristic is that you can do spectroscopy. So using this spectroscopy, you can really study the electronic and magnetic properties with very high energy and spatial resolutions, which is very important. And then I'll give you a couple of examples, which are basically some significant work in this field using these microscopes. And totally, I'll show you some very elementary confinement effect in a metallic systems. And then I will talk about another unique microscope, which is basically extension of the STMs to resolve the spin of the atoms, so-called spin poise STMs. So where I will show you that how one can actually measure the magnetizations or magnetic hysteresis loops, so-called, of a single iron atoms or some iron clusters. And later, if time permits, I'll talk about the one of the project I was recently working on. And this is towards a finding some exotic quasi-particles, so-called myron of fermion, which is a particle with its own antiparticles. And in the laboratory, in condensed matter laboratory, in the system of made of gold nanowire, using again scanning tele microscopy and spectroscopy. So just to tell you that I cannot see any audience here, and so it's like a blank. So please feel free to stop me and ask questions. If I don't get any question, then I'll continue, but I have no idea how it's going on the other side. So please feel free to stop me anytime and ask questions if you have any doubt. Okay. Okay, so the scanning tele microscopy or spectroscopy is a surface sensitive techniques or surface sensitive tools to visualize the surface with high spatial resolutions. And this microscope was basically a kind of open up a new perspective and to address a lot of fundamental questions in the quantum mechanics. So you remember that since the quantum mechanics discovered, and then there is a lot, in order to study the surface of a materials, it was very important. There was a lot of technique which is sensitive to the surface has been discovered, namely, say, angle photoemission spectroscopy, X-ray photoelectron spectroscopy, low energy electron. All this electron-based spectroscopic technique has been discovered to study the surface. But all this technique, you can learn a lot about surface, but all are mostly actually microscopic average. So they actually typically the laser light used to probe the surface in the order of millimeter or like some 100 or micron. So then there is no way it is to understand what is happening in the atomic scale. We had to wait till 1980s to visualize, to get a powerful tools to know what is happening in the atomic scale. And this is the reason actually today we are going to think about like this way, that why we need to really care about to learn a material down to single atomic level. So one of the challenge in the in condensed matter or in technologically also that that every day the advancement of this information technology that so fast that probably there is a fundamental question that we will slowly going to the limit very fast with the silicon technology. So as you probably seen that I had a
It seems your voice is breaking.
Oh, sorry. So please remind me whenever working that I could repeat, because the last few days I'm in the campus, but the really the internet is relatively poor. So is it okay now? How's it going now?
Yes,
Vishal?
it is.
Now
It is okay.
So my volume is also fine, or I increase the
Yeah,
volume
it's
a
fine.
little bit?
It's fine. It's
Okay.
fine.
Okay. So typically nowadays you have the smartphone in your hand that typically you can easily get a storage of more than 50, 60 gigabyte, and they have a basically resolution is very, very high. But if you remember that in 60s, this Commodore, this IBM Commodore, which is basically used to store the information in the floppy disks, and then you actually have a actually screen which has a resolution. So it's basically much poorer than that this actually normal phone that nowadays people used to carry, which is not the smartphones. And think about actually the typical RAM, which actually was only 64 bits in around which was actually this computer was run in between 80 and 8 in the early 80s and so on. And the storage was at around 10 megabytes. So think about that, that how much folds we have actually increased the storage, and also the speed of this kind of device, the computer speed is many, many hundred times faster, and these RAMs are actually 10,000 actually times faster than those in 80s. So now, then you can ask a question yourself that how much smaller you can get. So then you probably know this about this Moore's prediction in 1971 that since this tremendous progress about this information technology, that every year that the number of transistors in a processor increase, and they increase exponentially. And here actually this is the transistor count as a function of the times, which actually shows that every alternative year you have like a doubling of the number of transistors in your microprocessors. And of course, that you can think about that the transistor was discovered in 1947, and immediately after the first microprocessor was actually consist of thousands of I think 5,000 of transistors, and then over the times you have nowadays how many million of transistors in a microprocessor, and then always you can ask that how smaller you can make your device, or the smaller the processor, and then what is the limit you could reach, and once you get it smaller and smaller this processor, then the another thing is very important, that is the power consumption. You know that your device gets hot a lot over the time. So how we can get an alternative device which have a low power consumption and also faster and smaller, and then ultimately you can think about that if you can store the information in a single atoms, that ultimate limit, and this is why you need to study the individual atoms and also their interactions in down to atomic scale, and this is one of the reasons why the scanning tile microscopes actually basically is very important to actually not only just study the fundamental interaction of the individual atoms and their visualization, also you can build up also by using atom manipulations, very tiny small device with a full controls. So there is other things is that in the normal CMOS device, you actually store the information in as a charge in a capacitance, and you can actually use the gate control for the processing. But alternatively, people are thinking that why not to store the information in a tiny magnet made of single atom of the cluster. So that's how, and the information technology will be replaced by the alternative materials. And this is why the interaction of the individual magnet and magnetic spin is very, very crucial. That's what we are going to understand using scanning tile microscope. We can even understand the interaction of the atoms and their spin as well. So now you can just think about, by forgetting everything what I just said, the iron atoms in iron is a ferromagnet used in a refrigerator, and a one single atom which is basically 10 billion times smaller than a meter. The meter is, you can think about a table. And so question is how we can visualize such a small object. And there is a number of ways to visualize since the electron microscope came into play. So just to think about that, typically in our eyes, which has a resolution in order of submicrons, and if we use light microscope, typically used in the biology labs, we can go down to a micron scale, even submicron. Even nowadays, with powerful light microscope, you can actually go actually couple of microns or less than couple of microns. But since electron microscopes came up, then it turns out that you can actually, instead of using light, now using the electron, you can visualize the object with the high spatial resolutions and down to single atomic scale. So that means using electron, you can actually, if you use the light microscope, you have to actually basically zoom to visualize the atoms the 10,000 fold more. And so this is the electron microscopes, which is basically in case of scanning tile microscope, electron microscope which works in the Spooky principle of the quantum mechanics, so-called quantum mechanical tunneling. And you probably know what is quantum mechanical tunneling when you study the quantum mechanics. So in order to understand this quantum mechanical tunneling, you can think about that You can have a light bulb in a circuit and you charge it. In classical, you can think about if you switch on the battery, then you basically can actually start flowing the current to the battery, and by um, basically you can flow the current when there's actually then light bulb will glow here and then electron will flow through the circuit. And you can also think about like that, that if you can disconnect the circuit, say your light bulb filament got broken, then classically you can think about that electrons cannot pass through the circuit anymore because there is a gap. So your light bulb will not glow anymore. The quantum mechanics says that yes, it is even possible that electron can flow even there is a gap, that there is discontinuity. If this gap is very, very small, then electron can still flow. And what is this flow of the electron is called tunneling of the electrons through a small barrier gap. And then you can still actually see the current in the circuit. The question is this simple understanding, can we build a powerful microscope using this fundamental about the quantum mechanics of so-called quantum mechanical tunneling? So you probably have seen this picture before, that this is that if you have you and your enemy separated by some kind of barrier, then actually to catch you, your enemy has to overcome this barrier. But if the barrier
You have frozen, it seems.
The voice has gone. Hello, am I audible? Yes, I'm not.
Yes, sir.
Sujit, you have.
We will rejoin in a while.
hello, Bisal.
Yes, yes, yes. You're audible. You can keep your video off and just give your presentation.
Yeah, sure, I'll do that.
So,
Yeah, I'm sorry about these
no,
interruptions. It's actually, yeah, this is actually in the campus in the last few days. I don't know what they're doing. Um, anyway, so I shared the screen. Is it visible now, Vishal?
yes, yes, it is visible. Yes, it is.
Okay, so the point I was trying to make here that the probability of tunneling one actually particular object from this side to that side is actually very much depends on the what is the width of the gap or the width of the barrier. And it turns out that if you can solve Schrodinger equations and think about the electron going from one side through the potential barrier to the other side, then you can see that the flow of the electron from one side is basically very much exponential depending on the width of the barrier. And based on that, the question is whether we can actually build a microscope with this principle. And this is what exactly was done by actually two persons from IBM Zurich back in 1981. And this is the Rohr and Breinig, and they got Nobel Prize in 1986. And this is I think, the second Nobel Prize for the development of the instrument in physics. And And they actually basically visualize very fast times the surface of the silicon using the scanning tiny microscope with atomic resolution. This is their Nobel Prize winning image, and where they actually resolve the silicon atoms, where the silicon made of all your devices basically. And then it took a lot of years to get a very good atomic resolved silicon surface to fix the lot of aspect of this microscope. And this is the one of the microscope they actually first developed to and used to visualize this silicon atom first times using this principle of tunnel. And since then, there was a number of scanning probe technique has been discovered and developed, which is one of them is atomic force microscope, where typically STM works in the metallic system, and AFM you can also visualize the atoms of insulator and so on by measuring the interactions of your tip and your sample, and some other technique, magnetic force microscopy, and some lot of other scanning probe technique. So the question is how this technique works. So this I said that this works in the principle of quantum mechanical tunneling. So you take a very sharp metallic tip and you bring very close to your surface. As I said, the distance has to be around the order of nanometer, even less than nanometer, couple of angstrom typically. Then your sample is typically metallic and your tip is also metallic. You bring very in the vicinity. And then you apply a voltage between your tip. You can have a sharp needle and your sample. By applying voltage, you can actually pass a small tunneling current, which is very small. You have to measure them precisely. By this measuring the tunneling current as a function of the positions in real space on your sample surface, depending on what object on your surface, we can actually visualize the individual object by measuring the tunneling current as a function of your position of the sample. Let's just look in the small cartoon image that, so you have a sharp metallic tip, you fix that tip and keeping some distance, and you try to actually apply voltage between the tip and sample and move the sample from one position to another positions and measure and tracking the variation of the tunneling currents as a function of their positions. By measuring this tracking this tunneling current, if you can do rastering, you can actually basically can visualize the surface with very high spatial resolutions and typically in the sub-angstrom scale. And so these are the actually rastering over the lines and so on. And so this is the one of the real example that how the materials looks like using this microscope in the atomic scale. This is basically iron, a single layer of iron grown by molecular beam epitaxy on top of a tungsten single crystal. And this is a size of 50 nanometer or 50 nanometer area. And where you can see that the individual here, which is basically forms some kind of square lattice, which is the iron BCC lattice. And in addition of this basically arrangement of the BCC lattice of this iron, you also see some blobs, some actually defect, some also iron cluster. And this is the real material. So whenever you study materials and their properties, and the nanoscale, in the atomic scale, their structure is very often dominated what would be the property, your bulk properties. So it is very important to know what is in the atomic scale, how the sample, and what are the individual defect, what is the role on the bulk resultant property that you measure with the bulk sensitivity. Nevertheless, using this technique now, you can fully study, characterize the electronic and structural property down to atomic scale with a high spatial resolutions. And this is a, here I will show you one interesting thing. Hello, there is any question here? I see somebody unmute itself. If not, then I continue. So just I will show you actually small video. So this was actually a couple of images taken on the surface of the same surface of the iron, one monolayer of top of tungsten, and over the scale of actually 350 nanometer by 50 nanometer. And you see that in the atomic scale, the surface actually looks quite ugly. There is a lot of roughness. And the question is, whenever you grow a materials, even in the nanometer scale, very often your sample contains this kind of rough thing. So one of the idea on this working in this STMs to understand that that what is the role of this unintentional defect or impurity or the formation of the island or domains in your bulk property of your system. So this is a typical one of the scanning tile microscope instruments looks like, and this was the actually this actually lab is from Professor Pijandaga in Hamburg, and this actually microscope is basically this is your scanning tile microscope inside of this big cryostat. This is a cryostat to produce low temperature, and in order to synthesize the material with atom by atoms, you have a molecular beam epitaxy chamber, and this chamber and the microscopes also all are maintained in a very ultra high vacuum environment, typically in the order of 10 to minus 10 or 11 millibar, and in order to keep the sample clean for very very longer time, such that the mean paper is actually of this constituent element in the inside is basically can travel few kilometers before they collide to each other, and that way you can keep your sample very safe, and you can actually really can prove individual atom for many hours, even few days. So this usually typically this how this experimental setup works, that you grow some sample here, then you actually transfer that sample from your chamber in situ inside the vacuum from one chamber to another in your STM chamber, and then your chamber actually STM is also very cold at low temperature, have it actually which have a higher energy resolutions, and then you can actually track the surface with a high spatial resolution. So in order to understand this, how the scanning tile microscopy and spectroscopy work, let me go a little bit in details. So one of the advantage of this microscope that you can not only just visualize the surface with a high spatial resolutions, but you can also measure their local electronic property, so-called local density of states. So here I will explain you how one can probe the local density of state, both occupied and unoccupied state of your materials with a spatial resolutions with a high energy resolution as well. So typically in STM, you bring your tip very close to the sample, you apply bias and measure the timing time. That much simple. So in your typically your sample is metallic and your tip is also metallic. So you actually your formula actually electron is filled up to the formula for both your tip and the sample. So if you don't apply any voltage, there will be no tunneling current, whatever the gap is or the barrier width, there will be no tunneling current, because there is no unavailable state or unoccupied states that the electron can hop or tunnel from one tip to the sample or vice versa. So once we apply a little bit voltage, either positive or negative voltage, then the situation changes. So if we apply a negative voltage to the sample, then basically you change the chemical potentials, the Fermi energy of your sample, then you can have a situation that you have a lot of electronic state, which is occupied electron state. They can tunnel to the empty state of your tip. So when you apply negative voltage, then there will be electron will be tunneled from occupied state of your sample to the unoccupied state of your tip. So then that means by measuring those tunneling current, we can actually get information about those occupied state of my sample. In the vice versa, if you apply positive voltage, then your tip occupied state of your tip can tunnel to the unoccupied state of your sample. So you get information about the density of state of your unoccupied, density of state of your sample. So this way, by applying for changing the polarity, you can actually probe both occupied and unoccupied states. So technically, the tunneling current that you measure is basically depends on the, of course, the tip sample distance. It also depends on the what is the density of state of the sample and also the density of state of your tip, because those are the states which contributing to the electron that tunneling across these junctions. So typically the tunneling current is integrated density of state of your tip and the sample multiplied with tunneling probability, tunneling matrix elements, and you have to integrate over all the energy scale, all these density of state which is contributing to your tunneling current. By measuring this energy dependent actually density of state tunneling probability, you can measure the density, local density of state very precisely by measuring the change of the tunneling current as a function of change of the bias voltage. So by measuring the small change of the bias voltage, what is the change of the tunneling current, you can measure what is the density of state of your sample, and that density of state depends on the energy and typically close to the Fermi level, and that is called local density of state. If you want to know density of state of your whole sample, then you have to integrate over all energy scale. Here we made one approximation which is very critical also, but that we assume the tip density of state remain constant within the interested energy range also during the experiment. So that's why you have to make a choice of your tip, which also very much suitable. But one of the important things using this called spectroscopy, so-called by measuring the local density of state, by measuring the change of the tunneling energy function of change of the bias voltage, and you can do a full spectroscopy at different positions as a function of different energy. So that is what is called di by dV map, where basically you actually map out the density of state at a particular energy within the certain area of X and Y. So in this way, you actually get a spectroscopic for full spectroscopic information. So you get a topography, which is basically gives the real space image of your positions of the individual object on your surface. At the same time, you can also map out the density of state of the same area at different energy. So at close to the Fermi level, at zero energy, then positive energy and negative energy, you can actually map out the density of state. And once you know the density of state, you can actually basically know what is their electronic structure, because electronic structure is mainly governed by the what is your local density of state of its own. So this is how you basically do. Here actually I'll show you that in a laboratory how typically one actually do this kind of spectroscopy. So this is one of the my actually colleagues a couple of years back in Hale, it's Hiro Fumioka. He was that time scanning a cobalt island on top of a copper. Cobalt is a ferromagnetic cobalt double layer island on top of a copper single crystal. And I'll talk about this in details. You see that the sample is basically scanning, and you see that actually the height variation as a function of the positions. And then as you actually see that if you want to do the spectroscopy, you basically put your cursor, you bring your tip on the center of this island, and then you basically measure the change of the current as a function of bias voltage. This is the IV, and then you can also use the lock-in amplifier to measure the change of di by dV as a function of bias voltage, which is measure of the local density of state, so-called electronic structure. You can also not only just visualize the topography, you can also simultaneously track down the density of state of your, or know what is the density of state of this island and the surface and so on. So immediately you can also distinguish the material. So this is a cobalt island grown on copper. So this is actually, for example, this is the IV. I'm just not sure that my cursor was working. So so this is the IV and this is the di by dV taken on this cobalt island. So now we can move, for example, from this cobalt island to the copper surface, and then you immediately can distinguish that by measuring the spectroscopy with the spectral behavior is completely different. So by using these techniques, you can really actually distinguish the chemically also the elements. So for example, here you see that now I'll actually Hirofumi is bringing the tip from your cobalt atoms on the top of the cobalt island to the copper surface, and then he's basically measuring on the copper surface what is the spectral feature, what is the density of state locally at that particular position. So he bring his tip to here, and then he actually measuring now sweeping the voltage as a function of current, and then he see completely different type of IV nature and the step like density of state, which actually basically typically copper surface states and so on. So this is how actually this looks like, and usually these are the electronic components and oscilloscope, and you measure the temperature, and then there is the electronic component for the monitoring the scanner heads and so on. So this is the one of the example that was actually very remarkable, that people have actually first time visualized the confinement effect. So this is one of the sample which was basically a cobalt island. It's a double monolayer, or two monolayer, or two atomic layer of cobalt island grown on copper 111 surface. And if you actually measure that the density of state, or the di by dV on this cobalt island, basically clearly see that the density of state has actually very inherent variations as you change the bias put. And it turns out that this is actually cobalt minority D states, which is basically actually confirmed by theory, is basically this is the cobalt D states that you can probe locally on this kind of cobalt island. You can also measure the variations of the contrast, the density of by using measuring the density of state match as a function of different energy. And from there, you can also track down their modulation patterns, which actually comes from the confinement effect, which is basically electrons get confined within this actually small island, which is basically a very small object with the size of 10 to 20 nanometers of this island. There is a little variations. And all this blob that you see on the surface is basically, I'll explain a little bit later here. Those are the defect where electron is basically getting scattered, and also, and then when they form some kind of interference pattern. And so essentially what I wanted to say that you can actually measure the density of state of a very small ferromagnetic islands locally using this kind of scanning time spectroscopy with a high energy resolutions. So in addition of doing this kind of spectroscopy, one of the advantages to this actually spectroscopic techniques that you can also actually measure the band dispersions. So band dispersion is basically energy as a function of momentum. So you can actually map out this density of states over the area of your sample, say 40 nanometer, 20 nanometer at different energy if you measure the density of state. And by measuring the density of, you could do Fourier transform. From Fourier transform, you can actually measure the corresponding wave vector that actually responsible for the scattering at different bias voltage corresponding different energy. By plotting this wave vector, the function of energy taken at different bias voltage, you can really actually measure the band dispersion. So typically, this is a ferromagnetic metal. It's like a free electron-like gas in the system. So it has a kind of parabolic band that you see this one branch of the parabola, and that actually I can measure the experimentally very, very fast time on those days. So typically the STM works in the two main operating mode. One is the constant height and constant current mode. So typically if you have a sample which is typically very rough, you don't know their characteristic, then it is better to measure in constant current mode, because the tip, you can avoid the crashing of the tip. In constant current mode, so you bring your tip close to the sample and you ask that keep the current constant and actually raster the surface. Depending on what you have in the surface, then in order to keep the current constant, you have to bring the actually tip either closer or far away, and you can track down the surface morphology in the constant current mode. That typically apply if your surface is quite rough. So on the other hand, if you know that your surface is very, very smooth, then you can also image the surface with a constant height mode, where you basically keep your sample and the tip distance constant, and you actually measure the change of the current as you move from one position to another position. And that's in that mode also you can actually visualize or you can measure the topography of the sample and track down what is how looks like the morphology. So I'll quickly give you the few examples. So this is about 40 minutes. I already spoke with some interruptions. So I was talking about this copper surface, which was basically one of the surface of the noble metal surface. You can easily clean them in an ultra high vacuum. If you look those surface with this kind of high resolution scanning telemicroscope, the topography will look like very smooth, large terraces, and then there will be some kind of atomic layer steps, which is basically gives another terrace. So this state age, if you look very carefully in the local density of state map, at the state age you will see very unique features. So typically, if you zoom in this small area in the topographic image, then you will typically see the atomic resolutions, which are individual copper atoms. But if you look the spectroscopy, the variation of the local density of state at particular energy, then you will see at the state age, there is some kind of modulations of the density of states. If you just look actually a little bit different energy, then you basically clearly see this modulation very nicely. And this basically this modulation caused by the fact that electrons in your copper surface is basically on the surface, those electrons are basically kind of free electron, but they cannot escape from the surface because there is a vacuum barrier. And then those surface electron also trap from the bulk, because you have a bulk state. Between bulk and the surface, there is the energy barrier, so electron cannot also go to the bulk. So that means the electron trapped within the surface, they cannot escape. But and these electrons are moving in your solid on the surface. When they see a step edge, so that is kind of barrier, they get scattered back. So then you have an incident electron wave, and then scattering electrons actually get in return from the step edge. They actually interfere. They can actually make a constructive or destructive interference. So when they make constructive interference, that you clearly visualize in your local density of state map. That's what you see here very nicely. So here you see also there is some copper defect, which is the absence of copper atoms, or there is excess some additional atoms or absorbents. Whenever also there is electrons, free electron gas, see those defect, they also get scattered and reflected back. And that's why around this defect, you also see huge scattering amplitude. So if you zoom in those two defects, you see the modulation of this density of state getting very, very strong at the defect center. And actually, these two actually scattering processes also again interfering each other and giving this kind of miraged image, which was very remarkable using the scanning tunnel microscope in those days. So that what was I was saying, that why this copper surface showing this kind of unique feature, that if you look the energy as a function of momentum, so-called band structure within actually in the K parallel momentum, then you will see that electrons in the surface of your copper has one particular band, which is surface band, surface electronic state here, and this is the bulk band. So those electrons who living in the surface actually get reflected at the step edge or the impurity, showing this kind of interference pattern. And these surface states actually can be directly measured by measuring the density of state as a function of energy. And this is what you see here. This step-like behavior is a true measurement of this kind of the surface states of the copper surface is coming from this band. And you can also actually measure a lot of important parameters, which I'm not going into details. So you can also measure this kind of modulation of this density of state of the copper surface at different energy, because this density of state is an energy dependent quantity. So if you measure at different energy, at the topography, you don't see them in a flat area, but once you look at the density of state map or di by d map, then you basically can see that there is a modulation around those defects, and this modulation is actually changing as you change the energy. So this is a local density of strain. If you do a Fourier transform, then you go to Fourier space or K space or Q space. From there, you can actually extract what is the scattering vector that is responsible for this kind of interference modulation patterns. And by measuring this wave vector, you can really measure the band dispersion. So if you do a Fourier transform of this kind of image at a particular energy, you will get this circle. By measuring this diameter, you can actually calculate what the scattering wave vector, and you can measure the scattering wave vector for all this image taken at different energy, and then you can actually measure the band dispersion, so-called energy as a function of momentum. And it looks like that copper has a parabolic band, and that you can measure this parabolic band using the scanning tunnel microscope. There is another technique you already maybe heard of. This is called angle photoemission spectroscopy. Works in principle for photoemission spectroscopy, where you can actually directly measure the band dispersions. Because it is a momentum resolve technique, you can also compare those with the measured scanning tunnel spectroscopy that fits very well. So this angle photoemission spectroscopy is a momentum resolve technique, is basically another complementary technique of scanning tunnel spectroscopy. So here I may actually say that the STM just not only can visualize the object with a high spatial resolution, you can measure the electronic state also with a high energy resolutions, and by measuring that this local density of state as a function of energy, you can also really measure the density of state locally at your sample with at different energy, and you can have access of your momentum, which is very important element to understand any kind of properties of your mixture. So just to give you another example, you probably heard a lot about graphene and this graphene you can also actually, it's a graphene is basically a honeycomb lattice of carbon, and this graphene you can really can create by exfoliating a graph from graphite or HOPG. But typically in STM, we actually used to synthesize the graphene on top of iridium by molecular beam epitaxy. And this is the graphene island grown on iridium in ultra high vacuums. This is the small graphene island. If you zoom in those island, you will see those actually carbon atoms form this honeycomb lattice. And these islands has a different size. And on this island also you can actually see this kind of interference patterns because of the confinement of the electrons, and they also have a energy dependence because you see the modulation changing as you change the energy from actually -1 volt to actually plus close to Fermi energy. So by measuring again the Fourier transform and then measuring the corresponding wave vector as a function of different energy, by doing this, you can also measure the band dispersion of this graphene. As you know, the graphene, you have this linear band instead of parabola, this relativistic like Dirac-like dispersions that you can also measure by the scanning time spectroscopy that what actually Park and Kishner showed back in 2011, that you see this kind of linear dispersion in the graphenes and from this kind of local density of state of the matter. So this is another image which was very remarkable, done by actually IBM, this Eigler and Cromie. It was back in actually, I think it was close to late 90s. So here actually, this is the same copper surface covered with they actually used 48 iron atoms. They actually arranged by using atom manipulations technique. And then they actually see the modulations of this density of states of this copper surface state electron inside this quantum coral. And this kind of visualization is the first, the quantum mechanical variable electrons for the nature of this wave is first time shown by artificially arranging the iron atoms in the form of quantum coral. So this was very remarkable presentation using scanning time microscope and so on. So nowadays, a lot of people also apply this kind of scanning time microscopy technique to visualize a lot of phenomena. It's a new type of material like topological materials. So this is one of the topological insulating materials, which is called bismuth chloride. It's a complex compound, which unit cell is a little bit complex. It has like a tellurium as bismuth as alternative layer. This green balls are the tellurium layer, and then alternative bismuth and tellurium is a layer compound. So within this layer compound, we can exfoliate very easily and always get the tellurium terminated surface, which are hexagonally arranged on the surface. So if you look those surface on using microscope, then you can see the clean surface, which is very well defined terraces. The height of this each corresponds to integral of this quintuple layer height, which is about 9.4 angstrom, that you can measure by the lines profile of this image. And if you zoom in this image, you can easily clearly see the hexagonal lattice, which is basically represented by this the tellurium atom on the surface and form this hexagon. In addition of that, you see some kind of interference patterns. Even in the topography is basically due to some defect, which is basically very often the bismuth and tellurium atoms, they replace each other. And this is a topological insulator material. It has also some surface state, and those surface state electrons also get scattered by those defects. And this scattering phenomena can be visualized using this microscope by this kind of topographic map. And using STMs also, in the scanning time spectroscopic mode, you can also map out, actually measure the density of states, which is basically can be compared. And you see this minimization of the density of state, which represent the Dirac points, which is the Dirac state of this topological insulator, which basically complement the measure of the RPS measurement, which is basically angle range of potential spectroscopy, measure the band structure, actually very precisely as a function of energy. And in case of STS, you basically measure for a particular momentum, and as you switch the energy, then you change the momentum. So as a moment, and you can measure the density of state function of momentum, and you can measure the Dirac point very precisely, and which can actually confirm the measurement of the RPS using the scanning time spectroscope. So now I switch to the next part of the talk, which is about spin-wise STMs, which actually, if you have any question, then you can stop here and take the question. Is there any immediate question? Do you have any question?
Anybody having question can unmute themselves and ask. Is there? Okay.
Okay.
Most
Yeah?
likely they will ask
Oh.
at the end of the session.
Okay, yeah, very good. So I continue. So then actually after actually showing that we could resolve the surface with high space resolutions, and we can also map out the electronic structure, electron density of state with a high energy resolutions. Now the question is, can we actually resolve the spin of the materials or the atoms using these microscopes? And the answer is yes. That's what I'm going to show you. And this is all about the question is, can we actually understand the magnetism of a single atoms, the atomic level? And this actually brings me to the technique so-called spin-point scanning tiny microscope. Spin-point scanning tiny microscope is nothing but spin-resolved scanning tiny microscope, and it basically works in the principle of scanning tiny microscope with a additional phenomena so-called tunneling magnetoresistance. So in case of spin-point scanning tiny microscope, you basically replace your metallic tip with some magnetic tip, which is basically generate the spin point actually electrons. And you know that tunneling magnetoresistance is a phenomena which was basically discovered a couple of got also very Nobel Prize for GMR and TMR, and which says that if you have a two ferromagnetic layer separated by insulating layer, then the resistance of your device actually depends on the relative orientation of your top and bottom ferromagnetic electrodes. So if top ferromagnet and bottom ferromagnet, they are aligned parallel to each other, then your resistance will be low and you have a large current flowing from one ferromagnetic electrode to another ferromagnetic electrode through this insulating barrier. And if a ferromagnet, the top ferromagnet and bottom ferromagnet, that anti-parallel, their moment are anti-parallel, then you have a large resistance, you have a very small current. So we can see that in STMs, we can actually realize the similar phenomena mainly by following this way. And this particular technique has a lot of applications. So it has actually addressed a lot of fundamental questions about the spintronics in spin-point STM. So essentially, you can talk a lot about atomic scale spin texture and magnetic phenomena using the spin-point STM. You really can study the magnetic nanostructure even down to single atom or molecule. Even using spin-point STM, you can study fundamental interaction like exchange interactions and Celsius-Mourier interactions and their interaction constant, interaction energy. You can also study a lot of phenomena like Kondo effect and different kind of spin-point surface state and so on. And this technique also, people have shown that you can actually combine this technique with a atom manipulation technique, that you can create a logic device where you can show the spin-based logic operation in the atomic scale. And nowadays, this technique also has been used to apply for the smoking gun experiment for the detection of some exotic quartz particle like Majorana fermions. So now I'll tell you how this works. So as I said, that spin-point STM is basically in the spin-point STM, your tip is basically spin-point. That means it's a magnetic tip. It has some magnetization direction. So you basically have a tip with a magnetic material. So it will have some magnetic anisotropy. It will actually, the magnetizations will have some preferential directions. If you bring that tip in close to your magnetic sample, then keeping some distance, keeping some vacuum barrier, depending on the relative orientation of your sample, you will have a deep tunneling current. When the tunneling current actually will be very, very large, when this magnetization of your tip and the sample are parallel, you will have a large tunneling currents. And when this tip magnetization and the sample magnetization is anti-parallel, when you bring this tip to here, then you will have a small current. That's what is the TMR phenomena. Explain that. So by measuring this position-dependent spin-point tunneling current between the tip and the sample, you can actually measure the magnetic structure of your sample down to single atoms. This is how it works. So I will tell you a little bit about this in the spectroscopic point of view. So just let's first look at this. So you bring a very small magnetic cluster added magnetic tip close to your sample, which is magnetic. So depending the relative orientation of your sample and your tip, you have seen that the tunneling current is different. If you want to keep the tunneling current constant, then tip need to either move closer or get away from the sample. And depending by measuring that, the change of the tunneling current as you go at different positions, you can really visualize the what is the magnetic structure of your sample. So this is the actually conceptual actually section to understand this kind of spin poised tunneling phenomena. So in spin poised STM, you can have a very simplistic case. You have a tip which is magnetic, and you want to resolve some magnetic sample which has a some kind of well-defined magnetic structure, has a magnetic anisotropy. So your tip and sample are both magnetic. So in simplistic case, if we assume that tip and sample are both are parallel, having some vacuum barrier, then if we look at their density of state, so let's assume that tip and sample both is ferromagnetic. And ferromagnetic, your density of state has a spin splitter density of state equal to Stoner criterion. So spin up density of state and spin up down density of state are asymmetric, they're not same. So your tip has this kind of spin poised density of state, and your sample is also magnetic, which has also spin poised density of state. Now, when you bring them closer together, if you look the tunneling possibility, then in case of when they are parallel, then you can see that there is a many tip electronic state in the downspin channel. That electron can tunnel to the downspin channel of your sample to the empty states. So you will get a large tunneling current from when they are parallel. On the other hand, when this tip and the sample are anti-parallel, then you will see that in downspin channel only few tip state electronic states that electron can tunnel to the few empty states in the downspin channel of your sample. Then you will get a small tunneling current. This is what I've shown in this cartoon image, that depending on the relative orientation of your tip and the sample, you will have a different amount of tunneling current. By precisely measuring the spin poised tunneling current, you can actually determine what is the relative orientation of your sample magnetizations with respect to your tip magnetization. And typically, you need to characterize the tip magnetization first, and then without changing that, you can actually measure the unknown magnetization of your sample. And here also there is a lot of tricks, and typically the tricks is that you need to actually produce or create a very good spin poised tip, which actually typically people use. You have a non-magnetic tip, you cover with very small thin layer of magnetic film. Typically you can take a tungsten sample and you actually anneal at very high temperature. You remove all the oxide in tungsten in the ultra, and then you deposit some layer of iron or cobalt or chromium, some magnetic element by molecular methylation, have a nice thin layer which have a well-defined magnetic anisotropy and which is very stable, does not change when you raster or scan over the surface, and it will give a very precise magnetizations in a particular the in plane or outer plane. And in order to do the spin poised STM, you always need a external magnetic field to change the magnetization of your tip and sometimes also sample. And this is how you know the exact magnetization of your tip to reveal the the unknown magnetization of your sample. This is one of the very important example. This was like one of the first spin poised tunneling was shown on the chromium surface, and it took many years to get to this point. This is a chromium, which is basically an antiferromagnet, which is basically in this chromium. If you look with a non-spin poised tip, normal scanning tiny microscope, the topography will look like this, which basically nothing but the different terraces, which has a basically different height, which is one atomic layer height. And now if you look the same surface with a now magnetic tip or spin poised tip, then you will see that that the modulation of the spin poised density of states, and which basically looks like that the spin in one terrace is oriented is actually in opposite direction with respect to the other one. So it's like a each layer actually has an opposite magnetic magnetizations with respect to the another layers in the chromium surface. So this is the spin point density of state modulation, the height variations of the spin point density of state as a function of lateral positions. And this is actually the very first time the model actually mapping out the spin point density of states in real space using the scanning time spectroscopy. Here is the another example that again we have deposited some monolayer of iron on top of a tungsten. This is the iron island, and if you look the contrast of this oil island using non-spin porous tips, it looks very similar, the contrast. And this is your tungsten surface, and this is the just a one monolayer of irons. And when you look by spin poise scanning telemicroscope, the same iron island on tungstens, then you would see depending on the actually which island you look, have a different contrast, which basically caused by the relative orientation of the tip or with the magnetic magnetization of your islands are different for different islands. And these are the tiny nanomagnet. It has basically have a different kind of magnetic anisotropy and favor. And one island is favoring the magnetization of this direction, and the island is favoring magnetization in other directions. Also, by measuring the spin poise tunneling, you can actually really visualize the magnetization directions of these individual nanomagnets with a high spatial resolutions. People even got further, and by using this atom manipulation technique, they actually not only just create some kind of artificial atomic structure on the surface. This is the iron atoms actually on top of copper surface, and they actually deposit the iron randomly, and then by using atom is spin actually scanning telemicroscope, they arrange them, make it this kind of one-dimensional array or this kind of Lego, and they also could measure the spin poise tunneling. By measuring the spin poise tunneling, they could identify that depending on the distance of those iron atoms, they have a different type of coupling. For example, one iron atom to the another atom, they are basically antiferromagnetic coupled. These two iron atoms ferromagnetic coupled, and this is basically a distant dependent exchange interactions. It's caused by this kind of phenomena. And by atom manipulation, they can actually play the distance between them. So using that, they can really tune the magnetic interaction between the two neighboring atoms and create a artificial magnetic nanostructure, whatever they want. And this is very cool that using this kind of spin poise tunneling, they can detect not only the spin of the individual atoms, what is the spin orientations, but they can actually play the interaction of the individual atoms depending on their spin. So even few days later, they actually, this Friesen-Danger group, they have actually also measured the magnetization curve of this kind of single iron atoms on top of a copper surface by measuring the field dependent, the change of the spin poise density of states of by bringing the spin poise tip. And this is what is the actually shown it here, that they measured this kind of density of state as a function of magnetic field, which you can think about the spin poise density of state is basically equivalent to the magnetic moment. It's like a history, basically image curve. And you see that of a single iron atoms on top of a copper, actually showing this kind of behavior. These are the black dots are basically showing the major density of state function of magnetic field for on the single atoms. And this is actually fitted one. And you see that the single iron atom on top of copper do not show the hysteresis loop, which means that it is not a ferromagnet. So it behaves like a paramagnet. But if you have a ferromagnet, single iron atom is supposed to be ferromagnet, you should see this kind of hysteresis which have some kind of remnant magnetization. But here that there is no remnant magnetizations. When you switch off the magnetic field, the actually magnetization or local density of state also becomes zero. And by theory, also combining theory, they have also estimated what is the magnetic moment of these individual atoms, which is around 3.5 Bohr magneton, and the bulk value usually per one iron atom, 2.2 Bohr magneton, and or in this the 3 iron atom is around 4 magneton. So depending on which environment, here iron atom is actually in the copper environment on the top of the copper, it's basically have a different kind of magnetic downstream and amount of magnetic moment. Here really big question is why the single iron atoms is not ferromagnetic at all. So one of the reasons it was not ferromagnetic because it was not stable. It was continuously moving, although this experiment was done at very, very low temperature, around 300 megakelvin. So if it is not ferromagnetic, that means one single iron atom cannot hold the information, it cannot store the information, single iron atom. So immediately that was the question, that how many iron atoms, so you need to actually store one bit of information, and then that's why you have to make the iron cluster to make it ferromagnetic. So one single atom really behaves like a copper atoms, which is not attract each other. So a couple of years later, they actually able to actually make a cluster of, by moving a couple of iron atom. Here is the 5 iron atom. They move to one positions and then form a 5 iron atoms cluster. And then they measure the stability of this 5 iron atom cluster. And by measuring this kind of histogram, that's height as a function of time. And they have shown that this 5 iron atom cluster has a huge stability of many hours under small magnetic field. And usually if you have small magnetic field, this cluster is switched very fast from different magnetic state, from up and down and so on, switching. So they are not stable, but just applying sufficient magnetic field, they can stabilize this 5 iron cluster is very, very long time, and which is ferromagnetic, and measure the hysteresis loop. And this group also has able to actually measure, show that this kind of magnetic Lego by creating a spin logic operations, by creating atom manipulation. They have actually create some electrode by the magnetic islands, and which is considered input. And by arranging the iron atoms, they have some kind of gate, which is actually produce kind of output. So they can send the informations from this kind of input of this electrode, and then they can track down or what is the information that is sent from this input, and then measure in the output by using spin poise streams. And they shows first time this kind of logic operations, both OR and NOT gate operations, using this kind of single atoms in this kind of cobalt island on top on this kind of cobalt atoms, by arranging, by adjusting their distance. I really insist you read this paper. They have very fascinating and breakthrough works. Yeah. I think with this I almost came to the end. So, Bisal, I think I'll stop here, and open for some discussion possibly. Bisal, are you there?
Yes, I'm here.
Yeah.
So the floor is open for questions.
So, Bisal, do you see any question from the chat or something? Yeah.
Yes. There's a question. How do you control the atom basically using an STM?
Yeah. So the idea is that, for example, that yeah. Let me see. So actually, this kind of technique called atom manipulations. So you can have a surface, very clean surface, and you can actually deposit in materials or atom by atoms on this surface, in cold surface, by molecular beam epitaxy, very small amount. So fraction of monomer you deposit on the surface. Then you have an individual atom on the surface that you can visualize or resolve by normal scanning time microscopic image. But then you bring your STM tip very close to your individual atoms, and then you bring it so close that you then actually you can touch or actually the individual atom by your STM tip. You have to make sure your tip is also single atomic, and then if you apply a voltage, then actually large voltage pulse, then you can really pick that atoms by your using this your atomic single atomic STM tip. And then we can withdraw the STM tip. You can bring the STM tip little far away with your desired positions, By applying the reverse voltage, you can again apply pulse voltage, the opposite pulse voltage. You can drop that atoms to a desired positions. And then you basically can have a atom manipulation. So you can bring one atom from one position to atom by using atom manipulation technique. And this is actually done by basically measuring the height of this atom in the function of positions while you apply. It's a drop down technique. So you pick up the atoms and by a voltage pulse, and you also drop the atoms by again applying some voltage pulse with a different polarity. And then you have to measure that whether really it is moved from that place to this place. So when you move, then this place there will be no atoms, then you will see additional atoms. So you have to scan before the movement, actually this atom manipulation or operation, and after that, and in between also several times. Yeah, is that answer your question?
I hope so. And another question is, how do you define the size of an atom?
Size of the atom. So it's
boundary of an atom, like
yeah. So it is very easy. For example, this you can have a example. Let me maybe I will bring some image which um, yeah. So for example, so this is the bismuth chloride surface where we see the tellurium atom in the surface. So if you draw a line scan, first of all, that this microscope has a special resolution in the order of picometer. So that means it can resolve two objects with specially separated in even the angstrom can very precisely because the resolution in the picometer. So when you measure the topography, then you see the position of the individual atoms. So if you draw a line from 1 atoms to say 10 atoms along this line, then you know that what is the area 10 atom cover, what is the length. Then you can actually measure the distance between the individual atoms. So by measuring the individual atoms, you can also measure the separations. And if you draw a line scan along this atom, you can also measure the separations. What is the size of those atoms in the typically few hundred of picometer.
okay, it seems like the question is like the size of an atom. Atom is mainly 98% vacuum, and there's only electron clouds around there.
Yes.
So that's why that's the reason I think the question has been asked. How do you define the boundary of an atom rather than since all you have is a haze, right?
Yeah, that's actually a very good question. Let me show you. So these are the individual atoms. We are saying these are the individual actually iron atoms, and in STM is all about this tunneling currents. It's basically integrated integrated density of state of the sample. So when you talk about that, this is the position of the atom, this is the atoms. We are basically saying that how the modulation of the density of state around this area. So we can measure the modulation of the density of state around that area by measuring the spatial variation of this density of states around these positions. And so we can say that this is the positions where the atom is located, and by changing the bias voltage, changing the tunneling probability and looking the density of state, the contrast of the density of state around this atom will also change. From there, we basically also say. But in STM, you always measuring the probability of the electron, the tunneling at a particular energy. So until unless we actually know all the energy, the tunneling, what is the tunneling taking place, we cannot say what is their full density of state of your atoms or around this atom. So we cannot really say that what is exactly the inherent structure of the atoms. The resolution we are basically can say this is where the atom is located, and this is the variation of the density of state around these atoms at particular energy. but we cannot say what is the internal structure. We can basically what is happening that in individual atoms, you have this electron cloud. Basically, those electrons have some kind of, when they actually have a many atoms or the, then you have a, some kind of environments or some kind of density of state or the states where basically I'm tunneling the electron from my tip to the that area. So those states are involved to contribute or giving this kind of tunneling current. So it's very difficult to say that what is the internal structure, but you can certainly say that what is the exact density of state around that atoms in that particular energy. Because you can think about that this sample, this topography was measured at particular energy. So it's an energy dependent actually contrast that you mostly see on the surface.
So it is basically the potential distribution on the surface, is it?
Yes, yes. Something like that.
Well, someone asked a question regarding the indistinguishability of electrons and atoms. Well, that's not clear.
No, I mean, here basically indistinguish. I mean, the atoms and electron are distinguishable anyway. um, I don't know what we actually mean by this indistinguishable of electron, because you can measure the flow of the process, actually motion of the electrons by measuring the current. And here also you can also measure the position of the individual atoms in distinctly, separately, that they are really located in that particular position. This is the copper atom, this is the cobalt atom, so you can say that. And by measuring the tunneling current, you confirm that electron is really flowing from one of your tip to your sample, or even you can measure the bulk transport properties like measuring the resistance of your sample by flowing current. Also, that prove that there's a flow of electron. Yeah.
Okay. Another question is, why is there a need for epitaxy?
Yeah, so the reason is that we always so epitaxy means that that you want to, so especially in this epitaxy, this word is comes when we talk about thin films and growing some small thin layers of materials. So that means epitaxy means that having like some kind of symmetry of your substrate and your films. So when you talk about that one film is growing on the top of another substrate, epitaxially means we are basically, if we take a silicon 111, and then if you want to grow a lead film on top, if lead film grow also on the in the direction of 111, then we say that lead film is grown epitaxially on top of silicon, and it's also preserve the crystallographic symmetry of your substrate. And very often it turns out that materials also properties depending on what is their crystal symmetry. So very often actually we also interested to grow a particular single crystal with that kind of symmetry, crystal symmetry. And there we really essentially choose very smartly the substrate with a particular orientation such that we grow a film on the top, it also follow the same with a have a minimum lattice mismatch in the same direction. And there it's really. So nevertheless, if you do not care of the epitaxy, then very often your films, the size of your film will have a, it's very actually very, will not have very continuous, will be not very flat. It will have a domain, it will have multiple domain or 3D island like variations. It will not give a two-dimensional flat sample, which you essentially want to study the electronic phenomena in a thin film. So it is really, particularly in surface science community, people actually care about, but very often in the reality, when you intentionally want to grow epitaxial film, after a few layers, then epitaxial relationship cannot be hold, then there is the formations of small island and cluster and so on. So it is very common that, but epitaxy is, it's basically essentially is important to have a materials with particular orientations. We have a particular with some particular properties that you want to actually create or realize.
Okay. Then there is another question regarding which metal is used in making of the tip. I mean, possibly he means what are the criteria on which the metal, the tip is selected, metal used
Yeah,
for the.
so this actually actually already said once that um, so typically you can choose any metallic element and you have to make it very sharp like a needle, and but there is some choice, the preferential some choice of the material. Typically, you use some materials like tungstens or platinum, iridium, which are very basically materials which are does not get easily oxidized and also very robust. So once you make the tip very sharp, it also stay very robust for a long time. It does not drop within individual atoms. So in ideally, you want to make a tip which apex will have a single atom or few cluster, and you don't want to see that cluster of the atom does change over the time. Okay, so that's why you need a certain material which is uh, does not chemically inert mostly and does not get oxidized. And this is there is a couple of choice, but in principle you can take any metallic element like you can take a copper or gold or other materials. But in generally in the STM lab, that's actually professional STM labs, the people use mostly tungsten and platinum iridium, because in tungsten you can actually it's basically it stay very inert very long times in ultra high vacuums. Like if you want to, once you remove the oxide layer from the tungsten, you can keep it very many days, even sometimes months without any contamination. Platinum iridium sometimes a good choice that you can actually operate them. It does not get oxidized so easily. You can operate them even at room temperature. But some other tip like gold is also works very fine. So the choice is up to you. For example, if you want to do spin wise tunneling, then you choose some magnetic tip. You have to make sure your magnetic film or the tip made of magnetic material like chromium does not get contaminated so easily or does not get oxidized, and it also does not drop some atoms. It should be also very strong. It does not drop over the time some atoms from, and then your shape of the tip will change over the time when you scan. So it is very, you have a like a lot of open choice of any metallic tip, but typically you can actually tungsten platinum.
Okay, can alloys be used instead of metals?
Yes, that is a platinum iridium itself, the alloy that I just said. And so people typically use some polycrystalline alloy also to use that is, yeah, to
Okay.
make it match.
Okay. So the answer is yes. Can can we find the magnetic domain in FE using spin polarized STM?
Yeah, certainly there is a, I not show that kind of information, but and there is a really plenty of paper on this direction that visualizing the domains of ferromagnet and antiferromagnet and some complex spin structure like scarmion by using spin poise STM. So by using spin poise STM, it's not only the spin resolve, it's also spatial resolve. So typically in ferromagnet, you have a domain, you can really see at the domain boundary, there is a change of the magnetic orientation of the spin of these individual atoms that you can clearly visualize using spin coexistence. You can find there is a lot of papers from this Hamburg group about this resolving the domains of a magnetic ferromagnetic films on top of ferromagnetic also substrate.
There's another question. How are impurities distinguished on the surface if the surface is imaged as the function of tunneling current?
Yeah, so actually, yeah, that's very good questions. That first of all, you you know that STM is basically a real space technique, and let me bring one slide to discuss about that. Uh, Yeah, so maybe here, not sure. Let me try to explain it. So, uh, first of all, using STM, you can map out your surface or your sample with a small area, say few nanometers. And then, if you are good enough with the scanning, then you can also resolve those individual atoms if it is single crystalline. And then you have to identify if suddenly you have some FCC structure, you will expect some kind of hexagonal arrangement or cubic symmetry on the surface. Then you suddenly see that there is one atom is missing. And then you can clearly see in real space that one atom is missing. And then you clearly say this is the defect, that absence of one atoms. That the question is, if you have, you also see that in real space that you see that in a hexagonal surface there is additional atoms. But then you can say also this is the additional absorbers which also create a defect on your sample, which also can be visualized. So by measuring a real space, by measuring with a high resolution, actually topographic map, you can distinguish that. But it is always challenging to identify what is the chemical identity of that defect. It is quite challenging, and that's why you have to do spectroscopy. You have to do spectroscopy in that defect. You have to identify what is the exact electronic structure of that, how they are different from the electronic structure is expected from if there is atoms in that defect area. So by comparing this, you can always understand what is the defect and what is their chemical identity and also the structural identity. So it is possible because you visualizing the surface with high spatial resolution. So you can identify the location of the defect. You can also identify their electronic structure by measuring the vicinity of the defect and also far away from the defect and comparing the di by dp or local density of state map. Okay, is that I don't know.
I think there are more questions. I'll just check if anyone faces. Okay, that's it. I think.
Okay.
Anyone you can post on the chat, the Telegram, as well as YouTube, as well as in the chat box. And you can unmute yourself to ask question as well if you want to.
Yeah. Sujay Dadwila, yes. I'd love to see you.
Hi, sir. How are you? Yeah, good to see you, sir.
Hi.
Thank you. I was actually nowadays. How are you?
I'm good. So how are things with you?
Yeah, going slowly. Then I took some students, 3 students, and they started, and then every time there's a pause, and they had to return, and then it is very difficult to continue. Even could not spend the money that I had this small project from SRG 2 years. Could not spend. That was going to finish in December. It started 2020 January. Could not finish this money, even small amount of money. So I'm trying. They came back trying, and we actually have this small one. Actually bought some controller from this Quaja instrument, Quaja Tech. I bought a controller cheap, and then I have a one build up little STM head, and I can scan HOPG and I can show you some image sometimes, and they looks promising. But if I get an opportunity, I want to send my student to your lab if possible. That they really need to learn something to make a progress on that.
Possible. Yeah, sure, that we can. So let the virulence of the virus go down a little bit because now I think travel is difficult.
Yes, right.
But
Even institute are not allowing for external students. Even they are not
exactly,
cannot handle their own students.
yeah, that's roughly the problem that we also have. But so you are, I heard IIT Delhi is buying a low temperature STM or something.
Yes, actually, there is a lot of details. I mean, it is very strange. So first of all, they actually, when I joined, before that, they placed an order
With
with
RHK and then they
RHK.
cancelled it.
It was cancelled because of the lockdown, which is good. Because they promised that they will give millikelvin sorry, uh, 13 or 14 Kelvin, 13 Tesla low temperature STM with a without with a cryo cooler. Like
Yeah.
you can go 10 Kelvin with a large magnetic field, but with a Raman in TIF Hyderabad.
Yeah, his
So
feedback is not good at all.
yeah, at all. I mean, so then I also know from Professor Hoffman, Jenny, when I was in Boston, he bought the exactly same thing. It does not work at all. You cannot
Yeah,
see
no,
anything.
so the problem is the spectroscopic resolution is very bad.
Yeah.
The imaging resolution is okay, but then to actually get it running in magnetic field, you have to do a lot of work. It is actually a system. It's a promising system, but it's a system under development.
Yeah, yeah.
So it's not really a tested system. So yesterday I had a meeting with Adam Collin.
Okay, I
So,
see.
but that cryogen-free system, I think maybe 5-6 years from now it will get standardized. But at the moment, it's very risky to buy
Yeah,
that.
right. I think a lot of other company also parallelly trying to build this kind of cryogenic STM. But later, then we finally actually order one millikelvin STM from basically Unisoku with the standard ESM 1300 like Gautam Da has.
Yeah.
But that is also central facility, running STM with a CRF facility,
Yes,
and they also sponsor in CRF camp in Sonipot campus, which is 1 hour from here, and you cannot come back from there in the afternoon to take a
no,
class.
the problem is, see, central facility is okay, but are they making you the in charge?
No.
Then
See,
you're sunk.
I made a PFC and NIQ, like all the specifications, but the buyer is a different person. So,
So this
and
is what, some mechanical engineering professor or something like that in only.
exactly.
So some guy who cannot identify a STM from a screwdriver.
It brings a polymer also to that USB STM. So then, this is
No,
how.
this is the problem. So STM is not a central facility. It cannot run as a central facility.
Yeah.
And millikelvin STM cannot run at all as a central facility. It's out of question. These people actually, they think that it is something like an electron microscope.
Yeah.
But this is
Plan.
very, very different.
Yeah, even what they plan. Even they run some MB system in a central facility. They hire some technician, and it's difficult to find a postdoc or technician with experience even to handle a pump or USB.
No,
So
no,
it's
forget it. That is, I will write off that investment straight away. If they don't make an expert the in charge, it's not going to work. But how is your feedback about Quasar?
So Quasar we have a two Quasar in our teaching lab. They bought it for a MTech student, and then I see that even in HOPG, it is very difficult to get atomic resolutions. You have to spend 2-3 days to get a decent atomic resolution.
So it's not stable, or is
with
it?
a scan with the scanner is not very stable.
No, no, no. Forget the scanner. I am talking of the electronics. How is their electronics?
So electronics is basically you cannot compare with even RHK S9 or anything. You cannot compare. It's very low.
That I can understand. Yeah, but
for a teaching purpose or room temperature things, you can work with it. But since it is written in Python, so we have modified a lot. But we had to dig down a lot of things, ask them to give this access and so on. So we modified completely a lot of, because for example, we cannot read what is the tunneling current as a function of time when we don't just approach the tip. I want to see the stability. Like I don't scan at all. That is a distance. I want to measure that as a function of time. This kind of function was not there. So we even to measure the noise level and so on. But now looks like going direction because it is a cheap, so I could buy.
Yeah, cheap means how cheap?
If you can get with a 11 to 12 lakh whole things with a scanner head also. So in the you can buy only 7-8 lakhs on the controller.
Okay, but 7-8 lakhs is not that cheap.
Okay, sir, that's why because I have no money to buy RHK this S9 which is around
Yeah,
50, 40
that
lakh
is,
and
means if it
so,
was, let's say, 1 or 2 lakhs, I would have just bought one and tried. But 7-8 lakhs is still some money. But I guess now Vishal is possibly getting anxious.
yeah.
So I will possibly have to start.
Definitely
Sure.
not.
It was good to
Yes, sir,
connect.
good to see you. I will stay here to listen your talk. I actually heard about before about the Vortex Latin. Thank you. Good to see you. Take care.
Yeah, okay. Yeah, now this is a very simple talk, so you don't have to sit through the whole thing.
Yeah. Okay. Exactly. Thank you.
Vishal, I cannot hear you.
Can you hear me?
Oh, yeah, now I can.
Okay. So, yes, would Menon sir would like to talk something?
No. I think it was very nice talk. Okay, welcome, sir, Dr. Roy Chaudhary. Welcome, and then Dr. Vishal will introduce Dr. Roy Chaudhary. Okay, thank
Okay.
you. Yeah.
Should I share my screen first so that?
Let me give some introduction or.
Yeah, it is just to check. I am not a user of. Let me just check it once. I am not a
Yes, sir.
user of this.
Sure, sir.
Is
Sure.
it okay? Can you
Yeah.
see my screen?
Yes, sir. Yes, I can.
Now, yes, now we can.
Okay,
Yes,
is it?
you can. You are shifting also properly.
The transition is all right. All right.
So working very well. Just you can, Professor. Actually, you can minimize small window on the right side. There is small window is coming. You can minimize that. This Microsoft Teams small window. That's why.
Oh, this window.
Yeah, you
Okay.
can minimize that. Just
Now I have to one thing before. How do I stop the sharing? This is.
you click on the same
Okay,
place.
stop
Share
sharing.
content.
All right. Okay, fine. I think it's all right.
So. So you're not audible. It seems I can't hear you over this thing. Yeah. Okay.
Yeah, Doctor. Our student Shruti Shetty would like to thank Dr. Sujit Manna. Shruti, please. Then we'll start. Shruti, just a second. Shruti, you are there? Shruti.
Shetty.
Yes, sir.
Yep.
Yes, sir. It'll be Mrudula first.
Okay. Yeah. Mudala, yes, please.
Mudala is there.
Hello everyone. Thank you so much Dr. Sujit Manna for your lecture on sensing and manipulation of individual atoms using STM. You beautifully explained the technique used in STM and STS, the working of STS, why we need to study materials in the atomic state, example of an electron confinement, spin polarized STM and probing towards Majorana edge mode in gold nanowire. This webinar has been very informative and will definitely help students gain interest in the field of research. I once again thank Dr. Sujit sir for this guidance. On behalf of Physics Department, I am thankful to everyone for the enthusiastic participation.
Thank you, Shruti.
Okay. The next to start now. Yeah, go ahead.
Yes. So we can.
Welcome.
So the next.
Dr. Chaudhary. Dr. Vishal will introduce him. Vishal, please.
So yes, Professor Pratibha Roy Chaudhary is a faculty at TIFR. He is a full professor. He has an illustrious career before him. I mean, he had the best experimental project in his BSc, MSc time itself. He did his MSc from IIT Kharagpur, then went on to do his PhD in TIFR, then did various postdoc work at TIFR as well as Liverhome University of Birmingham, and he has been awarded Shanti Swarup Bhatnagar Prize in Physical Science in 2014, and is an elected member of IUPAP, which is International Union of Pure and Applied Physics, in 2018. He has a citation of more than 4,300 and an H index of 335, which essentially measures the relevance of the work he has been doing in his research. So he'll be the topic that he'll be talking about will be investigating a vortex solid using STM. So he'll be talking about quantum current and in a type 2 superconductor. So over to you, Roy Chaudhary.
Okay, thank you, Vishal. So it's a pleasure to give this talk. What I would, so since I understand that there is a large fraction of undergraduate students in the audience, I will try to keep it as simple as I can. And in between, if you have any question, just interrupt me and ask your question. You don't have to wait till the end. So, am I clearly audible?
Yes, sir, you are audible.
Oh, good. Okay, so as Vishal has already told you, I will be telling you about, let's say, about the melting of a solid. So the overwhelming theme of what I will be telling you is how a solid melts. It's an age-old theme. So it's a it's something that you have all studied in school, but we will be looking at it in a very different kind of solid, which is called a vortex solid, and we will be seeing this melting, if you want, constituent by constituent. It's like seeing atom by atom how it is melting. All right, so it will get clear as I get along. So most of the work that I will be showing you was done in my group, and these are the students, postdocs who contributed to this work, and some bit of theory that we also need to analyze our data is done in collaboration with this group in University of Rome. With this, let me get started. So you know that a large variety of systems then at low enough a temperature, they go into a periodic structure. So of course, you all have studied in your solid state physics course about crystals. So if you take a collection of atoms and then you start from a high temperature, first it's a gas, then it cools into a liquid, and then this liquid, when it solidifies, most of the times it forms a crystal, which is a periodic array of atoms like this. Now, these things need not, this constituent of this solid, of this periodic structure, need not be atoms. You can take, for example, here this is spherical glass particles in water. So you have spherical glass particles, and you have put in a water solvent in between two glass plates. And even here you see that it looks like a polycrystalline solid. You have a hexagonal arrangement of these glass particles, and then you have domains which are sort of oriented in different direction with these domain boundaries. Similarly, if you take, let's say, magnetic particles, these are iron oxide nanocrystals. These, they interact here, now they interact magnetically with each other, and again you form this kind of a periodic solid. And when I am talking of solid in today's talk, I refer to this periodic structure that formed due to the interaction of the constituent elements. Now, in some cases, in fact, the solid that forms need not even be physical particles. For example, this is an alumina surface. So you take aluminium, you take a sheet of aluminium, polish it very well, and then you electrolytically oxidize the surface. So you form a thin layer of alumina on aluminium oxide. Now, due to some process that is not completely understood, this aluminium oxide does not form a continuous layer, but it forms this kind of a template where you have this aluminium oxide, and then in the middle of the aluminium oxide here this darker region are holes. And these holes, you can see during the formation of this, due to the interaction of how this aluminium gets oxidized, these holes get a periodic structure again which is hexagonal. So now you could ask, why do everything go periodic, or many things go periodic at low temperature? And this is an outstanding problem of physics. No one can give a real proof or even a good qualitative reason as to why the ground state of almost all assemblage of atoms are regular rather than irregular in nature. So this is from this book Concepts in Solids by P.W. Anderson, who is one of the most influential condensed matter physicists of the last century. Nevertheless, we know that solids exist, and if you take a crystalline solid and you heat it, then at some temperature it will melt. We study in school that this melting is a first order phase transition, and this first order phase transition, it involves a latent heat. So therefore, if you heat a solid at some point, you have a latent heat that comes out, and then you get a liquid. If you look at it more microscopically, then you have a solid here, a periodic solid. When you increase temperature, then each of these atoms, they start vibrating about their mean position, so that you form these atom waves. And when the amplitude of the vibration becomes larger than 10 to 15% of the lattice constant, then the solid is no longer stable and you go into a liquid. This criteria is called Lindemann criteria. Now, just as an aside, Lindemann was a very interesting person. Most of the people today have forgotten who Lindemann was, but there was this very nice article in Scientific American by Madhusri Mukherjee, which you should possibly read just for historical interest. So Lindemann was also known in history as Viscount Cherwell. He was one of the most powerful scientists ever, because he was Winston Churchill's personal technocrat, and he used to advise him on all kinds of things, including things outside science. And he was also responsible for the Bengal famine, which killed about 3 million people. Because his argument was that this is a country, India is a country which just reproduces too much, and therefore by natural selection some people have to die, otherwise there is no future. So anyway, you can read more about it on Lindemann from this. So this is a little bit of a demystification. Not every great scientist is a great person. All right, but this is the Lindemann route through which a solid melts. Is of course the most common route that we study. But on the other hand, there is, we could ask ourselves if there is any other route through which a solid melts. Now this other route, I'm sorry, this other route is through topological defects. And let me first explain what are topological defects. So suppose I have a telephone like this, and you have this nice spiraling wire which connects the handset to the receiver. This is how you buy it. But once you start using it for a few months, you see that this wire will form kinks. Just go and check any telephone. It will have these kinks. Now these kinks, you can look at it carefully. And you will see that these are non-trivial objects. Because on one side of the kink, the wire is wound in one sense. In the other side of the kink, it's wound in the opposite sense. So which means that though this kink is a very small local object here, you cannot get rid of this kink just by doing locally something here. You have to take the entire wire between these two kinks, unwind it, and then wind it in the correct sense, in the correct direction. So these kind of defects are called topological defects, and they are topologically protected, which means that it's very difficult to get rid of it by locally doing something at the defect site. These kind of defects happen all the time in nature. For example, if you take in your wash basin, if you fill the water and let the water go, you form a vortex in the wash basin. That's a topological defect. Then you can have topological defects in crystalline lattice, in magnetic systems, and so on. Now, when you increase temperature, you not only induce lattice waves, but you also form these topological defects. And you can ask yourself, these topological defects, can they also melt a solid? Now, this question was addressed long back by two people called, this question originally was addressed in its preliminary form by Landau-Lifshitz, and this is a problem that is there in Landau-Lifshitz's book. So let me try to explain this. So Landau-Lifshitz took a very simplified version of this problem. Instead of these telephone wires, now suppose instead of this spiraling wire, you have a collection of spins. These spins can be either up or down. Now, if two adjacent spins are parallel to each other, then the energy is lower. It is minus J. If two spins are anti-parallel to each other like this, then the energy is J. And then you sum over this energy over all spins. Now you can see that the lower energy state will be when all the spins are parallel, because the energy of adjacent parallel spin is minus J.
The audio has broken, sir.
Yes? Excuse me?
It's audible.
Sorry. Vishal's audio was
I
broken,
see.
but it's audible.
Was the voice broken?
No, it is
No,
audible.
it's audible now, sir.
Oh,
Audible.
okay. So now you can ask yourself, this kind of one-dimensional, let's say, chain of spin, this is actually a very famous model. This is called the Ising model. And you can ask yourself whether such a one-dimensional Ising model with this nearest neighbor interaction will show an ordering. So you know that for a nearest neighbor, the interaction energy is 2J if you make it antiparallel. So if you just consider the energy, you'd possibly conclude that if you are at low temperature, everything would become parallel because that's the lowest energy state. However, statistical mechanics tells you that there is also something called entropy. And therefore, what matters is not the internal energy alone, but what matters is the free energy. And this free energy is internal energy E minus temperature into entropy. Now you know that this entropy goes as log n. So if you have n, which is the total number of spins, then you create, let's say, this kind of a domain wall. So this kind of a domain wall will immediately increase the energy by 2J, because you are going from a configuration here where the local energy was minus J and you are pushing it to plus J. So therefore you have a energy increase of 2J. But this domain wall here, you can put it anywhere. You have a choice of putting it anywhere on the n sides. It could be here, or you could put this anti-parallel configuration here or here, and therefore the entropy will be Boltzmann constant into log of n. N is the total number of spins. So therefore the free energy will be E minus Ts, which is 2J from here minus temperature into Kb into log n. Now you see that this free energy is less than 0, which means that when you create a domain wall, you decrease the free energy. And since if you go in the thermodynamic limit where you have very, very large number of spins, say ideally infinite number of spin, the entropy will always win. And therefore, when you create a domain wall, you have a very large decrease in the free energy. And if you can create one domain wall, you can create two domain wall and decrease the free energy further, and three domain wall even more. So you will proliferate with enormous number of domain walls. And since you will have domain walls everywhere, you will have no order. So there is no order state at any finite temperature. No matter how small T is, if you are in the thermodynamic limit of very large number of spin, this n will always win. So log n will always be very large, and this 2J, since it's a constant, you can go to large enough a system where the free energy will dominate. So at finite temperature, this has no long range order, and this problem is done in Landau-Lifshitz book, and you can go and read it in more detail. There are many other funny things here. Now this is what you have, this is what you have when you have nearest neighbor interaction. What happens if suppose the interaction between the spins was not nearest neighbor, but it extended larger distances? So what was shown later on by other people, that if this interaction is long range, so if it falls off slower than 1 by r square, then you can have ordering. If you falls off faster than 1 by r square, so if this exponent is 2 or larger than 2, so sorry, if it is larger than 2, you will not have this ordering, and this argument will hold. So now you could ask yourself, what would happen when this exponent is exactly 2? So this was addressed by David Thouless in the late 60s, and this is again a problem that you can very easily solve. Now the energy increase when you create a domain wall will not be given by just twice of J like before, but now you have to do an integration because the interaction is long range. But it goes as 1 by r square, and if you do this integration, what you will get is 2J into log n by 4. Now log n by 4 is actually log n minus log 4, and you can neglect the log 4 part. Entropy, of course, will remain the same. It is Kb log n. So now the free energy will be like this, 2J minus Kt log n. This is more interesting. If you go to low temperature, this prefactor is positive. So that means creating a domain wall increases the free energy, and that is not energetically favorable. So you will not create any domain wall at low energy, And if all these spins had a magnetic moment, you will have a completely saturated magnetization. But when you reach this temperature, J by twice Kb, then this will become negative, and now creating a domain wall will actually decrease the free energy. So it is preferable to create a domain wall. Then above this temperature, your magnetization will suddenly crash to zero, because now you will have huge number of domain walls proliferating like before. This is all fine. So this essentially, this kind of change tells you have a phase transition. And those who have studied phase transition would immediately tell me that this is a first order phase transition because there is an abrupt jump. But remember, first order phase transition is not just an abrupt jump. First order phase transition has other things. It should have a latent heat. So therefore, there should be a discontinuous jump in the free energy. This is where this result actually startled even David Thouless when he derived it, because if you look at this free energy here as a function of temperature, there is no discontinuity anywhere. It just smoothly goes from positive to negative through zero. So there is no jump in the free energy, there is no jump in the derivative of the free energy, and therefore this cannot be a phase transition. This cannot be a first order phase transition, this cannot even be a second order phase transition. That is when Thouless realized that he has actually found out a new kind of phase transition. This is a phase transition mediated by this topological defect. And today this is known as the Kosterlitz-Thouless transition. After Thouless, who discovered it from the one-dimensional system, and Kosterlitz and Thouless together extended this for two-dimensional systems. So one-dimensional chains are not very common in real life, but two-dimensional systems are plenty. So you don't need to have necessarily a one-dimensional chain of spin. You can take an array of spin like this on a plane with the only constraint that the spin has no component out of plane. And again here you will have the same kind of topological defect driven phase transition. Only thing here, the topological defect is slightly different. Instead of being the domain wall boundary that I showed you before, here these are points where you have the spins that spiral around. These are called vortices. All right. Now, this was quite a remarkable discovery, and this is what got a Nobel Prize for Kosterlitz and Thouless few years back. Berezinski was a Russian physicist who predicted the same thing 1 year before Kosterlitz and Thouless. However, he published his paper in Russian, so it was not very well known till Kosterlitz and Thouless did their work. And unfortunately, Berezinski also died early, so he didn't get the Nobel Prize because when it was given, he was already dead. All right, but this phase transition, we call it Berezinski-Kosterlitz-Thouless phase transition. Now, these are mathematical models, but as it so happens, this Kosterlitz-Thouless, you can actually map it on a real two-dimensional crystal. So suppose you have a two-dimensional hexagonal crystal like this, then the equivalent of the domain wall or the vortices here is what is called dislocation. Dislocation is this. You see here every point has 6 nearest neighbor. Here this red point has 5 nearest neighbor and the green point has 7 nearest neighbor. Together, when this red or green are next to each other, this is called a dislocation. So just like at a certain temperature, you have domain walls or vortices which proliferated in the mathematical model. In this kind of two-dimensional solid, what you expect is that at some temperature, you will suddenly get huge number of dislocations. And initially, BKT thought that this kind of dislocation will drive the solid into a liquid. But they were only partially correct. And that is because what was realized very soon, if you take this kind of solid and you do, let's say, a diffraction experiment, you will get 6 black spots as you expect. When you have lots of dislocations here, after the transition, you don't have 6 black spots anymore. Now they have gotten very strongly smeared, but you still have a 6-fold symmetry in your diffraction pattern, which means that the orientational order is not completely destroyed. So this was a puzzle for quite some time, till 3 other gentlemen, Halperin, Nelson and Young, they showed that actually to completely go into a liquid-like state, you need a second phase transition where another kind of topological defects come in, and these are called disclination. Disclination is isolated points which have 5-fold or 7-fold or 4-fold and 8-fold coordination, but they don't have any adjacent ones. So if you have, let's say, 7 and 5 next to each other, that's a dislocation. But when these two defects next to each other, they separate out in space, you end up with 2 disclinations. And when you have disclination, here for example, you can see the disclinations by these red and white points. They don't have, this red have 5-fold coordination, this white have 7-fold coordination, but they don't have any adjacent nearest neighbor of the opposite kind. And when you have these disclinations that proliferate in the system, your orientational order is also lost, so you have a liquid. So this brings to the question, what is this thing then in between? After the first BKT transition, if I don't have a liquid, what do I have? So it was soon realized that you have a new state of matter which is present only in 2 dimensions, and this is called a hexatic fluid. Now this hexatic fluid is a very strange object because it has orientational order, it has specific orientation of the atoms, but it does not have positional order, and more importantly, it has very interesting flow properties. So you know that liquid can flow. Here also a hexatic fluid can flow, but it cannot flow equally along all directions. Hexatic fluid flows preferentially along the direction of the principal lattice vectors. Okay, so this was a very important discovery, and there was frantic search by experimentalists to see whether in real systems you actually get hexatic fluid. So the obvious thing to look for actually would be a 2D solid, like let's say 1 sheet of graphite, which is called graphene. However, these cannot be used for an obvious reason. The reason is that here there is nothing to constrain the atoms in the 2-dimensional plane. So by the time you heat it and it melts, it has already formed wrinkles, wrapped up, or it has formed a blob. So then the melting will be just the regular Lindemann melting, which is the first order melting. So 2D solid was not an option to look for this. So people started looking at other things. As I told you, here a solid means a periodic array of entities which have become periodic through their mutual interaction. So one of them is, for example, the Wigner solid. Wigner solid is on the surface of liquid helium. You can have these electrons, and these electrons then, because of their Coulomb interaction, arrange themselves into a hexagonal solid. People also tried gas molecules adsorbed on the surface of graphite. However, all these atoms essentially did not provide any conclusive evidence of a hexatic fluid. So each of them had one problem or the other. The problem here, I told you, here for example, when you try to heat and get into a hexatic fluid, these electrons actually form bubbles and dissolve in the liquid helium. so they don't remain on the surface. Here the problem was that this is not really a two-dimensional system. You have these gas molecules absorbed on graphite, but you have the underlying graphite which is holding this gas molecule. So therefore, together with graphite, it becomes a three-dimensional system. It's not a two-dimensional system. So far, the only system in which one has seen some conclusive evidence is this magnetic colloidal crystal. This is like those iron nanoparticle that I showed you, which through magnetic interaction forms a solid. However, we wanted to look at a very different kind of a solid, which is the vortex lattice in a superconductor. So let me explain to you what that is. So for the completeness, let me first tell you what are superconductors. So you know about metals, semiconductor and insulators. That is what the kind of system that we normally encounter in everyday world at room temperature. However, a certain class of metals, if you cool them to very low temperature, then at some temperature they lose their electrical resistance. So here the electrical resistance becomes zero. And when I mean zero, this is not very low. This is exactly identically zero. So you start having a system which has zero resistance. And of course, this is remarkable because if you had, for example, such a system at room temperature, our energy problem would be solved. You could have energy transportation without any loss at all. Unfortunately, that is still not realized in a usable form. But nevertheless, there are numerous now materials which are superconducting. The first one was discovered in mercury by Kamerlingh-Onnes in 1911, and over the years hundreds of superconductors have been discovered. These superconductors have also another property that they expel magnetic field. So if you put a superconductor on the top of a magnet, then the superconductor will float above the magnet. So this is what I have illustrated here, and this is actually the basis of maglev trains. Many of you might have heard of maglev trains, which float over the track instead of rolling over the track. Now there are two kinds of superconductors. One of the superconductors are called type 1 superconductors, and these are mostly the elements, lead, tin, indium and so on. And they are perfect diamagnet, so which means that they expel magnetic field. And above a certain magnetic field, of course, superconductivity is destroyed. And for type 1 superconductor, that magnetic field is quite low. It is of the order of 1 kilo. On the other hand, what we will be concerned today, for obvious reasons, the reason will become obvious in a moment, are type 2 superconductors, which is almost all superconducting compounds. And in type 2 superconductor, the superconductor is a perfect diamagnet up to some field Hc1, and above Hc1, the magnetic field can enter inside the superconductor, but in a very special way. So it enters in the form of a flux tube, which I will explain to you in a moment. Here, the superconductor becomes a mixture of normal and superconducting region. That is what is called a mixed state. And at a much higher field, the superconductivity is destroyed at a field which we call Hc2. And this can be very, very high. It can be thousands of kilohertz. Okay. Now, why are we today, when we are dealing with solids, concerned about type 2 superconductors? We are concerned about type 2 superconductors because, as I told you, above this lower critical field Hc1, you have magnetic field that can penetrate inside a superconductor. But it does not penetrate uniformly. It penetrates in the form of these flux tubes. So you have these bundles of flux that enters in the superconductor, and each each of these flux bundle, which we call the vortex, that carries one flux quantum. And this is a universal constant h by 2e, where h is the Planck's constant, e is the electron charge. Now, if you look carefully from the top, this is, let's say, a side view. I have applied the magnetic field in this direction. If I was looking from the top, what you would see is that where the magnetic field has entered, you have created a normal metal region. This is what is called the core of the superconductor. And around this core, there is this circulating current. And this circulating current is the reason why we call it a vortex, because this circulating current has a vortex structure. Okay, now this is like having, you can now immediately imagine, this is like having a collection of bar magnets with the same polarity. So these bar magnets will repel each other. These bar magnets will repel each other, and under their mutual repulsion, actually, these flux tubes or vortices, they arrange themselves into a hexagonal structure. This is called Abrikosov vortex lattice. So it is this periodic solid, not made now of atoms, not even made by physical particles, but made of flux bundles, which we call vortices, that we will now investigate to study the order-disorder transition and the Kosterlitz-Thouless transition that I have just explained to you about. The question is, how do I image? How have I taken this photograph? Okay, so I don't need to explain the STM anymore. Sujit has done a great job of giving you an exposition to this technique. You have a tip and you move the tip over the surface. You measure either the tunneling current or you keep the tunneling current constant, and with a feedback you take the tip up or down and record how much you have to take it up or down. And with this you can get this kind of atomic resolution images. This is the image that you have on an IBM diselenide single crystal. These are the selenium atoms. Okay, but today we don't want to image atoms, we want to image vortices. So I take a superconductor like this and I apply a magnetic field larger than the lower critical field so that I have vortices. How do I image these vortices? I take this STM tip here. Now, if I take the STM, let's say, these dark points are where I have the vortices. If I take, let's say, in between two vortices at point A, then I am tunneling from a normal metal. So this tip is the normal metal tip. I am tunneling from a normal metal to a superconductor. But if I go at point C, which is in the core of the vortex, now I have told you the core of the vortex is like a normal metal. So now I am tunneling from a normal metal to a normal metal. And then of course if I do B, then it is similar to A. So now there is a difference in the tunneling conductance when I am tunneling from a superconductor source to a superconductor, and when I am tunneling from a normal metal to a superconductor, and when I am tunneling from a normal metal to a normal metal. This contrast I can record while I am moving the tip on the surface, and whenever I see these regions of low conductance, these local minima, they correspond to the position of the vortices. So this is how I can, this is a zoomed image, this is how I can do over large area and get these beautiful images of the vortex lattice. So this allows me now, if I change temperature or magnetic field, I can track how this vortex lattice happens at the scale of arrangement of vortices. So our scanning tunneling microscope is a home-built scanning tunneling microscope. This is built by our hard-working students, and this is something therefore we are very proud of. If you want to know how a scanning tunneling microscope is built, You can refer to this paper, or you can ask me or whatever. Okay, I will not go into this detail, but now let me go straight into the system that we are studying. I will take a superconductor, niobium diselenite, and we go to very low temperature, 350 millikelvin. This is 0.35 Kelvin above absolute zero. And now if I measure, let's say, SI susceptibility, then it has this very interesting non-monotonic feature. And actually, around 16 kilooersted, the Vortex solid, from this bulk measurement, we know that at 16 kilooersted, the Vortex solid starts disordering, and this disordering gets complete around 25 kilooersted here. So this non-monotonic variation of the SI susceptibility is a signature of the melting of the vortex lattice. Okay, however, what we want to see is, with this microscope, we want to see how the vortex configuration evolves. So we start. We start here at this field, which is before the order-disorder transition starts. So here at 15 kilooersted, I have a perfectly good vortex solid. And here what I am showing you is what I had earlier explained to you as the diffraction pattern. We don't really do a diffraction. We take this image and we do a two-dimensional Fourier transform. That is equivalent to doing a diffraction. So you can see 6 black spots. When I increase magnetic field here, this is equivalent to increasing pressure. So for example, if you take ice, you know that if you increase pressure, ice melts into a liquid. So here, if I increase magnetic field, it will gradually melt, and let us see how it melts. I increase to 20 kilooersted, and I start forming dislocations. So when I form dislocations, I know that these black spots start getting broader. However, here I have just one dislocation. But as I increase a little more, 24 kilooersted, I start having many dislocations. Black spots are even broader. At 25 kilooersted, I have lots of dislocations. And now black spots are very broad. But still I maintain the orientational order, because you can see 6 black spots. So there are specific orientations. I go to 26 kilooersted, and that is where I have disclination. And as soon as I have disclination, my entire orientational order is completely lost. Now, at 30 kilooersted, it's even more diffuse. Now, however, why didn't I get a liquid state? So what I am getting, this is, you know, that liquid is not just a state where I have a lot of disorder, but liquid is also a state where the atoms are moving. So here the vortices, why are they not moving? So the reason why they are not moving is because here in a superconductor there is an additional ingredient which is called random pinning. The random pinning, what it means is these are crystallographic defects. So here the image that I am showing you is the crystal lattice. These are selenium atoms. But these dark spots here is where we have some impurities. Most likely cobalt impurities. We don't really know what these impurities are, but they are most likely cobalt. And these impurities, actually, they tend to act as potential minima for the vortices, and they lock their position. So the system is melting, but even after melting, the vortices are not able to move around because of these crystallographic defects. This is which provide a random pinning. So they pin the individual vortices. This is what is called a glass. It is just like the window glass that you have on your window. That is exactly the analog of this, where you have the atoms which have no periodic orientation. They are like no periodic arrangement. They are like a liquid, but they are frozen in time. Now, in this case, of course, you can go to even higher field and you get a tiny window where you see a liquid phase, but that window is extremely tiny. You can also, however, okay, so now you can see here that we got something which looks like a hexatic, but this is not what Berezinski, Kosterlitz and Thouless predicted. This is not a hexatic fluid, it is a hexatic glass. Here there is no motion. The hexatic has very interesting flow properties, the real hexatic fluid, and this one has no flow properties. You can also find out that this is not actually an intrinsic effect, it's actually an effect that is driven by the amount of defect that you have. So for that we did on 3 different samples which have different levels of purity. In the phase diagram, in the magnetic field temperature phase diagram, or in these measurements which is at a given temperature, if you look at how big the hexatic fluid phase is, this red region, you see that for a very disordered crystal which has a lot of defect, you have a large hexatic region, but as you increase the purity of the crystal, this hexatic region shrinks, and presumably you cannot go to completely clean, that is only hypothetical, but presumably for a completely clean crystal, these two will just merge into one first order phase transition as you expect in a Lindemann scenario. So that means that we are doing something wrong and we have to look at a different system. Now, the reason why we did not see a hexatic here was, one of the thing is because we have a lot of defects, and second thing is that we were using very thick crystals, because of which this was not a real two-dimensional solid. So the vortex here was like a tube, but this tube is not entirely straight, and this tube can also meander. So it's more like a collection of loose hanging spaghetti, and therefore this has degree of freedom in both x, y and z. It's not a real two-dimensional system which Berezinski, Kosterlitz and Thouless predicted their theory for. So we tried to look for a good system to find the hexatic fluid. And we ended up, after a lot of investigation, with this superconductor, which is, I'm sorry, there is something that came at the top. Okay, can you see clear? Can you see properly my slide?
Yes. Yes.
Okay, then I won't bother. Okay, so we started looking at this. We chose this superconductor, which is molybdenum germanium. Now, molybdenum germanium is an amorphous superconductor. So this superconductor, it's like your window glass. It does not have, the molybdenum and germanium in this material have no crystalline order. And what we realized here, because it's an amorphous system, it is homogeneous, and the pinning strength, the pinning that was preventing the hexatic fluid from flowing in niobium diselenide, here is very weak. Yes.
So the title of this slide is not visible here.
Exactly. That is what I am not on. Yeah. Okay.
Yeah.
Then,
no, it's
all right. Good. Yeah. That is something came at the top. I don't know why. All right. So here the pinning is very weak. Actually, the pinning strength that we can quantify from various measurements is 5 orders of magnitude weaker than usual superconductors like niobium diselenide that I showed you before. Other than that, of course, there is also another reason for choosing a amorphous system, and that is because, for example, if you have a crystalline system, this crystalline, the underlying atomic crystal has a symmetry, and this symmetry starts influencing the orientation of your vortex lattice. So the crystal lattice and the vortex lattice have a orientational coupling. That is what we had seen before in niobium diselenide, and we did not want that. We wanted the underlying crystal to be completely featureless, and that is achieved for an amorphous system. Okay, so otherwise this molybdenum germanium is just a conventional superconductor. It's unremarkable. So we took a thin film because, as I told you earlier, the second problem other than pinning in niobium diselenide was that it was too thick, and because it was thick, it was not really a two-dimensional system. So here we took a thin film, and this thin film had a thickness of 20 nanometer. There is, however, a problem of working with molybdenum germanium. And the problem is that molybdenum germanium gets oxidized very fast. So we have a technique called pulse laser deposition, with which we grow the thin film. And after you grow this thin film, if you take it out in air, immediately you have an oxide layer on the surface, and after that you cannot do scanning tunneling microscopy anymore. So what we had to do is to use this toy, which is a vacuum suitcase. So you make the film and then you immediately transfer in this vacuum suitcase and you close this gate valve. So your sample, your thin film is in this suitcase. It doesn't look like a suitcase, but it has the same purpose as a suitcase, except that it keeps your sample under extremely high vacuum, under ultra high vacuum. Then you disengage it from here, take it to your scanning tunneling microscope, engage it again. The scanning tunneling microscope is always under very high vacuum. You push your sample in without ever exposing to air. So this was an extremely challenging job experimentally, and this required us to develop many interesting techniques in terms of sample transfer, sample holder, and so on. And this is what allowed us to do this experiment, which no one actually could do before. So with this, we start the imaging again. So at 1 kilohertz state, I have a vortex solid. At 3 kilohertz state, I start forming dislocations. And then I have dislocations all the way up to 70 kilohertz state, and above 70 kilohertz state, I have disclinations. The question is this again a hexatic glass, or have I really got a hexatic fluid? So for that, I will be showing you some movies. So here what I am doing is I am imaging the vortex lattice over a small area, and then I am taking this image at every 10 minutes interval and connecting this position of the vortex by arrows. So I am tracking how each vortex is moving. So you can see that when I am in a vortex solid, the vortices hardly move. They just move a little bit around their mean position, and that is exactly what you expect for the case of a solid. When you go to a hexatic fluid, let's say 3 kilohertz state, I am already in a hexatic fluid. Here the vortices are actually moving. But look carefully. So in this panel, I am just zooming this box here. Your vortices preferentially move along this direction or this direction. They could in principle also move along this direction, but that I don't have that in this panel. And this preferential direction of motion are actually the principal direction of the vortex lattice. This is exactly how a hexatic fluid should be. Now remember, this motion that I am showing you here, these are spontaneous thermal motion, like Brownian motion. These are, I am not applying a current or a drive to move it. This directional motion is even more prominent at 55 kilohertz state. Here, for example, you see that individual trajectory is somewhat jagged, but overall they are moving along a crystal direction. But now if you go to 70 kilohertz where actually I have lost all orientational order, here the motion is exactly what you expect for a Brownian motion in a liquid. The motion actually is completely random. It has no directionality. So this was a very strong proof that in these intermediate fields at 2 Kelvin, we are realizing between, let's say, 2 kilohertz state and 70 kilohertz state, we are realizing a hexatic fluid. Okay, these are quantification which I will skip. Now, I would like to know how much time do I have? Excuse me, how much time do I have? Am I audible?
Yes, sir. Yes, sir. Yeah. The session is up to 12:45, sir. Another 40 minutes.
Oh, 12:45, but 12:45 is including discussion.
Including discussion, sir. Yes.
Okay, fine. So I will just speak for another
half
10
an hour
minutes.
would do.
Yes.
All right.
Okay.
Okay, good. So, okay. Now, this, what I have shown you here is, of course, from these images, you have a very strong indication that you have a hexatic fluid. But then the real question is, how does the hexatic fluid affect the transport properties of a superconductor? How the resistive properties changes? After all, superconductor is interesting because it has very unique resistive property. It has zero resistance. What happens when you have a hexatic fluid? So for that, we started seeing what are the signature of this melting of the vortex lattice in electrical transport. Now, to explain this, I have to explain you a little bit about electrical transport in the presence of vortices. So when you have vortices, as I told you, these vortices are flux tubes. They form, suppose, a vortex solid like this, and I pass a current. Now, if I pass a current, what will happen? I will have a Lorentz force on the vortices. And this Lorentz force will be perpendicular to the magnetic field and the current, as you all know. And because of which these vortices will start moving along this direction. Now, if the vortices start moving along this direction, then I have a rate of change of flux. And a rate of change of flux means that it is associated with the electric field and a voltage. So now I will have a voltage drop across the superconductor, which means that the larger I apply this current, the more the force will be on the vortices, the faster it will move, the larger will be this voltage. And actually, if you do the mathematics, you can show that the current versus voltage will be linear. Sorry. So therefore, now I have a problem. Is it a superconductor or is it not a superconductor? If I have a linear voltage that is appearing with current, that means I have a finite resistance. And if I have a finite resistance, then it's no longer a superconductor. Well, what saves the day normally is that I never have a crystal lattice that has zero impurity. It always has defects, and this defect, as I told you, act as pinning centers. So when I have, let's say, few pinning centers, that I am in a relatively clean limit. Now these few pinning centers, these are not pinning all the vortices individually. But you know very well that if I have a solid, I don't need to hold all the atoms in a solid for the solid to become immobile. If I have to fix this, let's say, on a wall, I'll just take two nails, I'll put one nail at one point, another nail at another point, and this will be fixed. So the property of the solid is that with few pinning, I can pin the entire solid. So if I have these few pins, which I show as these red dots here, that will pin this entire vortex lattice. So now when I increase current, there will be no voltage appearing because these vortices will not move. So there will, of course, there will always be a critical current, and this critical current is when I am applying so much force on the vortices that they will tear apart from the pins and start moving. So when they tear apart from the pins and start moving, then again I will have a voltage that will appear, and the slope of this current voltage curve will be roughly same as if it was free. So this is, but till I reach this current, I have a zero resistance state. Now this is how the day is saved for the superconductor. But what would happen if I don't have a vortex solid, but I have a vortex liquid? Now in a vortex fluid, so whether that fluid is hexatic or a regular liquid does not matter. If I have a vortex fluid, then you know that I cannot pin a fluid by using 4 nails. So then this becomes like putting some obstructions in a river, in the flow of a river. Those obstructions will hinder the flow of the river but will not stop the flow of the river. So therefore now in a vortex liquid, pinning is no longer effective in stopping the flow entirely. So in a vortex fluid, what will happen is I will have a finite slope in the IV characteristic, but the slope will be much less, which means that the resistance will be small because I have still these pins which are hindering the flow. So the velocity, the vortices will not be able to pick up that much velocity. Of course, above the critical current, it will not matter whether I have these pins or I don't have these pins because it's enough to just tear these pins off, and therefore above the critical current all these curves will have roughly the same slope. What this tells me is that if I have to distinguish a vortex solid from a vortex fluid, then I have to do measurements at very, very low currents. And that is, and I have to measure the current versus voltage, and I have to distinguish between this red curve and this orange curve. Precisely what we attempt to do here. So these are the current versus voltage characteristics that we take at 2 Kelvin for at various magnetic fields. So these are magnetic fields up to, let's say, 3.1 kilohertz. This region here is where, so I have my critical current roughly here, and therefore this region here is irrelevant. I don't care about this region here. What I care is about this very low current region here, and that is where I have to zoom and see what's happening. So look at this scale. I want you to pay attention at the scale here. This is 4 milliamps. And now I'll be zooming this and showing you what happens from 0 to 100 microamp. Okay. So this is 0.1 milliamp. When you zoom in this low current region, what you observe is that up to 1.9 kilohertz, you essentially have no resistance that appears. So you have your voltage is 0 within error bars. And above 1.9 kilohertz, you start having a finite positive slope telling you that resistance has appeared. So this is where the solid is melting. If I plot now from the resistance, from the slope of these curves, I can plot the resistance. And if I plot the resistance, then I will see that up to 1.9 kilohertz, my resistance is 0. After that, the resistance is appearing. Now, these are spectacularly precise measurements. For example, if I go in the normal state, the resistivity of the sample is 1.2 micrometer meter. And here what I am measuring, this resistance, this scale is about 1/10 of a nanometer. So It's about 10,000 times smaller than the normal state resistance of the material. But nevertheless, if you do this precise measurement, you see that this is the field where you go from a solid to a hexatic fluid. Now you could also ask, what this is where I have the transition from a solid to hexatic fluid. So this is the first transition. What about the second transition, where the hexatic fluid will go into an isotropic liquid? For that you continue this measurement. So in the hexatic fluid, your resistance roughly saturates, and then when you reach the isotropic fluid, again your resistance starts increasing rapidly again. Why? Because in the hexatic fluid, your vortices could flow, but it could flow only in preferential direction, so the mobility was not very high. But now in the isotropic fluid, this constraint is removed. They can flow in any direction, and therefore the mobility suddenly increases rapidly. I would like you to note that this scale of resistance is log scale. It's a logarithmic scale. So from here, from the bottom to the top, I actually change by about 5 orders of magnitude, more than 5 orders of magnitude. Alright, if I plotted you this in a linear scale, then you would just see this drop and rest would all appear to be 0. Okay, so now we can do this measurement at many temperatures. This is measurement of resistance as a function of magnetic field, and we can construct a phase diagram. So if you construct a phase diagram, you see that you have a vortex solid here that goes into a hexatic fluid at higher temperature or higher magnetic field, and then at high magnetic field you have this vortex liquid. This is the regular liquid state, and then even above that, if you apply a field larger than the upper critical field, you go into the normal state. So this was a neat demonstration of yet another system that shows a hexatic fluid. Now I will stop here for the interest of time, but this hexatic fluid has many other interesting properties, and if there are questions during the question answer session, I will refer to some of them. Thank you. So I am now available for questions.
So the session is open for questions.
Okay, I have to see the face of people to answer questions. Just give me 1 minute. I am not very familiar with this, with the teams. All right, good. Okay, anyone who has a question, feel free to unmute yourself and ask. I would prefer if you ask the question yourself rather than someone reading out the question to me. And preferably, I would also very much appreciate if I could see your face when you are asking the question.
Unmute, no?
So we will have to
Unmute them, sir.
give them the right.
Unmute करो.
Unmute किया है.
क्या है?
किया है.
Unmute. Huh?
Video also.
I know.
Video also needs to be turned on.
May I ask a question? Vishal sir, may I ask a question?
Yes.
Yes, go ahead.
Okay, let me just turn on my camera. Sir, as you said that there are interesting properties of these hexatic fluids. So, are we seeing any practical applications currently available in the market of these hexatic fluids?
Currently available in the market, no, because the hexatic fluid is a state. The hexatic vortex fluid is a state that we discovered 2 years back. So I don't think we will see anything in the market so as yet. But the question is very interesting. The question is whether hexatic fluid has any useful property. Yes, it has. So let me see if I can quickly open something where I can show you. Just give me a minute.
Yes, sir.
Okay, while this opens, let me all right, yes. Okay, so the hexatic fluid indeed has one very interesting property, and that interesting property happens to be its extreme sensitivity to electromagnetic radiation. So one of the application of superconductors. So superconductors have few wide, so more popular application and some very niche technical application. So for example, this magnetic resonance imaging, MRI magnets, all have superconductors. That's the heart of a MRI machine, which you have at every hospital. So this is, for example, one of the very widespread use of a superconductor. Now, in contrast, one niche use of the superconductor is in terms of sensors. So you can use superconductors to have extremely sensitive sensors of electromagnetic radiation. Where are they used? These sensors are mostly used in astronomy, in millimeter wave to terahertz astronomy. So millimeter wave is a very important region, wavelength range in astronomy because of the cosmic microwave backgrounds and various other sources. However, it's an extremely difficult range to experimentally access. Superconductors are extremely good as to make sensors in this range, and the reason for that is that the superconducting energy gap is exactly, the energy scale is exactly equivalent to the photon energy in this range. It's in the milli-electron volt, and the photon energy here is also in the milli-electron volt. In contrast, for example, semiconductors, which are very good for visible, ultraviolet, infrared, are not good in this range because the gap is really far too high to have any sensitivity. However, to use a superconductor for detector, one of the conditions is that the superconductor has to be extremely sensitive. So the moment a photon falls, there should be a large change, for example, in the resistance or the kinetic inductance or any of its measurable properties. For that, you need what is called superconductors that are on the verge of an instability. And this hexatic state is precisely that. So one of the things that we discovered after our initial discovery of the hexatic state is that the hexatic state is tremendously sensitive to electromagnetic radiation. How? Pay attention now to this slide that I am showing you. So you have here, this is my superconductor, and I am doing a resistance measurement. I am passing a current through this extremum contact and measuring the voltage through this, across this inner contact. Now, if I directly connect wires, let's say, then these wires, of course, will catch all electromagnetic radiation. Electromagnetic radiation comes from cell phone, they come from radio station, from television transmission. All these things have electromagnetic radiation, and all this electromagnetic radiation go and fall on my sample. So normally you never directly connect wires, but you put filters. These RC filters, they block your electromagnetic radiation. And typically, if you see most systems, these RC filters that are used have a cutoff of about 1 megahertz or so. So sometimes half a megahertz, but that's a typical cutoff, because if you take any of the devices like your cell phone or wireless mouse or whatever, these are things that operate at much higher frequency, often at gigahertz frequency nowadays. But in this case, we were very, very startled that when we did the measurement without any filter, of course, this without any filter, by which I mean that we have a filter which is about 1 megahertz, that is always there by default. We have this large resistance that appears. So this is at a low temperature of 300 millikelvin, and you have this I am measuring as a function of magnetic field, and this is the hexatic state. This is the Vortex solid. Then you have gone into a hexatic state, and you have this large resistance. We put a filter first of this one is with a filter of 10 megahertz. We reduce it to 7.8 megahertz. It decreases a little bit, fine. We decrease it to 1 megahertz. It decreases further. But interestingly, even when we have a filter of, let's say, 710 kilohertz, we still have a little bit of resistance appearing here, and this resistance completely goes away at a frequency of 340 kilohertz. Now we were extremely puzzled as to what happens, because what is a device that can produce electromagnetic radiation at 340 kilohertz? We don't know of any such device. You can go to Google and you can check all the devices that you have. For example, this fan remote or your AC remote. All of them, they will work at much, much higher frequency. Then we realized that Bombay has still a medium wave radio station. And this radio station, it transmits signal at 500 kilohertz. Now with FM, medium wave radio stations are almost out of the picture, but Bombay still has one, and that one is has a frequency of 500 megahertz. That is 500 kilohertz, and that is why when we put a filter of 340 kilohertz, we eliminate that and we don't get any resistance. But then we did a controlled experiment. In the controlled experiment, we first put a filter of 340 kilohertz. So we eliminate all external source of radiation. And then by hand, we start putting a small AC frequency, which is to simulate external AC noise. And what we observed is this, that this, what I am plotting here, for example, is the resistance that appears as a function of frequency of this external noise that I am putting in. And above, what you see, above 10 kilohertz, below 10 kilohertz, there is no response, the resistance is 0. Above 10 kilohertz, I have suddenly a large increase in the resistance. So this is remarkable, and here remember the excitation, the AC noise that I am putting in is tiny. It is much, much smaller than my DC measurement current. So now to answer your question, is there a usefulness of these? Yes, the usefulness is to make sensors. One can make extremely sensitive and precise sensor out of these materials if you push them in the hexatic state. And this is something that we are doing some pilot experiments now, which is on trying to realize practical sensors out of it. So the problem with practical sensor is that you cannot really make a practical sensor by putting it in a superconducting magnet and applying magnetic field. That would just make it too expensive to operate. So we are trying to have permanent strong neodymium iron magnets that can produce enough field that the superconductor will be pushed in the hexatic state. We will glue the superconductor on this magnet. We are gluing the superconductor on this magnet so that we don't have to bother about magnetic field after that. Then it becomes a black box which will have a very strong sensitivity to external electromagnetic radiation. So this is the potential application of this material.
So one discovery has given rise to multiple possibilities in future, in a way.
Yeah, of course. Every discovery in basic science gives rise to multiple possibilities, and this is one such possibility that we have envisaged. There may be other possibilities that we have not thought of.
Yes, sir. Thank you, sir.
Anyone else? So if someone has any connection problem, then and has written in the chat box, I will of course definitely take that.
No, I was on mute. Okay.
Yeah.
One question. Yeah. One question one I asked is, can you make a solid into a liquid by stretching it?
I could not hear you. Can you be closer to the mic?
Okay. Yes. Can you make a solid a liquid by stretching it?
No, normally not. Normally not. Why? So you cannot drive a solid, you cannot drive a phase transition by applying a static deformation. So just by stretching the material, it will shear off, but it will not undergo a phase transition. However, there is something else which is a matter of active research, which are called dynamic phase transition. For example, dynamic phase transition, by which I mean that there are phase transition, there could be situations where you can unravel a phase transition only when you shake a material or you apply an excitation to a material. So these kind of transitions, or you can also have phase transition driven by a high frequency excitation as a function of frequency of the excitation or amplitude of the excitation. So the answer to your question is that a DC shearing or stretching will not make the system undergo a phase transition, but on the other hand, a high frequency excitation can sometimes make the system undergo a phase transition. And on the other hand, there is one third thing. So it's actually, this is a question that has, it's a very interesting question that has many aspects. There is a third thing which is called metastable states, which is sometimes, for example, I showed you that a superconductor normally has pinning. Now, if the superconductor has a lot of pinning, then it is possible, for example, that the vortex lattice is not able to go to its equilibrium state. It is getting stuck into some metastable state. That metastable could be, for example, a disordered, it is getting stuck into a disordered state and not being able to go into, let's say, its ordered solid state. In those cases, often if you give, let's say, a sudden impulse to the system, it can overcome this blockage which happens because of the metastable state and go to its equilibrium state. So if Vishal allows me, I can give you a small example of this. Just give me a minute. Yes, okay. Let me then answer your question completely. So let me share this. All right, now let me show you how in some situations, so your question was whether by stretching I can go from a solid to a liquid, and I told you the answer normally is no, not in equilibrium, but if you have these non-equilibrium metastable states, you sometimes could. So let me explain to you what I am doing here. You can create, let's say, the vortex lattice in two different ways. One way is I cool the sample in zero magnetic field to the lowest temperature, like this. I go along this green line. I am cooling in zero magnetic field and then applying a magnetic field and creating a vortex lattice. So this is what is known in the literature as zero field cool state, and this produces, in this case, a very neat ordered vortex solid. On the other hand, I could come to this point on the HT phase diagram by first applying the magnetic field. So I have applied the magnetic field. I have applied the magnetic field at high temperature above Tc and then cooled it here. Now you see I get a completely different situation. I get actually here orientational glass which has lots of defects. So I have lots of dislocations. Now both of these are finally at the same point at 15 kilohertz state and at 350 millikelvin. So the question is that only one of these two states have to be the true equilibrium state. The other one must be a non-equilibrium state. How do I find out? What I do is that I apply an impulse to this. I shake the vortex lattice. How do I shake it? I give a magnetic field pulse. So I give a magnetic field pulse means I change momentarily the density and let it relax. So when you are hitting an object, that is exactly the same thing that you are doing. Locally, you are giving an impulse, so locally the density is increasing and then relaxing. When I do that on the zero field cool state, nothing happens. It remains as it is. When I do it on the field cool state, this is what happens. All the defects have gotten annihilated and I have a vortex solid. So now I know that the zero field cool state is actually the equilibrium state, and what I had gotten by field cooling along this red line was a metastable state in which the vortex lattice had got trapped. So I think, does that answer your question?
He's again asking about how non-Newtonian fluids behave. So is this an example of a non-Newtonian fluid?
No. Okay. So non-Newtonian fluid is is a very broad term. So in a way, this kind of pinned fluid can be non-Newtonian, but non-Newtonian fluid essentially is sort of characterized by something else, by the stress strain curve. So these here we have not measured really the stress strain curve, so I cannot really make a definitive statement on whether it is non-Newtonian. Given that it has many metastable states and it has a kinetics that is hindered by pinning, it is likely to be non-Newtonian. But to establish a non-Newtonian fluid, a different set of experiments need to be done.
Dr. N.K. Sharma is asking, Dr. N.K. Sharma is asking questions.
N.K. Sharma.
Hello.
Dr. N.K. Sharma.
Yeah.
Yes.
Yeah.
Yes.
I have one question. Hello.
Yeah.
Yes, sir.
I have one question. You talked about pinning centers in superconducting materials.
Yes.
So are these pinning centers enhancing superconductivity or destroying superconductivity?
So, okay. Pinning centers, whether they are beneficial for superconductivity or whether they are destroying superconductivity, that is the question.
Yes. Yes.
Okay.
Yes.
Pinning center, okay. The point is pinning centers have two effects. Pinning centers are actually impurity centers, and pinning the superconductors normally, conventional superconductors are extremely resilient to non-magnetic impurities. So if you have non-magnetic impurities, unless you have a lot of non-magnetic impurities, your TC does not decrease much. It might decrease by a tiny amount. So, however, what increases a lot is your upper critical field, because now your vortices cannot move. So if you had a very weak pinning, your critical current would be very low, and when in magnetic field, for example, if you want to make a high field magnet, then in a high field magnet, your superconductor will necessarily have vortex, and you have to make for a magnet to work, you also have to pass, let's say, some 100 ampere of current. You have to pass a humongous current. So now if you don't have pinning, it will just not work. You will not be able to make a high field magnet. So therefore, pinning is actually beneficial, but on the other hand, you have to optimize it. If you put a lot of impurities, then at some point your critical temperature itself will come down. So that will be detrimental. So this is a entirely, this is an extremely advanced and active branch of material science, is what is called as defect engineering in superconductors. So you try to engineer defects that have minimum effect on the transition temperature, but maximum effect in terms of being able to pin the vortices.
Okay, thank you. I have one more question.
Okay, for example, let me give you one example. So you have heard of all these experiments in CERN, the LHC experiment, which use huge, very big magnets, superconducting magnets.
Yeah.
So what do they use as the material? Niobium is a superconductor, but if you use niobium itself, niobium has really very weak, it doesn't have very strong pinning. So what is used instead is niobium titanium. This titanium you put in niobium essentially to introduce defects and to increase its pinning so that the critical current goes high. Okay. So this is one of the classical defect engineering, which is known, a trick that is known for many years. Yes.
I have one more question.
Yeah.
Yeah, I have one more question. See, what is the latest transition temperature achieved? Highest transition temperature. Yeah.
Highest temperature achieved.
Yeah.
So this is something that actually deserves a completely separate talk, because the highest temperature which has been achieved last year is room temperature. however, no, there is a caveat. Don't get too excited.
Yeah.
It was discovered in hydrides. So in multi-hydrides. So lanthanum hydride. Similarly, there was one on H2S. However, to get superconductivity above room temperature in those materials, you have to apply humongous pressure. You have to apply about 300 gigapascal, which is of the order of the pressure at the center of Earth. So therefore, though in principle superconductivity has reached room temperature, these superconductors are not really yet useful. They are so that kind of pressure you apply inside what is called a diamond anvil cell. So it's a specialized technique where you have two sharp pointed diamonds and you put sample inside these two diamonds and then you apply this pressure. Because diamond is very hard, you can apply this humongous pressure. But these are tiny samples and you will never be able to make a cable out of this with that pressure. So in terms of usable superconductor, what is right now available is about 100 Kelvin, which is high temperature cuprates, and there has been considerable progress in making devices out of cuprates and also cables out of cuprates. So it has not hit the market yet. It's still under development. People can make something like magnets of, I think, half a Tesla or so, little superconductors, but things are gradually improving. 100 Kelvin, though it is quite low, it's still not bad because it is above the temperature of liquid nitrogen. And liquid nitrogen is cheap.
Right. So one last question I would like to ask, if you permit me, organizers, please. Yeah. See, in the superconductors, there was one theory, BCS theory.
Yes.
So initially it was that BCS theory is responsible for the superconductivity in the materials. When cuprate superconductors were discovered, then this BCS theory could not explain how this superconductivity is there in oxide superconductors and visco system, thallium system superconductors. So what is the basic explanation about that, how these oxide superconductors are showing superconductivity?
Okay, so this is a problem that is not yet completely solved. So there is the part of BCS theory which does not work in high temperature superconductors is that the basic entity of a superconductor is a Cooper pair. You need electrons to form a pair. The question is, what is the glue that forms? What is the attractive interaction? And that glue in the case of BCS theory is very well understood. So in the original BCS theory, it is electron phonon. But then you can extend this to magnon. So it is a boson which is mediating this attractive interaction. In the case of high temperature superconductors, the problem is that it is this glue is non-trivial. What exactly the glue is something that is yet not completely understood. So people have fancy theories like resonance valence bonds and so on. It is thought that the underlying chemistry of the oxygen copper bond has a role to play in the pairing, but there is still no real consistent theory which captures all aspects. So BCS theory actually has set the bar very high in the sense that BCS theory is undoubtedly the most successful theory of modern condensed matter. Then if you take conventional superconductors, almost no theory explains so many things so quantitatively for a given phenomena. BCS theory, it works with every property of conventional superconductors for the gap, for ultrasonic attenuation, for the superfluid density. So you name the property, you can calculate from BCS, and actually you can do experiments and you can validate that. It just works. The problem with all the theories of high TC that have been proposed so far is that they work only on to explain one or the other aspect of the material. Some theory appeared very good when you try to match one aspect, one experiment, it matches very well. But then when you try to look for consistency across all the variety of experiments that have been done, you don't get a theory which matches everything. So this is a puzzle that is, I think, yet to be solved.
Okay. Okay, thank you.
It's a topic that will come up in the next session also. Okay, so there is another question that Dipayan Dasgupta has sent. He starts by basically he doesn't have a camera and all those things. I was very much impressed by the vacuum briefcase that you have improvised for such measurement. Can you enlighten us about more such instrumentation in superconductivity that you and your team have improvised in the recent past?
Well, so this actually will possibly require you to visit our lab sometimes. So our lab actually has a conscious policy to rely as little as possible on ready-made instruments. So we buy very few ready-made instruments. It is not that we don't buy, often we buy components and assemble ourselves. So we try to fabricate to the extent we can fabricate. So the kind of the low temperature scanning tunneling microscope, as you have seen, is a machine that is entirely fabricated in the lab. The electronics is not fabricated in the lab. The electronics is a commercial electronics, but the actual microscope is entirely built. Now, this is the most sophisticated instrumentation that we have done. There are many other kinds of instrumentation. Our pulse laser deposition chambers are all designed by us and fabricated by a company in the outskirts of Bombay in Vasai. And we have designed sputtering units again with this company. We have variable temperature inserts which have very good stability, actually remarkable stability from, let's say, 1.5 Kelvin to room temperature, which are all built in the lab. So there is a range of things that we have, and if you are interested, sometimes visit our lab.
Next question is, what is the effect of domain wall motion on magnetization of ferrites?
I couldn't, can you repeat?
Yeah, what is the effect of domain wall motion on magnetization of ferrite?
Okay, what is, I don't understand the context, this domain wall, which domain wall is being referred to? Is this is the context magnetic domain wall, or is the context of domain walls within a vortex lattice? So
that has not been mentioned here.
Okay, so I think this question is a little ambiguous. I am not able to completely grasp the question.
Okay, there's one more question. Do those quantum vortices collide with each other? I mean, do they behave like particles or waves type?
Okay. Now this again brings to something very interesting, which unfortunately I thought that there will not be the scope to cover it. Now, first of all, do they collide with each other? In principle, yes, because these are like particles, and therefore these particles would interact with each other, and it depends on what you mean by collision. They will repel each other. So if one tries to move, then it will of course push the other, and if that is meant by collision, they will of course collide. There is one difficulty with vortices as opposed to, let's say, ping pong balls or marbles, is that when you are working with marble or ping pong ball, they are all distinguishable. You can say, this is my ping pong ball, I write my name on it and then I track it. Unfortunately, on Vortex, you cannot write your name. One vortex is identical to another vortex. These are indistinguishable particles. So therefore, uh, at some point, if the motion of vortices is very large or very fast, then it does not make sense to say whether this vortex has gone there or that is the other vortex which has gone there. Means you cannot distinguish them anymore. That is the problem. However, I think if your question is more basic, do they behave like particles? Now, one of the things about quantum particles is that they have a zero-point motion. For example, if you take helium, then helium, you cool it down to T equal to 0, it still remains a liquid. Helium never solidifies. Why does helium not solidify? Helium does not solidify because it's a light atom, and the zero-point motion, which is the quantum mechanical motion of any particle which is trapped in a potential. The zero-point motion is so large that it exceeds the Lindemann criteria. So just from quantum mechanics, the uncertainty of quantum mechanics itself, the helium becomes a liquid. You don't need any temperature. So therefore, even at T equal to 0, it is a liquid. Very, very recently, we have shown, and this is a paper that we published just last month, that zero-point motion of vortices is actually also measurable. It is measurable, and we have measured it experimentally using scanning tunneling microscopy. So any property of a particle that you can imagine, and you can, from the zero-point motion, actually we have even estimated what is the mass of the vortex, and the mass of the vortex happens to be about 30 to 35 electron mass. So any property that you ascribe to a particle, here the vortices have it.
Okay. So that would be, I mean, there are a few more questions it seems, but then if it is...
Well, you have your schedule also to keep, so just at some point you will have to stop.
I will ask Shruti Shetty to give the vote of thanks to Pratibha.
Yes, sir. Thank you, Professor Pratap Rai Chaudhary, for such an insightful presentation on investigating a vortex solid using STM. The webinar was very illuminating and it will definitely help us develop an interest in the field of research. Thank you for such a beautiful explanation on exotic fluids and vortices in solids. I once again thank you for giving us your valuable time for this lecture. On behalf of entire physics department, I thank one and all for such an enthusiastic participation. Thank you.
Thank you. It was a pleasure as well.
Thank you, sir. That was our MSc student, and they would like to do some project also if possible on superconductivity. So probably they will be interested in doing some project on superconductivity, sir. Maybe.
Yeah, sure. So feel free to contact me.
Yes, thank you, sir. That's nice. Thank you. Yes.
So meet for the post-lunch session at 1:30.
Okay.
Thank you.
Thank you. Bye. Bye, Vishal.
Thank you, sir.
Bye, Vinod.
Bye. Okay. The meeting will be ended right now. We will use the same link to join back at 1:20, 1:25. हाँ, same link पे चालू होगा। हाँ। Shall we start?
Vikram? Yeah, can start.
Okay. So, our next speaker for this afternoon session is Dr. Tanmay Das from Indian Institute of Science, Bangalore. Am I able to?
One second. Huh?
Yeah, मेरा आवाज नहीं रहा. Okay, you can hear me, right? ठीक है. Okay. He is an assistant professor in the Department of Physics in Indian Institute of Science, and he did his
There is a lag.
Saying some.
There is a lag.
There is a lag.
CTS. CTS.
Oh, it's
there. It's there. Come. CTS. Just a second. I think.
Sound or
just a second. I think there is something with the device. Just a second. Michelle, come here. तुम्हारा लैग होता है मेरा लैग है ओके ओके
I'm so sorry. Okay, so the next speaker is going to be Dr. Tanmay Das from the Department of Physics, Indian Institute of Science. He did his MSc from IIT Bombay in physics. Sir? Slow. Then he went on to do his went on to do his PhD at Northeast University in Boston, and then this is annoying. Okay. Okay. Because I can hear my own voice a little later. That's okay. 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 So he did his work in Boston. Then he went to LANL, and then had a brief visit at National University of Singapore, and then went on to join IISc. He has about 100 publications and has more than 3,300 citations, which is basically the degree of acceptance of his work in the scientific community, and has an H index of 31, which is basically the degree of relevance of his work. So he will be talking on 100 years of superconductivity. He will be taking a journey of through the development of the physical aspect of or the physics of superconductors since before 19th century. So over to you, Tanmay Das.
Yeah, can you see me? And can you hear me? Vishal?
Yes.
Okay. Yeah. And let me. Okay, I need to share the screen as well. Let me do that. So let me know when you can see my screen. Huh?
It is visible, sir.
Yes, it is visible now.
In fact, I can hear you not so clearly, but as long as you can hear me clearly for the time being, we are fine with that.
Yes.
You can hear me, right?
Yeah, I can. Yes, I can hear you, and your screen is also visible.
Very nice. Yeah. Okay, so thanks everyone for thanks the organizer for putting together this nice one-day virtual outing, if you like, scientific outing, if you like, and having me there. I would have loved to be there in a person. Vishal is my friend. We are from the same place, IIT Bombay, and as well as I had many friends from who are the alumni of SIES College. So I would have loved to be. And when I was actually looking for the logo, and I went to the website and looked into the buildings and all, I knew that what I was missing. But, well, maybe next time. So I hope so. My talk is after you just finished your lunch, and I know that how it feels to listen to a science talk after, because I remember of going to library after lunch in the day in your age, and I exactly know how it feels. So I will try to make it pedagogical, little bit of, or a lot of stories, little bit of science, and a lot of gossips. This put and everything said is Dutch physicist or physicist. So he is credited and he is more known not for superconductivity but for he was the first person to liquefy helium. big deal because you know from thermodynamics what all it required. But once you liquefy, you can achieve those very low temperature, and you can use that to cool down many things. So once he achieved it and he built a huge lab, then he just hired so many people and asked everybody that whatever you find, just cool it down and see what happens. You know, actually, I just wanted to make sure everybody can hear me or something. Let me see if there's anything. Vishal, can you confirm whether you can still hear me or?
There is some kind of a problem in the YouTube, it seems, but then in MS Teams it is audible.
So should I just continue?
Is it possible for you to?
I can, yeah, it's fine, it's fine. I can wait. But I cannot hear you very well. So what this means, when it is all sorted out and you ask me to go ahead, as I said, I cannot hear you well.
Okay, we will record this session here and then probably put it in the YouTube later on. Yeah, we will record it, yes. Yes, we will record it. Second. क्या प्रॉब्लम है अभी भी नहीं आ रहा है नहीं अभी okay, you may possibly start from maybe one or two slides back. No?
Tell me again.
Hello. You can go back one or two slides and then start again.
Yeah, I'm actually in my first slide only.
Oh, then it's fine. Then it's absolutely fine. So what we are doing is basically recording this session, and then we will be uploading. Okay. Huh?
Yeah.
YouTube.
So everything is shared, so you can see the screen, right? In my slides.
Yes. It's visible.
If there is any such issue again, just let me know. I'll stop and start.
Sure. Definitely. Yes.
So I'll start, huh? Okay.
Yes.
So as I was saying, what I'll do is that I will first give you a story. I'll tell you the entire story of 110 years story, and these are, I'll try to do it kind of chronologically, but the story would rather flow better if I don't be completely chronological, but rather make the flow of the story according to what is important in steps in terms of understanding and progressing as a science, as the science progress, the stepwise process through which the science progress. Okay, and just to benchmark where are we at different stages of year in terms of material and superconductivity, the transition temperature below which a metal becomes superconductor. And just to benchmark, this is where all the things are, like Pluto, Moon, and Earth. Fortunately, Earth is at the top, so that our field of research is still active. We have not gotten the room temperature superconductor, and liquid nitrogen is here. And I'll tell you why I particularly mention liquid nitrogen. Okay, so most likely you already know what is superconductor. It is the super person, Superman, superwoman version of conductor, but I'll explain that. So everything started by this person, Kamerlingh Onnes, who is a Dutch scientist. He is rather more famous for liquefying helium gas, and then you obtain a temperature of the liquid which is 4 degree, 4.2 I think, but below 4.2, so 4 degrees centigrade, right? So that was a big deal. I mean, he essentially got the Nobel Prize for helium, liquid helium. But once he obtained that and he got the technology, and actually if you go to the Leiden University, he was at Leiden University, you can see that the original setup is still there in front of the university. Anyway, so once he obtained that, he just hired a bunch of people and say whatever you find in front of you, you just cool it down and measure whatever you can. I'm sure he will be bedazzled by everything you find, because nobody has and it's always the experiment was much ahead than theory, and obviously in material science there is no exception. You can find all this amazing thing. And one of his student indeed, when he cooled down mercury, he indeed found that the resistance of this metal sharply drops to 0 value. Yeah. Hello.
Oh yes. Oh, क्या हुआ?
No, so somehow I can only hear myself, so I thought some echo or something happened, but you can hear me fine. I will just continue. Huh?
Yes.
Okay. Yeah. So he found surprisingly the resistance just sharply drops to 0. 0 within the error bar, but now we know that it's absolutely 0 within the instrument, below the instrument's resolution, if you like. That happens at a temperature. That's the transition temperature of this material. Okay, so you can see it was in 1911, and this is the quantum mechanics was also not even invented. There are indications that people started thinking about it, but it was not even known that there is a quantum mechanics which exists. It turns out this is actually a quantum mechanical phenomena, but people, including Kamerlingh Onnes, sort of never believed that this is a quantum mechanics effort. Initially, everybody had apprehension about quantum mechanics anyway. So he always thought that this is some reason the material becomes a perfect conductor. Okay. Perfect conductor means, again, obviously the conductivity is infinity and resistance is 0. But later on, and with many other experimental evidence, we can distinguish a superconductor, not just a perfect conductor, but it is a new phase of matter. In fact, the phase of matter which is driven by quantum mechanics. Okay, So obviously everybody jumped into it to understand and to find better superconductors and all. And after a few years, these people discovered something called a superfluid phase of helium. Okay. And what that is that if you take one of these isotope, helium-4, okay, and then you cool it down, it gets to a phase in which the viscosity of this material becomes completely zero, not the resistance. Okay, so the viscosity, and so it's like the flow of whatever the particle that was going, it was just completely no scattering. But it was not the charged particle, because it was the viscosity, or it was the kind of energy transport, if you like. Whereas if it was the particle which were also charged particle, then they will also carry electric current, and it will also give you the resistance to be zero. But that was not the case. Okay. Initially, I think people even didn't know all this so much. They first thought that this is a manifestation of superconductor. And people started trying to understand superfluid in terms of superconductivity and vice versa, but it didn't work. But you understand the fact that these are different quantum particles. One is charged, another is not charged, but both sort of get to a phase in which there is no sort of resistance or scattering and so on. Okay. So I'll keep this aside and come back to superconductor. So why it is not perfect conductor was sort of convince everybody by these people, in which they found that as the material becomes superconductor, it also becomes diamagnet. So it starts repelling the magnetic field, and it's a pure diamagnet. It just repels the entire magnetic field. Okay, which is not necessarily the case for a perfect conductor. And then everybody starts thinking very differently. But by this time, I mean, he always advocated that this is a classical phenomena, but he sort of passed away in between, so he didn't get the chance to see that it is not a classical phenomena. Okay, and you can, and the diamagnetic phenomena is also called Meissner effect. It's just because a superconductor completely repels magnetic field, and it's like start sort of floating. This is a superconductor which is sort of cooled down, so and that's why you sort of see this gas are coming out, because it's been cooled down with liquid nitrogen. And this is some sort of a piece of magnet, and it is also so stable that it just keeps on going without any resistance or anything, but it also doesn't get derailed from it. And that's also been used in the technology, perhaps you already know. But I may also talk about it. Okay, so this phenomena was one of the very important kind of nail in the coffin to say that this is a different phenomena. And another is by this person named Josephson at Cambridge. He found that he took two superconductors and put an insulator in between. It's like a wood or something, and they were just coupled with some voltage and give some initial voltage. Actually, you do not need also voltage. Is ideally speaking, you start measuring current and you will find that there will be a current which will just pass through this insulator. Okay, that's clearly not the case for a metal. So that means whatever the carrier of the current, which we will find out to be something called Cooper pair, can actually penetrate through an insulator. And that was a very important fact. And that's also clearly, I mean, you know, by this time that quantum mechanical particle can tunnel the potential barrier, but it cannot tunnel so much if you make an insulator and big insulator and all. But Cooper pair is so coherent that it can actually tunnel. And that made a big role in the understanding. So then these are kind of the three main experiments, if you like. And then it sort of bothered everybody, every heroes of physics that you can think of during that time, including Einstein, Bohr, Heisenberg, Feynman, Max Born, and Landau, any hero that you could think of, have actually thought about it and had some proposal of theory of superconductivity, but all of them failed. There's a nice article of what sort of theories they all proposed and why they all failed and all. It's a nice article. You can find it from Google search. But there is one person here, John Bardeen, who is the same John Bardeen who invented transistor when he was at Bell Lab. And he was a theorist. So after transistor thing is done, he got the Nobel Prize for the transistor. And when he actually went to get the Nobel Prize, he didn't take any of his family member, like his kids. So the in the Nobel Prize ceremony, they were asking like, this is such an important event. Everybody sort of wait for their entire life to get a Nobel Prize to come to Sweden, to the Royal Society of Sweden, and you didn't bring your kids. How come? So he said, oh, they have some exams, so they are studying. But next time I come, I'll bring them. So it looked like a joke, but it turned out to be that he was not joking. Well, at least he kept his promise, and he got second Nobel Prize. And he got his second Nobel Prize for giving the successful theory of superconductivity. He and one of his postdoc and a PhD student. Maybe I should take a pause and remind you the theory that Landau, and everybody was thinking, Landau was also thinking, but he gave a theory which turned out to be a good theory for the superfluid helium, which are like chargeless particle, no viscosity sort of particle. And he showed, actually he used the idea of Bose-Einstein condensation. He showed that if the quantum particles, and what happens in this helium atom, helium-4 atom, these atoms are, and atoms are charge neutral, but atoms are bosons. Okay, atoms becomes boson. The atom can also become fermion because based on how much spin it has. You may learn it later, or probably many of you already know. If it's integer spin, it is boson. If it's half integer spin, it's fermion. And this turns out to be bosons. And bosons have a Bose-Einstein condensate. So what happens is that if you cool down, that means you reduce the kinetic energy of the bosons. At zero temperature, zero absolute temperature, all the bosons can actually go to the same state, the lowest lowest possible energy state. And in general, the lowest possible energy state is a state where momentum is zero. Okay, if you look at the momentum versus energy dispersion, that's typically come out to be the case. So every boson sort of condensate, and since it doesn't have any momentum, it doesn't have any scattering, so it doesn't have any viscosity. So it is a manifestation of superfluid phase, is a manifestation of Bose-Einstein condensation. In my opinion, and I guess many people's opinion, that was a kind of experimental evidence. So superfluid helium should be taken as a experimental evidence of Bose-Einstein condensation, and Nobel Prize should have been awarded to Bose. But there are only a few subtle differences between them, not in terms of that this is not a Bose-Einstein condensation. It is a Bose-Einstein condensation, but there are some other subtle physical properties that turns out to be slightly different. But in my opinion, I think this was a first experimental evidence of Bose-Einstein condensation. which should have, and the Nobel Prize should have been awarded accordingly. Anyway, once people realize that Bose-Einstein condensation can give you this frictionless behavior, and now we are talking about superconductor, which is a charged particle, and they are fermion, like electron. Essentially, we will find that these are the electrons which is carrying electricity. So why electron will suddenly have no friction, no scattering? They cannot condensate because these are fermion. There is a Pauli exclusion principle which prohibits all the fermion to go to one state. So they have to have different state to occupy. In fact, in one state, one can only have one electron or one fermion. So obviously it cannot condensate. But if you form a pair of two electron, then two electron with half integer spin, you get a integer spin. So this two electron pair or bound state can be treated as a boson and then can condensate, at least in principle. Okay. And that's the sort of idea they used, and it was the Cooper who came up with the idea first, and then these guys Bardeen and Schiffer worked out the details. But the problem in their theory, I mean, Cooper gave a theory that if two electrons can form a bound state, you can get superconductivity. But the problem is that these are the same charged particle, so there is a Coulomb repulsion between the two electrons, and there is no. I mean, then how can you make a bound state? How can they attract? Okay. I mean, by that time, similar questions were already asked in the proton, because the proton, the nucleus is made of all the positive charge, but how come they are stable? And Yukawa already had this theory that because of the exchange of some bosons between the neutron and proton, that effectively mediates a attractive interaction between proton, which is the strong nuclear force, and then you can get a stable. So you can get an effective attraction between the same charged particle by bosons. And boson also thought about, boson is kind of mediator of interaction, or interactions can also be thought about as exchange of bosons. Okay. And so, but we do not have any such neutron or anything for the electrons to provide a bosons. But you have lattice vibration. Vibration means it's phonon, right? And mathematically, you can write down a similar Yukawa sort of theory here. But let me give you the physical picture that how come those two electrons still start forming a sort of feel effective attraction. So think of an electron, and so these are sort of the atom which are sort of vibrating around its a mean value, and then there is and so this vibration and the vibration gives phonon. So what happens is that once an electron starts coming close to between two atoms, if you like, then let's see here. So once an electron comes close to an atom, close to a nucleus, which is a positive charge, it has a attractive potential, right? So a nucleus can be shifted towards this electron. We are looking from the reference frame of this electron. So what happens then, since it's been now moved, the center of mass of this nucleus and electron has shifted, and then you can think of an effective charge of this medium, which has now become positive. Because this is positive, this is negative, and the center of mass has changed. So you can just think of, and this is also larger positive. So you can think of an effective charge cloud around this becomes positive in this position. And that tends to attract another electron. So that means once this electron goes, it brings these two atoms close to and having an effective positive potential around it, then another electron will flow together close to it, and then they will start going. And that's how a effective attraction between two electrons forms, and that's the Cooper pair. So then I will show later, then these two electrons effectively can move without any scattering. And then it can also be think of as if this two electron has sort of condensate into the zero momentum state, and they are going to flow. You can immediately ask, if they all go to the zero momentum state, then how can they move? We will find that that's where the quantum mechanics comes. It's not the physical momentum of this Cooper pair, but it has to do something with the phase of the wave function. That actually gives you a effective momentum through which this Cooper pair will start moving. Okay. Very nice. So it's all explained well. Everybody is happy. And there are two other things that, because the previous talks also talk about vortices, and just to tell you how superconductivity is also contributed to understanding of other things, let me just point out a couple more things. Which the Abrikosov's theory of vortex in a superconductor, you were introduced to what is vortex the previous talk. So it's like some Cooper pair velocity or momentum or something, if you like. It's actually the direction of the wave function. Okay, but there is a special sort of a orientation of it. And then with some impurity or some reason, you can actually create this vortex, that exactly the same vortex you see in water or in the air when the tornado and all these things happens. It's the velocity field, the velocity of the particle that starts curling around. And once you have a curl, which is the conservative force, then you do not need any other energy or force. It is just a constant energy vortex, which you cannot destroy. And that's what it forms in the Cooper pair, between the Cooper pair. Or you may also think of the center, the relative distance between the two Cooper pair is sort of having a rotation. Okay. And typically one would form a vortex and anti-vortex together. And that's the cartoon wise, that's what it looks like. And we will show that that has some interesting effect with the magnetic field. And much later, 1973, these two person, Costaris and Thaulas, he also showed that whatever this vortex that Abrikosov was talking about, these are actually a topological sort of object or soliton, if you like. And this vortex also can behave like a particle. It's kind of a special configuration of velocity, you know. Or if it was all wave functions, if these arrows are some sort of a, because wave functions are complex, so it's two component, a real part and imaginary part, and you can take two component of the function and create a vector. So you can think that way too. But this is like some special solutions of those wave functions. We know that the wave function itself gives you a particle, or for a particle we assign a wave function, but the wave function special dependence, especially this car-like behavior, can also define a particle like solutions, which we call soliton. So vortex is kind of a particle. In fact, actually, interestingly, much before people had this quantum mechanics and we understand what is the particle of a wave or what is the wave of a particle and all these things, Lord Kelvin had a proposal that what we call atoms, the fundamental constituent of matter, by that time it was atom, and he actually proposed that atoms are like some sort of a vortex in ether medium. That time people were looking for ether between the sun and earth, right? So he said that, okay, atoms are created by this vortex-like behavior in the ether. Obviously, ether theory didn't work, and that definition of atom also didn't work. But later on, we realized that actually the theory itself stands, and the special solutions, special configurations of this wave function, or even you can think of this as spin. Actually, they did it for spin, and then they also realized that this can be realized in superconductor, can also be thought of as particle. And essentially, these are the same particles as high energy physics. People also talked about quark, because quarks are all elementary particle of proton, right? Proton, proton is a fundamental particle for us with the wave functions defined and so on, and which has a wave function. But if you take the wave functions of a proton and look for some special solutions, the wave function can also have this sort of a vortex or topological solution, which are called quark. So quark are kind of a manifestation of this vortex, if you like. Okay, so that means there are two types of particle or elementary particle that we talk about all the time. One is just defined by the wave function, and another is just the special solution of the wave functions, which are called topological particle. So they propose that in the superconductor, and it looks like a very nice story, and so many Nobel Prize was awarded and everybody was happy. Then you can start using it. I mean, everything is fine in terms of theory, but you can ask what's the use? Where are we in terms of usage of it? And these are the material elements or some of the materials which become superconductor, but they become superconductor only the maximum temperature was like 37 or something for magnesium chloride, whereas our Earth is here. There is two family which are discovered at different time, but I just wanted to show that these are the two families which we can understand in terms of this BCS theory. Okay, the theory that describes superconductivity. Okay, and there was also limit put by theories that you can never get superconductivity by this electron phonon coupling above this temperature. And so by this time, 70s or 60s, it was kind of a dead end. Right? Nobody was actually pursuing looking for superconductor also. Many groups just turned down or just started looking into some other field, not superconductor. And by that time, there was already quite a bit of, I just showed a few of them, but there are all the elements which were discovered to be superconductor. There are many alloys which were discovered to be superconductor. So there is this guy, Matthias, he studied all this material. And that time, the idea of artificial intelligence or machine learning was not there. So what people used to do is that people will just do everything, study all these materials by hand. So you can call it human learning. So he did that. He just studied thousands of, not thousands of thousands, but thousands of materials. And then he is just trying to find a roadmap that can we get some insights from the existing material and see whether we can find some clue how to get a better material with better superconductivity. And he came up with these rules, which are known for Matthias rule for the discovery of superconductor. Many of them are boring, at least for this talk, are like high symmetric material is better. Density of state, material with density of state, that means better metals are better superconductors and so on. But the other things he also noticed among the materials is that any material with oxygen is bad for superconductivity. Any compound with oxygen. Any compound with any magnetic compound is bad. Insulator is bad. And also he proposed that stay away from theorists. Theorists are junk. I'm a theorist, so I can say that. Okay. So don't listen to theory. That's what he said. That you just use your own intuition and don't get discouraged. Just so that means theorists put this limit that you cannot get a superconductivity higher than this value. So he just try to encourage people saying that don't be disheartened. Okay. Actually, some people, some research group, I know one research group from France who actually took these rules very seriously, and whatever the material they were studying didn't include any of them. If they find a magnetic material, they will not even search for superconductivity. Okay. And so a lot of people sort of narrowed down their focus. But this person, Alex Muller, who was at some IBM lab in Zurich, he was already kind of known. He had a very big lab and he got a very big grant to study material, to study superconductor. And he was a very intuitive person. He realized that we can make use of this electron phonon coupling, but rather than looking for phonon, but let's look for the distortion of the material rather than the vibration. And the distortion, if you make it collective distortions of many atoms together, and we can, any collective motions is like a wave, and then there is a particle bosons. So the collective distortion is also is quantized to call polaron. So he looked for material which are polaron, and he thought that okay, polaron might be the right way to go ahead. And he found the polaron material, which are most of them are insulator, magnetic, and oxides. These oxides are good for distortions. So then he was still very optimistic that we should still pursue, but he was not able to get any PhD students because PhD students all took this Matthias Bull very seriously. Then they thought, okay, what is this Alex Muller talking about? I don't want to go and ruin my career by studying oxides, looking for superconductivity. Okay, and so in fact, there are few people that who became known later on, but they turned down his offer to study superconductivity. But then this person, George Bednoch, he graduated from some university, but his PhD didn't go very well. So he was just looking for some job in some industry, and he was also probably not getting it. So he thought that, okay, fine, I will get some salary. So let's go and work with this crazy person and listen to whatever he says. Okay, so he joined. And what they had this idea is that the lanthanum, barium, copper and oxygen 3 is the compound which has large distortion. And Muller said that this is the material we should study for superconductivity. And they tried to grow that sample, copper oxygen 3. Okay, and they grew the sample. Then they doped it also, because if you drop the sample without any doping, it's an insulator. So you have to, and also magnetic. So you have to dope it to sort of get a metallic phase and also kill the magnetism, which they did. And then they measured and it found high temperature superconductor. Okay, so then they realized it's a big deal. They wanted to confirm. And by this time, publications and getting scooped and all these things came into things. So everybody has to be, if something is big, everybody has to be very careful in publishing it before somebody news is leaked and somebody else published. So they shut down the lab and fired everybody else because they wanted to make sure they got it right, and because they knew that it's a Nobel Prize. And the legend says, I don't know how much it is true though, but the legend says that they sort of waited for a year. They just trying to make sure it's done and so on and so forth. And by the time maybe the news was leaked, somebody else started growing a better copper oxide material. And then they got to know that somebody else, including some people from India also. There was a lawsuit recently about who got the highest copper oxide superconductor, but eventually these guys won the lawsuit. But anyway, coming back to, so then they realized, so they published, but they published with a wrong formula so that nobody can get it scooped. And at the proof level, they corrected the formula of the compound. So the story is that they wanted to grow copper oxygen 3, but by mistake they grew copper oxygen 4. And that is the compound which is superconductor, but copper oxygen 3 is not superconductor. So with all this hard work and all, essentially it was the luck that helped them. And it was such a big news at this time. And I think like all the conference in the world, everything is just talking about superconductor. All the technology industry start jumping into superconductor because now we have the room temperature, or we have the hope to get the room temperature superconductor, and that is going to change the world, right? So everybody start jumping into it. And there are also Hollywood movies made on it. In fact, I was watching this movie, which is a comedy movie, which has a Bollywood version copy of it. And I was watching it as a, without knowing anything about the story, as a comedy movie in one fine evening. And the story of this movie was that these bad guys are trying to smuggle a piece of metal. And the entire FBI, cops, and everybody is trying to resist that smuggling. But everyone is completely frustrated that why this crazy guy is so much fascinated to this small piece of material. And at the end, when this bad guy is caught, and then the cops were asking like, why you are so crazy about this material? It looks like some gold or small gold. Then he hold off his hand and said, do you know what it is? This is the room temperature superconductor. Okay, so okay. But there is an Indian version of it, but obviously without the superconductivity part. And that is the discovery of copper oxide superconductors. And then again, a lot of gaps. And then iron-based material was discovered by this Chinese person. And actually, he is a semiconductor guy. He was looking for better semiconductor, but he discovered superconductivity, a semiconductor, and he discovered superconductivity. Recently, a higher transition temperature superconductor is discovered, which is in the hydrogen compounds. Okay, and I'll show you what sort of transition temperature we get. And so far, this is the guy who got the Nobel Prize for copper oxides. But the problem it starts is that this is a material in which Coulomb repulsion is very strong. In fact, I will tell you that story later. Okay, so this was all the materials talked to you about, which are the early classes of superconductor, which we can understand from electron-photon coupling. These are the other families which doesn't follow the electron-photon coupling mechanism. Or the BCS theory. BCS theory means this Bardeen, Cooper, and Stifford's theory. Okay, this material class was discovered before the cuprate, but it didn't get much attention because the transition temperature is very small. On the other hand, these cuprates or copper oxide materials got all the attentions, and also you can see everybody jumped after this discovery. Everybody sort of jumped into this field, and within a year or so, the highest temperature superconductor was obtained above liquid nitrogen. And liquid nitrogen is much easier to get in every labs, very cheap. So everybody can do this experiment. Earlier it was only very few people could do, but now everybody can do. So although it was not room temperature, but this was good enough for all labs as well as for many practical purposes also, including your NMR, MRIs, or even these maglev trays. And these iron-based materials, which are also there, but didn't sort of go all the way. Organic materials also. Okay, and these are all the materials in which the BCS theory doesn't work. The reason it doesn't work because you can see that these are the materials. They are magnetic, they are insulator, and what that means, the electron coulomb repulsion is very strong in this material. So now if the repulsion between two electrons is more, no matter how much attractive interaction you get through electron phonon coupling, the repulsion will always win over the attraction. So there is no Cooper formation possible. So obviously, but still there is a Cooper pair, but not the electron phonon, but the attractive potential is not enough from electron phonon. So then people started, now it is still an active field. We still do not understand where it is, where does this come from, but it has to be some effective attraction between electron that comes from many electrons interaction, Coulomb interaction itself. But this is still an open field. Okay. But my purpose is not to talk more about this open field. I will go back to the previous one to understand these properties. And let's tell you a little more about the last 5 years of what we have achieved. And one of the fun things is Japanese people did, and I'm sure you know that they are extremely hardworking, and as well as they also like to enjoy very much. So I don't know if it was a drunk experiment or they had some guideline. What they did is that they merged some of the superconductor into wine, and they started measuring resistivity. They found that the superconducting transition temperature can actually be increased of the order of magnitude, if you like. Okay. I had and looked into all sorts of alcohol, whiskey and Japanese alcohol, so on, and they found red wine is better for larger superconducting volume fraction. That was one fun thing. So then some recent experiment says that if you shine light, there is a chance. It's still not very well confirmed though. So there is a chance that you can make this superconductor to be room temperature superconductor. So there are a hydride, hydrogen sulfide, hydrogen lanthanum sort of family of material which seem to have superconductivity at room temperature. So the price you have to pay for this material, the pressure is like 250 gigapascal, which is too difficult. In fact, most of the samples will even crack. So I think this is still an open problem, even from the open challenge, even from the experimental side. And I guess you all know what sort of potential this superconducting material provides for technology. And some of you know, like power grid, of course. No resistance was excellent power grid. You can use the Meissner effect to have the magnetic levitation train. MRI, NMR, particle physics. So particle therapy, I do not know, but in the particle detector, they use nuclear fission there to shield the radioactive material they use, and LHC high energy physics detector they use, and many other. And some of you, you know, few others maybe I know, but I guess many others, even those who are talking about, they do not know. But these are kind of idealist design. Okay, so I can briefly talk about some of these properties and try to understand few of them. But before doing that, I want to understand how much more time I can get. Maybe not, huh? Vishal?
You have three, I think. Three, right? 3 up till 3 you can go.
3 or 2 minutes.
And then there will be 30 minutes.
I can talk 30 more minutes.
Yes.
Oh, that's fantastic. Then I can complete.
Yeah. Huh? No. It's till 3:15. No? Yes, you can continue.
Okay, I think I need just 20 minutes or so.
Okay.
So what is superconductivity? We already know. It's a property in which the resistance just goes to completely zero. And let's try to understand what it means though. We also have said that this is a property in which no magnetic field light can penetrate the material. Above superconducting transition temperature and below superconducting transition temperature, this is how it should apply. And yes, I hear some sound. Is it something for me or?
No, there is no.
Okay, fine. And then I also said that there is a Josephson current. The superconducting current can even flow without any voltage through an insulator. It's also a thermodynamic phase. I mean, we know from thermodynamics that there is a phase transitions like solid to liquid, solid to liquid to gas. And this is also, this perfect conductivity is not just an accident. It's actually a sharp phase transitions in which the specific heat has also jump. So that means this is a second order phase transition. And obviously it's a quantum phase transition. And I already gave you a hint that this is a phase transition. This is like a condensation. But it's not a condensation in the Bose-Einstein condensation sense, in which all the bosons go to zero temperature, go to same state only at zero temperature. But this is a condensation which is happening at some finite temperature in which all the Cooper pair goes to the one state. So it's just a sudden jump. So that's why it's a phase transition. And we'll try to understand what it is. And obviously there is no resistance, so there is no way to decay. So if you make a loop and start an initial current, then ideally the current will never decay. So, and it will just keep on going. So if you have a circulating current, you know from electricity magnetism that there will be magnetic field. So one can actually use this superconductor to get very stable magnetic field, which you couldn't get in any other magnets. Then you can get quite high magnetic field here, like 13, 14 Tesla. And another thing is the property known from experiment is that, so we know how the band diagram looks like, energy versus something here, doesn't matter. That you have a Fermi level, and if you have a metal or conductor, there are sort of free fermions floating around the Fermi level, so that there is no gap between the conduction and valence band. So these free electrons are accessible for conductivity. That's how you get metal. Whereas for an insulator or semiconductor, all the electrons are sort of frozen, and there is a band gap to take out this electron from your Fermi C to your empty states, to mobile state, so that you could get a conductivity. But there is an energy gap. You need a high energy, you have to pump the energy through temperature or something to get conductivity. We know that these are the definition of insulator where there is no conductivity. If you look at the band diagram of a superconductor, it is also actually from experiment. I think some of these STM experiment that you saw from the previous talks, that they are actually look like an insulator. But then you say this is an insulator which doesn't conduct at all, and this is a superconductor which looks like an insulator, but it conducts without any problem. So what is happening? And the clue is here, that when we said insulator, we said that there is no free electron. And this is also an insulator because there is no more free electron. All the electron has form a bound state with another electron and Cooper pair. So when we say insulator and when we measure insulating behavior from STM, it does mean that there is no free electron, but the electrons has formed a bound state. It actually has, you have taken this conductor, reduce the temperature, all these electrons form copper pair, and then you actually got to a copper pair. But then if all the electrons are now bound, who is carrying the current? Right. So that's what we will try to understand. But before that, let's try to understand a few things from the basic physics. So when we think of understanding current, voltage, we use Ohm's law, right? The proposal of Ohm's law is that current is proportional to voltage. The proportionality constant is the resistance. And resistance is a very ill-defined thing, because if I tell you what is the resistance of this material, you don't know what is this size of this material and all. So you want to talk about in terms of some material independent quantity. So you want to divide things by per unit length, per unit area. So you define resistivity and conductivity. If I tell you the conductivity of something, you know which material it is, iron or copper and all. But if I tell you resistance, you do not know immediately. So this is the more fundamental material specific property. So in terms of that, you have this formula, which is you just divide this by volume, and then you define a current density. So current divided by area. Then you have this resistivity inverse, which you call conductivity, and this one you call it electric field, because electric field is voltage divided by length, right? So this is the formula. So if I use this Ohm's formula and I say that there is a persistent current without even, that means there is no electric field, but the current will never decay. What this means, if there is no electric field, there is no current. So obviously, right? So conductivity is infinity. So that means the persistent current is not possible according to Ohm's law. Or current without an electric field or voltage is not possible. So obviously, you want to understand it. And what is the source of resistivity? The source of resistivity is usually from the Drude model, that there is a scattering of electron through phonon or between electron and electron. So there is some sort of a mean free path or average time between the collision that sort of gives you this conductivity. Okay, what this means, there is an average time by which the electron loses energy and loses momentum, and then it sort of stops, and that's how the resistivity appears. So so it sort of breaks the conservation laws, right? And that's how the resistivity happens. But when we are thinking about persistent current, so current is conserved as a function of time, it doesn't change. So we should actually go back and look more fundamental laws which are based on conservation laws. And when I was preparing this talk and I spoke to Vishal there from your institute, he actually pointed out what London brothers did. He's actually thinking in terms of Newton's law, which are the law which is based on conservation laws. You know, the Newton's law has energy and momentum conserved. So he actually used that law rather than used Ohm's law. He said that, okay, this is the acceleration and this is the electric field. And we know the current density, which is N, density of electron, density of particle, charge and velocity. And you just substitute it, you get this expression which is different from this Ohm's law. So it's the time derivative of current that is proportional to electric field rather than the current itself. Okay. And that just comes from the fact that there is no loss of energy or momentum. Okay. Now you can put E equal to 0, and if you solve it, you'll get current to be constant. just the differential solutions, right? So this one can solve. So that means there is a no friction, and that is consistent with the fact. Why there is no resistance and all, we do not know, but that's what it means. That's what London brother found out. You can actually use that also to find out why there is a diamagnetism. You know diamagnetism, that it is because of the electrons making a circular motions, giving another magnetic field which repel the original magnetic field. So it's the orbital magnetic field. So what we can try to obtain that from here itself. So let's take curl on both sides. Okay, curl on electric field, we can then use Maxwell's equation. You can convert this, use this equation, and then substitute magnetic field here, right? And now we have another magnetic field which is coupled to current from the Faraday law. So then we need to then take one more curl. So let's take one more curl on both sides. Then we know these relations. Curl of magnetic field is gradient, and then this one Laplacian. But then this one again, we know that there is no monopole. So use that. This one gone. So now substituting this on both sides. Here instead of J we put this one, and here we had del cross B, which we have used this. Then we can obtain this, and this is a solution of a Laplacian, kind of an eigenvalue solutions if you like. And if you solve it, the magnetic field as a function of position is going to decay with some length scale called penetration depth. And this is the magnetic field at the outside of your sample. Come to this one actually. Let me talk about this first. So what we have this superconductor, we put some magnetic field outside. Now magnetic field cannot penetrate, but it does penetrate according to this law, but it decays exponentially fast. Right? So what happens, why it decays is that when you put a magnetic field, there is a current of this Cooper pair, persistent current, and that produces a magnetic field which is completely opposite to this external magnetic field. So it cancels the magnetic field, and that's how it looks like there is no magnetic field inside. So that's how you have diamagnetism form. And you apply more magnetic field, then you break some of this Cooper pair, and then it can penetrate more and more and more. And this is the length scale, which is called penetration depth, which is consistent with this theory. So now you understand the diamagnetism as well. But this vortex that Abrikosov talked about is that instead of having this Cooper pair making these rotations of the entire system, if there are impurities or something, this Cooper pair can also make a circular motion inside. And it can actually make a motion by virtue of the impurity in a reverse direction, such that there is like a magnetic field which is sort of a penetrating in the same direction as this. So that's how in this region, if you have enough impurity, there is some magnetic lines which can penetrate, and that's the vortex. You can say, what is the supercurrent? I still have not talked about. I said that momentum is zero, so there is no resistance. I also said that there are conservation laws and all, but where does this current coming from? Who is actually carrying it? All the electrons are also from Cooper pair and sort of condensate, frozen down, and you got an insulating like band. So who is actually carrying the current? This is actually true manifestation of the quantum mechanics. Quantum mechanics has a complex wave function, which has an amplitude, which tells you the probability of having the particle, finding a particle in a given position. But there is also a phase, which is usually arbitrary. Right, we cannot determine that phase, and that's the arbitrary end of a phase is also called a symmetry. So it's always the case. I mean, actually, yeah, let's not talk about the symmetry. It's called gauge symmetry, but let's not talk about it. Okay, so phase is arbitrary in a given quantum mechanics. which is arbitrary. And usually we talk about a wave packet which has a group velocity, and that's the velocity of the particle. If you want to know the velocity of a particle in a quantum particle, you just look into the wave packet's group velocity, which is a collection of many plane waves which form a group like a standing wave. Then it's like the velocity of the standing wave. And you can see that it's kind of a collection of many plane waves. And then any scattering, the particle can lose the momentum and energy, and the velocity can change. It gives you, it allows you to transfer momentum. But in superconductor, we said it's a condensation. What happens is that, which is very difficult to explain. I may need another 15 minutes if you want me to explain, but you can just take it as a fact that this is a phase transition in which all the Cooper pair has the same and constant phase. Every Cooper pair will just take one phase. So it just breaks that symmetry where the phase can be arbitrary. And constant means everywhere also. And all Cooper pairs will have the same. So it's like a laser. It's like a complete coherence. Okay. So now you allow some perturbation or some energy or something to try to perturb that phase. This is try to change it from whatever the value it acquired. And if you try to change it in position, then you can write it in terms of this I dot P. It's just a definition. From here, you can define a momentum. So that's a phase velocity you can define. And the phase velocity, as you know, is always constant, where the group velocity can change. It's kind of an example here. This is your group velocity in a wave packet, whereas the phase velocity is always constant. So phase velocity is of a plane wave, which a plane wave means it doesn't have any potential. So if you can get a plane wave by virtue of this phase condensation, which feels no potential at all, and your momentum will always be constant. So this is the momentum phase coming from the phase velocity, and that's what it is. It never decays. Okay, so it is the phase gradient which gives you a momentum, and that's how the Cooper pair, or that's how the current is accurate. Okay, and that's what the Josephson actually what the junction is. You take two superconductor, so each superconductor can take a constant phase, but nobody guarantee which phase it will take. It just tells you that it will take one phase. But the same superconductor, if you grow it again, it doesn't necessarily go back to the same phase. It can go to another phase, but constant and same phase. So another superconductor will also have another phase. So if you bring it together, you actually have created a phase gradient between them. And that's how you generate a spontaneous phase velocity. And that's how the Cooper pair tunnels, like a plane wave, like a scattering wave or oscillatory wave. That's why you get a Josephson current without even applying any electric field. Okay, and then I can take this small fact that there is a stiffness to change to return the same phase of the Cooper pair. Right, I mean the system will always try to keep the same phase even if you try to destroy it. So that means there is a binding energy which is required. If you need to, which is the energy required to break a Cooper pair. So there is an internal energy associated with the energy, and there is also an entropy. So this is just coming from the thermodynamics, that how many ways you can obtain Cooper pair, how many. It's not that this electron always will form a Cooper pair with this. It can form a Cooper pair with any other. So there's a huge entropy cost, and entropy cost becomes important when the temperature is finite. So there is a competition between them, and essentially we always want to minimize the free energy. So at some point there is a minimum of the free energy coming from the formation of binding energy, but with finite temperature there is a entropy which can actually take over, and it can destroy it. So that's how your superconductivity can be destroyed. Thermodynamics. You want to understand in terms of thermodynamics, and that's exactly what happens. There is a binding energy which separates the free energy of a metal compared to the free energy of a superconductor, and this is the energy which is the binding energy of the Cooper pair. And as a function of temperature, it slowly goes down, and at some point they meet. So then superconductivity is destroyed. That's if you that's how the free energy will also look like. It's a lower free energy in the superconducting state, higher free energy in the normal state, the difference between them. And if you take double derivative, you will get specific heat. So this is the second order phase transition. So with that, I am done. And as I said, high temperature superconductor, we do not understand. And I'm sure there are many more Nobel prizes which are awaiting. So just put it in the perspective. So picture will be here. Thank you.
So the floor is open for questions. Yes.
Anyone has any question? Okay, someone asked what was the reason for the wine increasing the superconducting temperature?
I wish I had an answer. No, if you are asking for fundamental reason, there is no explanation. In fact, it's not only wine. Many other substrate, many other junk can also increase.
Okay.
There is absolutely no idea.
So do they form centers of seeding centers for interaction or increase in interaction of the electrons to form help in the formation of?
Absolutely no idea. And if you try to see why there is a Cooper pair form, what is the attractive potential in this family of superconductor, which is not electron phonon coupling, then maybe we could think how wine is helping, or alcohol compound, chemicals are helping. Okay. But also, I mean, even these alcohol compounds, whether they goes to every unit cells to sort of change the chemistry at every unit cells to provide a medium or screening in which the Coulomb interaction is changing and all. It's very a hard question to answer.
Okay. And there's one more, I think. Okay, is there a possibility of finding superconductivity at the center of stars?
Center of stars, there are always superconductors.
They are always superconducting.
There are neutron stars. I mean, neutrons are all fermions. Well, they are not charged, but astrophysicists have been studying superconductivity for fermionics systems all the time. There are all sorts of superconductor, Meissner effect. Even some of these I mean, we discussed with colleagues, and I'm not sure if I remember all the keywords. Is it the neutron star or somewhere that they do see Meissner effect? And well, it's not electron for sure, but you do not need electron. It's the fermions, right? Essentially, which will form pair if there are some effective interactions. There, obviously, there is nothing like a phonon or vibration. So if you can also understand this, in fact, gauge theory also gives you, and gauge theories are what causes this protons to bind. I mean, gauge theory are the mediator of strong interactions between protons and all. And they are also, gauge theory can also give you attractive potential. And then the fermions can create Cooper pairs. In fact, Yukawa potential is a manifestation of gauge theory mediated attractive interaction between fermions, protons or fermions. And that's exactly what is happening, maybe even many other way. It is happening in neutron star, all sorts of stars. Where, where they are all fermionic atoms, particles.
And what is the reason for the region of superconducting and a non-superconducting this thing in quantum vortex region of superconducting and non-superconducting region? That's what I
If you are asking in terms of this vortex,
yeah,
I can tell you. If you are asking in terms of this, I have to tell you in a different way, but I presume you are talking about this one, right? Where the vortex are forming. I mean, think of a Cooper pair, which is sort of circulating around a magnetic field. And because it's like a cyclotron orbit that we have all studied, right? That any charged particle couples to a magnetic field, and then you have this cyclotron orbit, and it will just go around. But think of having some impurity. So then it will hit back, and then it will start rotating around that impurity. Okay. And it can wind in every direction, but the one that we are interested in are the one which is winding in a different direction. So that if something is winds, a charged particle winds, then it creates a magnetic field just from the Faraday law. So that's why you can think of a magnetic field is penetrating now through this. And that's the kind of cartoon picture of having magnetic field penetrating through the superconductor, just through a vortex formed due to impurities.
So it is like type 2 superconductors that you see.
This is the type 2 superconductor I'm talking about.
And in the case of, can organic compounds be superconductors?
Yes. So organic compounds.
What would be the criteria?
Oh, it is the same. It is the organic compound are like benzene and all, but these are all elements, carbon. And here the organic compounds have, these are all carbons and all sorts of compound, but there are copper and other elements. But these are essentially, if you go back to the atoms of all these elements, these are all carbon, copper and all, which have all the electrons and quantum mechanics, and everything is the same. In fact, many of them have crystal structure, solid state crystal structure as every other elements. Then you have the same physics. You know?
Okay. So, what is the criteria for having a superconductor?
Okay, so we believe that this is not the same criteria as electron phonon. So when I said I can only tell you that what it is not. I cannot convincingly tell you what is it, because if I knew it, I will know kind of the same thing for every other material which we do not know yet. Okay? Which you do not know yet.
So are there any possible methods for explaining?
We are working on it, and it is some sort of a effective interactions obtained by many repulsions between electrons. It's a many body, many particle scattering term. Physically,
Emergence.
Yes.
An emergence property.
It is an emergent property. I can give you one example to think. So So when we talked about phonon, what we said? We said all these atoms are periodically positioned and they are vibrating. And then we saw from classical mechanics that there are normal modes. And in quantum mechanics, there are many normal modes according to various wavelength. So there are, and those normal modes are we called phonon. We just quantize them, and the waves or all these oscillations, collective oscillations of all these atoms, collective oscillations are like wave, and then waves can only take quantized value of energy, and we call them phonon. And the phonon was the bosons, which we can show from calculations that can mediate an attraction. And I gave you a cartoon on how that happens. So now let's think of spins. Spins are like some vectors. And think of a ferromagnet, let's say. All the spins are aligned. You can see my hand or not?
Yes, yes. It's kind of small. But,
Yeah,
I
but
think
anyway, I think what I'm saying will also make sense if I can say it with clarity. Let's say all the spins are up spin, okay, aligned. And all the spins are coming from all the electrons or all the atoms, which are all sort of aligned in a ferromagnet. But then there are quantum fluctuations in which the spins are also fluctuating. Quantum mechanics says that nothing can be completely known. It is always changing, fluctuating. So it is fluctuating. But then you can also use the same theory that you did for phonon, that there is a collective fluctuation. So it's like slow, slow, slow to all the spins. So this collective fluctuations of spin, or variations of spin, or oscillations of spin can also give you a bosonic like particle, like exactly like phonon that we talked about. So there is a wave of these spins changing, and then we can quantize, and then the change of this energy of the spin rotations will also take quantized value of energy. And those quantum particles we call magnon. Okay, and this magnon is bosons, which can effectively mediate attractive interaction.
okay. So, since it is this thing, what I will do is I will ask for the student to give the vote of thanks. Just a moment. It's 3 or 5 already. Okay.
Vishal, I'm done.
Yes. I'll just. I would ask Famida to give a vote of thanks. Famida Bano, I think.
Yes, sir.
Can you unmute yourself?
I would like to thank Professor Tanmay
Okay, your voice is quite low.
Hello.
Yes, yes. Now you're audible. Yes, yes. Yes, you're audible. You're feeble but audible, it seems.
Yeah, I can understand what you're saying.
I would like to thank Dr. Tanmay for such an interesting and insightful presentation on 100 years of superconductivity. Thank you for providing us such an opportunity to be a part of this informative webinar. I'm sure it will definitely help us develop our interest in field of science. I would like to thank you again for sparing me valuable time for this webinar.
Okay, thank you very much. I'm very glad to talk to you all. And I hope at least you feel a little bit of inspiration to study superconductivity, to know more about superconductivity. Okay, thanks.
Yes, they definitely would, I guess. Okay, so with this, we can go to the next speaker. Okay, the next meeting would be at 3:15. So we have some 8 minutes left. So we can come together again after 8 minutes. I think the speaker has already come. Oh dear.
Okay, welcome back to the last session of this day, of this one-day workshop um, on frontiers of physics. Today, the last session is being the last lecture of the day will be taken by Dr. Anuja Datta, who is a Ramanujan Fellow at ISCS, Ramanujan Fellow and faculty at the School of Applied and Interdisciplinary Sciences, Indian Association for the Cultivation of Science. She did her MSc from Jadavpur University in geology. She is a gold medalist, and she came into doing research in material science and physics. So she went on to do her PhD at ISCS in 2008. Then she went to do her postdoctoral research and became an assistant professor in the Department of Physics in University of South Florida, Tampa, USA. And then she went on to become a research fellow in Clare Hall College, University of Cambridge. Prior to, okay, so now she has her research interest she works on energy scavenging processes to develop, produce energies, basically to scavenge energies from sources, micro energy sources. Her topic for the day is harvesting microenergies, paving science and technology for sustainable future. Okay, so over to you, Anuja.
Thank you, Dr. Vijay. And I'll share my slides. But that was a very elaborate introduction. Whether I won a gold medal, that doesn't really count here. And it was in geology. So that was even not meant to be counted here. So can you see my slides? Huh?
Your slide is...
Yeah, somehow your voice is breaking down. So if
okay,
my voice breaks
down,
you also please let me know through chat or something so that it doesn't end up being a disaster. So thank you very much, Vishal, for giving that introduction. And first of all, I'd like to thank the organizers for giving me this opportunity to present my research topic here. It is not exactly the research topic. It's a topic which is very relevant to today's world, smart world, as we say. And as Vishal mentioned, that it is I work on mitigating energies. It's exactly not the same. I work on mitigating self-powered mainly worked on the ferroelectric material for memory devices, but then I slowly started exploring this microenergy industry, and I found that harvesting microenergies can give you like a big opportunity to explore the science behind the physics, chemistry, the engineering part, and also it has a direct application that actually intrigued me a lot. I started following this path of research. And unlike the talks that we have heard, I was actually present in the morning. over. Talk, and I like that, and it's very suitable for the students. Students want to know the research world to get motivated, and of course they are going to learn more when they get into the research, but it's mostly to motivate them. That's what I got the idea from when Vishal talked to me about giving a lecture here. So my topic here is actually not pure physics. It's a blend of materials engineering, materials physics, materials chemistry. So you can say that it's kind of everything together. That's why I'm in School of Applied and Interdisciplinary Sciences, and we have students, PhD students and MSc students from different backgrounds, from physics, from chemistry, from engineering, even from biology. And that's how we love to do. And that's how the interdisciplinary research works. You need the expertise of all the different people in the fields. Sorry, that is a call. So before I start, I'd like to first thank the funding agencies, that's SARB, which is providing me with all the facilities that I have started in ISCS, and SARB again for recently granting me a core research grant to look into the organic ferroelectric materials for energy and membrane devices. And of course, since I'm still a fellow of Clare Hall College, and it gives me an opportunity to thank Clare Hall College, University of Cambridge here, and School of Applied Interdisciplinary Sciences when I'm housed in, and also ISCS. And I came to know that probably not many of you have known the name of ISCS, which is Indian Association for the Cultivation of Science, which is the oldest research institute in Asia. And it is the only institute which has given a Nobel Prize in physics from India, which is by Dr. C.V. Raman, by Raman effect. So we still have that Raman spectroscopy, which he has used for getting his Nobel Prize. And definitely, I'd like to first pay my homage to Dr. Pai, who I have heard is a stalwart in her own field in teaching, which is the best thing actually to motivate the students. So with this, let me start. So since I'm talking about sustainable future, so let me, it's a more general thing that I want to actually discuss here. So what is sustainability? Of course, we know, all of us, we know, we hear news, we read news, and we know all these things from blogs. But sustainability is something in general, which is a method of harvesting or using any resource. It doesn't have to be an energy resource. It has to be any resource that is not depleted, or we cannot really permanently damage it. So that is how any sustainable practice actually works. So last June, when I went to find some research in Los Alamos National Lab webpage, there I saw that they are routing for these sustainable practices. Almost all universities, almost all companies, all R&Ds, governments, they are now routing for these sustainable practices. And here I want to show this is called Circle of Sustainability, which started in 2015. And Vishal, can you hear me, or any? I mean, it's okay with my voice and everything.
Yes, it's audible. Yeah.
Okay, thank you very much. And we started in 2015. We started with very small inclusion in this circle of sustainability that included environment, social, economic, equitable, then viable resources and everything. Then in 2020, the circle of sustainability has increased more and more, which included partnership, people, prosperity, and the people and prosperity. They're all connected together. And this partnership means this partnership between the government agencies and the stakeholders, the companies, the research labs, they're all connected together. So research in sustainable energy is actually driven by this sustainable practices that is going on since 2015. It is a bit of a rush in this area, but before 2015, we have also seen that how energy and like research have gathered momentum. But the sustainable energy practice is all about one goal: to reduce carbon footprint. and to reduce global warming, to make the temperature, which is about like 1.5 degrees centigrade below what is going on right now, average temperature on Earth. So the main goal for the sustainable energy is also to introduce, to focus on energy efficiency, to produce cleaner electricity from fossil fuels. We cannot really take out from the equation, because that is still the most important energy source for everything. But what we can include in is the cleaner energy practice. And at the same time, another term has come into recently, which is called energy security. Means like how efficiently you are using these resources, and at the same time, like you are not utilizing that source of energy for something which can destroy the whole practice. Means like, let's say nuclear energy, of course, the practice is that you're going to use it for energy production, not for warfare, because that will go against all these momentum that is going through this for past few years or past several years. So from 2015, I have shown that how the circle of sustainability have started to grow. And the main reason for that the world leaders came up to meet, that started in 2014, while Obama was like the president in US. And then in 2015, there was a major kind of major area or major kind of move in this direction, where the UN Paris Agreement happened, where the sustainable energy development goals were put forward. And the main interest for that was to ensure access to affordable, reliable, sustainable, and modern energy. One part of that was a very, very relevant part. And following that, we have seen that every year, this sustainable energy days, sustainable energy week, sustainable energy practices, sustainable energy industry involvement have been growing in. And this is only I've shown for the year 2021. So you can see that so many areas, I mean, we have also like Asia Pacific goal, specific goal for Asia Pacific countries, where India is housed in. And there is a big kind of the sustainable energy move in Europe. US have been a little bit behind this, because when Trump was there, he didn't want to be a part of the sustainable development goals. So he revoked out of this US Paris Agreement, while Biden, when came in, he rejoined in this SDG goals. So all these energy, health, and all this research also is very much related to the goals that have been put forward in 2015. And we have also seen that how actually these research development, these industries are slowly following them. And now it is not slowly, they're really into like following all the agreement deals that have been finalized in 2015. So by 2030, the agenda is to have these sustainable goals. Out of that, SDG 7 actually is specially dedicated for affordable and clean energy. And the other goals, if you see here, it's good health and well-being, which is definitely connected to the, again, to affordable and clean energy, because that's, so in other ways, sustainable cities and communities. So other ways, like all of them are somehow interconnected. You cannot really think of improving one, omitting the other. So sustainable and clean energy is also something that is related to the sustainable cities or smart cities. That is what I will show in the end of my talk, how Indian government is also promoting this sustainable cities. And there are 7 or 8 cities which have been already put forward in India to have to be smart city in next 10 years. So all these energy sector and everything is very much related to the sustainable energy goals. That was the main thing that I wanted to show. So now coming back to the thing that I will talk about, it's about energy harvesting. So I'm stressing on the point harvesting here, because there are other ways of producing energy, which is called energy harnessing. But energy harvesting has a special meaning. If you see the 3 circles of energy, they are also interconnected. They make a triangle by themselves. And energy generation is one of them. And we normally, actually, when we are talking about renewable energy, we mostly talk about energy generation by solar, by hydro, by wind, or whatever sustainable way that we can think about, or it has been put forward. The second part is energy storage. These two actually I have on purpose actually I have deactivated it so that I can focus on this part. So the second is energy storage, where of course the research in batteries, supercapacitors, superconductors here that we have heard. So all these are related. So energy generation, energy storage, and then third part is energy harvesting. So this third part, energy harvesting, is mainly for waste energy recovery. It's not exactly energy generation. You really can't think about powering up a city or kind of a big amount of energy you cannot get out of this energy harvesting. So that's why it's also called energy scavenging. So basically to introduce whatever is getting wasted, and because we have light energy, which is the indoor light. We have heat energy, vibration, magnetic, IR energy everywhere around us, and there are several sources of it. And this is like a very good picture showing that how like the energy harvesting technology actually can come to your day-to-day life, like when you need it most, actually. Of course, the big energies are definitely no one saying that you don't need it, but these small scale energies for small power devices, for automation of small electronics, for health monitoring, for small surgeries, small device monitoring inside your body are very much necessary. So here it shows that how if you can put different nodes at different places of your body, and if a person has to monitor its whole body anatomy and like the body processes that is going through, maybe glucose monitoring, heart monitoring, everything, how can different energy harvesting sources can be used to make these sensors? And mainly, so the energy harvesting is used for making the sensors, for making, I would say that IoT devices, the wireless devices, which are the future of next generation electronics. And so in a word, why do we need energy harvesting? Because the need for endless energy supply to all the electronic system that is getting piled up, and that is like the predicted for next generation use. Already, for example, I can understand, for example, my 8 years old daughter actually is using a laptop, a tab, and a mobile. And I cannot think about that when I was like her age. So thinking about 10 years back also, we could not think about so much of advancement in electronics. So you can understand that, of course, we need batteries, and that's what powers up these devices. So we want to reduce the dependency on batteries so that those devices have to be self-powered. And this self-powered technology can come in greatly from different energy harvesting sources. But we still have this thing, very clustered use, because of some greater adoption barriers, which is mainly due to the stakeholders, the companies that are going to buy this idea. So we cannot really strive to application. We cannot go to the next stage of application unless the industries are interested in it, right? So, but the thing is, which is the good news, is recently for last 4 or 5 years, we have seen that a lot of industries have come up with these interest in this energy harvesting technology, mostly the big companies, not for the small companies, but the big companies like LG, like IBM, they have a big, like Google, even Facebook itself. So they have even MS Teams. They are actually interested in this energy harvesting technology a lot for different kind of devices, different kind of uses they are predicting to have. So we have integrated application for this energy harvesting, and mainly the information processing, which is for the Wi-Fi, for the Internet of Devices, Internet of Things, which are connected together through Wi-Fi and satellite technology. For all this automation of devices, we need energy harvesting. And if you can see the general energy harvesting setup architecture, this is not nothing new. All of you are in physics, you know that how a general energy harvesting setup can be made. So this is in the box. It shows the general energy harvesting setup. So basically it will capture the energy. The energy has to be environmental energy. That energy can be from the light, from the vibration, from thermal or infrared that I have shown. There are many other also, like magnetic energy and magnetoelectric energy. So it will capture the energy, then it will use a transducer to kind of convert the energy into electrical energy. And we need another step, which is called power conditioning, because in most of the energy harvesting setup, you get either DC, but that DC is not power conditioned, or you get AC that has to be converted into DC to store finally into some form of like energy, or of course electrical energy, to be used in the later stage. But we want to omit this part also, this energy storage, so that like the future energy harvesting setup also just ends with this power conditioning and then directly to the electronic load as it is using. So we have boundless supply, which is basically the self-sustainable sources, which is from the environmental energy. And it's readily available anywhere and everywhere. For example, I showed you this picture, which is like when the person is moving due to its body heat, we can use scavenge that heat energy to run maybe the pacemaker or the BP it is monitoring or something like that. The pacemaker, which is running probably in his body, it can be used due to the vibration of the heart. So this is something that is like the energy is available anywhere, and particularly useful for the human monitoring devices, as we monitor, because like we know that human machine is the best machine in the world, and that never stops. And we have boundless energy sources in our body. And overall, the energy harvesting architecture can be extended to different kind of areas, starting from the microwave radiation to artificial lighting, even biomechanical energy, and biochemical energy through the electrochemical reaction. Then going from the bio to the ocean wave energy, you can use the AC linear generators. So all sorts of different energies, whatever Earth has, or whatever human have, and whatever animal have probably, that can be used for any kind of energy production is called energy. And as I mentioned, that world needs energy, of course, we all know that, but it needs energy from large scale to small scale. Whenever we are thinking of energy, we are always thinking of nuclear energy, solar energy, wind energy. That's renewable energy, of course, and that's necessary for powering up like maybe a city here. And some of the cities in Europe have been using it very intelligently. And like Lisbon is one country in Portugal, it's going to be like the first country to be using this general energy harvesting as or renewable energy as its sole resource for energy. But it's a small city. But if you think about New York, if you think about even Delhi, Mumbai, you cannot really rely on just solar energy, right? You need petroleum energy for sure, but you have to kind of substitute it with some part of it with the solar energy. But that's for the bigger scale of energy. I'm talking about a terawatt, gigawatt level of energy. But going to the other side of the spectrum, we have microenergies, milliwatt energies, and you may think that there is no use of that. I mean, what is the use of a microwatt level of energy? But then there comes the small scale devices, small implantable devices, small chips. In our mobile, actually, the power requirement is decreasing day by day. And what we are using is tons of lithium-ion battery, which is getting wasted like anything, because after it's wasted, you can't really throw away. You have to recycle it, but not all part of it can be recycled. So basically, we are trying to use batteries, small-scale batteries, but then ending up with another problem. So the main thrust of this area in the microwatt, milliwatt is then for using these self-powered energy harvesting devices, which can, at some part, actually reduce these dependencies on batteries, and then we can call it as sustainable. And everything if I'm talking about applications, then definitely the market growth comes in, and we cannot think about anything without the profit. So thinking about that, 2011, 2009 onwards, actually this energy harvesting research started in a great momentum. I will tell you why. But then 2011, we can see that from 2009 to 2011, there have been quite a growth, and the most of this application is in consumer electronics. And of course, a great deal of application is in military and aerospace, which is mostly in US and China and in South Korea. I cannot say that in India, it has a great deal of application in military and aerospace. But then from 2012, so this was about like 0.01 billion, something like that, dollars. And from there, it started jumping. And from 2012, which was like 0.7 billion, and then 2017 to 1.5 billion, 2021, this pie chart was not available, but I got from the IDTex itself that the market valuation for energy harvesting is about 4.4 billion. So it is obvious that if a market grows in a such exponential way, it definitely has some impact. And that we can see clearly from the chart, which was released like in 2017, that how they foresee it's growing. And you can see this APAC is the Asia Pacific market, and it is definitely, and India includes in that, of course, and it is, they are all growing simultaneously. Only this is some kind of African countries where we don't see much growth, but America, Europe, Asia Pacific, also includes China. It's a big market of energy harvesting. So market growth definitely shows that you have interest in energy harvesting, and that's kind of an exponential. But now, if I'm thinking about microenergy research, microenergy resources, before research, let's think about microenergy application. So what are the sources of these microenergies? Of course, sun, if you think about solar, outdoor solar is something where we get about like milliwatt level of power, but we have several, we can use several panels of solar cell that we can stack them, and we can increase the power a lot from this outdoor solar cell. So that's why we have the solar parks, solar grids now in everywhere around the world. But there are small sources, like if you think about light, indoor solar, not I will say solar, indoor light, the LEDs that we use. And those can be also source of light energy. So, so what can we do like with that? So those can give like you microwatt level of power. But this microwatt power might be used for powering up another LED in your house, another kind of small device in your house. So basically you can scavenge that energy and use it for something else in your area. There are other sources also, as mentioned here. So piezoelectric, vibrational energy means piezoelectric also includes the vibrational energy. Thermoelectrics means thermal energy, then acoustic noise, radio frequency, the outdoor wind turbine. The outdoor wind turbine gives you some kind of energy, but the sound from the wind turbine can also give you energy. And scavenging the sound can also, from the radio frequency sound, can also give you another sort of energy scavenging. So, but before that, we didn't actually know about it. We didn't think about it. Now, actually, we are all connecting together different aspects, different kind of contributors of energy together. So if you see this graph, it's not exactly a graph, but it is just a projection or kind of a schematic to show that this is a battery run time from years to hours, and this nanowatt level of power is needed as vibration sensors. So as sensors for this IoT devices, you need this kind of nanowatt and microwatt level of power, and that's how this area is. And the stress strain, which is a mechanical source, thermal source, and radiant source are there, which can provide you a great deal of energy around this area. And operational range for all the IoT devices nowadays are mainly in this area, this region of power. So basically, micro energies you can find from these kind of sources, from mechanical source, thermal source, and radiant sources. And there are also key design consideration for making micro energy harvesters. That is an engineering part. But we need to know this, as we are like energy harvesting research I'm doing. I need to know each and every part of the research that I have to do, where we can get stuck actually. So first of all, we have to determine the energy available from our environment. That is what I do also, like determine the energy from available on in our environment where it can be present. And then you harvest the energy as efficiently and cost effectively as possible. So cost effective is very important here. So most of the research actually are very costly. and cost effectiveness that we are routing for, because nowadays with the crunch in government funding, we have to definitely think about cost effectiveness of everything. And of course, if you want to make it in application state, if you make it a very costly device, there is no application for it. So you have to reduce the cost of any kind of thing that you're doing. So cost effectiveness is something that has to be done while we are harvesting the energy. Then calculating the application power requirements in all operation modes for any kind of energy harvesting power. So basically, what are the areas that we are going to use, and depending on what are the areas we are going to use, we can choose different energy sources. For example, if we're going to use an energy harvester to power up like devices which best in a remote Antarctic area where the solar power is not there, you need thermoelectric power or vibrational power maybe. In that case, if you select a device, if you make a device which is running with the power of light, that might not be possible. So basically, choosing the areas of operation is very important when you're judging the energy harvesting power. And size storage, of course, because the amount of power that you need for running a tablet is not same as you are running a watch. So depending on that, your materials can be chosen and your device can be made according to your need, which also means that bigger battery cannot be always better. So definitely you have to be very effective, you have to be very efficient in choosing your energy sources, even if it's micro energy sources. So what are the common, I have already showed you different energy sources for micro energies, which includes the radio, mostly 4 here, which is in the application state or application area. One is the radio frequency energy, which can convert, it basically gives you the DC power, and it's available in different forms, like radio frequency energy in the cell phones, in radio towers, Wi-Fi towers, in your laptops. Each and everything has a radio frequency generator, and that can be scavenged through radio frequency energy harvester. Vibrational energy harvesting, but that gives you very low power. It's about like 0.1 microwatt per centimeter square. That is the density of the power. And vibrational energy, which is about like 1 milliwatt per centimeter square. This is the mostly usable form of energy here. I mean, nowadays as energy harvester, and already there have been a lot of use of that. The most efficient sources of vibrational energy are human motion, vibrations, pressure. So piezoelectric, triboelectric materials are the ones which can convert a vibrational energy into usable electrical form. This picture actually I've taken just in the morning. Actually, I was looking for a good picture where I can really show that where the real application has been done. So in London subways are very popular. In London subways, they have started this paving, putting in this piezoelectric and triboelectric mats, which when you're walking through it, because every day thousands or I can say lakhs of people are walking on through that, it can generate its own power. So basically the subway light, whatever needed, it's kind of a sensor. When a lot of people are walking, it can generate that electricity, it can run the light, or it can power up the light which is in the subway, and then it can turn off automatically when there is no motion there. And thermal energy has been used also pretty good way as energy harvesters, particularly in automobile industries, where I'll show that how exhaust, like when you're running your car, most of the energy is wasted as heat energy through the exhaust, and you can put your thermoelectric devices, thermoelectric modules in there. General Motors is greatly working on that for last 10 years to scavenge that thermal energy and using thermoelectric materials. But pyroelectrics are also something which can be used or scavenge thermal energy for thermal sensors. And photovoltaic or light energy, we all know, recently has been shown greatly that indoor lighting, maybe the light LED sources which we're using is 5 watt, 3 watts LED sources, can also be used pretty good source of light energy for energy scavenging. for generating small power devices applications for small power devices application. So I will definitely not cover all of it because it will take a long time for me. I actually already have spent a lot of time on this introduction. So what I will show you here is these two areas of energy harvesting here, vibrational and thermal precisely. Also in that I will not go into the triboelectric and pyroelectric because that will also take a lot of time, and I don't think I have that much of time. So thermoelectric and piezoelectric is also something that I'm doing in my lab. So my students are involved in that research. So for any energy harvesting source, one thing has to be taken into or kept into mind before we start is like how can we manage the micro power, because the micro power, I mean the power that is we can generate out of it is like pretty low. It's like micro, sometimes of nanowatt, depending on what kind of device or kind of material you are using. So you have to utilize each and every bit of it. You cannot get it wasted. I mean, we can recovering waste energy, but you cannot get it wasted. So thermoelectrics or PV cells, I just write thermoelectrics here. Thermoelectric generators actually is also something which gives variable DC output. Means like the source that we are having, the environmental source or thermal source, it's not consistent. So let's say if you have a thermoelectric device like on the surface of your I'll say that the window, and like here in Mumbai also, in Calcutta also, we have sometimes outside temperature can go pretty high, about like 40 degrees in the hot summer months, and inside definitely then you are running an AC, right? So the temperature there is about like 27, sometimes 25 degrees centigrade is a normal time. So there is quite a lot of temperature gradient between just 27 degrees and 40 degrees, and we can definitely utilize that. But then this 40 degrees, which is the outside temperature, is not also consistent. Sometimes it may go down to 34, sometimes at night it's 28. So basically it's a variable DC output voltage also we are getting. So we need also a power conditioning, a DC-DC converter with a variable conversion factor, and to control this we need controller to provide it to the battery to kind of store it for future use, if that is a future use that we need for. And in case of vibrational energy, it's the AC output voltage that we are getting. So we require first to rectify this AC voltage to a DC voltage. We need a converter, and then to store it in a different level. So micro power management is also very much necessary while we are doing energy harvesting research, and we need to kind of operate it at a maximum efficiency. So basically if you're thinking about that the temperature gradient, so the temperature gradient has to be maintained throughout your device so that you cannot have really a variable power there. And particularly for the vibrational energy harvester, we have to kind of use a resonating frequency. So it gives the maximum power with the resonating frequency of its own device. So we need to kind of maintain a resonating frequency. We have to choose areas where these frequencies are mostly like picking or resonating along with your device. So those things are always to be kept in mind, but that resonating frequency can also change depending on the time frame, like at what time you are using that device and where in a daytime. So that is a very important, and that is an engineering aspect actually mostly. I will not go to the detail of that. Materials engineers actually take care of that, and civil engineers take care of that part, where it is more in a construction area or something like that. So basically to go into the thermal micro energy, as you have already known probably, definitely all the students are now learning a lot of this current research. And this heat source can be anywhere in our environment. If you think like whether we get the electricity from the thermal power plants, a lot of energy is used like wasted as like the heat energy, and you can see that only a part of that is converted into electrical energy. And also in vehicles, I give you the example of the exhaust. Nuclear power plant is also a source of big energy, and then factories and our own buildings, because all the ACs are running, and you can, if you're standing outside the AC machine, you can definitely feel that how the hot air is coming out. So all these are wasted energy. So basically our energies are getting wasted everywhere as thermal heat or thermal like energy. So those are the areas actually we need to look for. And already companies in US, in Europe have been greatly working on that. Particularly also to kind of scavenge your body heat. If you are a person who is staying in a cold region, of course, there is also quite a lot of difference between your body heat and the outside temperature. Then wearable devices, thermal devices can be used for monitoring many of the medical needs that we have recently. So it's everywhere. Ideally, thermal energies are everywhere. But to scavenge the thermal energy, we need a special material called what we name as a thermoelectric. So basically, a thermoelectric material can be is a semiconductor, a low band gap semiconductor, if it's an inorganic material. But if it's an organic material, then its HOMO-LUMO gap should be very low. Ideally, what should happen that thermal energy means like you have a temperature gradient, and then if you are exposing your material through a temperature gradient, one side should be hot and the side should be cold. So the if it's a major carrier is electrons, we can think it as like a gas of charged particles. So if it's made up of electrons, it's free carriers, then from the hot end to the cold end, the electrons will move. So to the cold end, we have a density of electrons, which will be negative side. And if you have a hole carrier as a carrier, then this cold side, then it will be a positive side. So ideally, if you have a hole carrier, it's a P-type material, of course, and it's an N-type material. So for thermoelectric material can be both P-type and N-type. So if you have a temperature gradient across, then the voltage difference should be generated between the two parts of the or two ends of the material when you are exposing it to a thermal gradient. And that's what a thermoelectric material is. And not every semiconductor definitely can have that kind of property. It's a special kind of material, we can say. And what is a special kind of material, I will tell you much more later on. So let's just start with the thermoelectric and the other heating effects that it has. So what are the heating effects can we expect from here? We all know about Seebeck effect. Is not a very new science. Of course, it dates back to 1800s, where the Seebeck first discovered the Seebeck effect, which is a generation of voltage across the material as a result of this temperature gradient. And that is principally that effect is used in the thermoelectric generators. On the other hand, Peltier effect is the reverse of the Seebeck effect. But it's not exactly reverse, where you can generate a temperature difference as a result of an applied voltage, or you can also apply a current. And this is mainly used for refrigeration for cooling purpose. And other than this Seebeck and Peltier effect, there are other heating effects also present in any material at any time. Thomson effect and ohmic, this Joule heating due to ohmic heating and resistive heating is present there. And these two are always present whenever we are calculating the thermal effects or temperature gradient across a material. So we have to be very clear or very cautious that what exactly we're measuring. Are we measuring the Seebeck effect or Peltier effect, or we are measuring a blend of all these heating effects that is present in the material? But if it's a good conductor, of course, you can understand it should have a Joule heating. So definitely that is something, also a barrier against this devices when you are making it, that I will show you. So I will not go too much in the detail of it, but mathematically a Seebeck effect can be shown as a voltage difference versus its temperature difference, the temperature gradient that we have. And while metals have a Seebeck coefficient of a few tens of millivolts per Kelvin, semiconductors sometimes have larger magnitude. And Seebeck, that is why it can be used for voltage generator as like a voltage generator in this thermoelectric material. And in the Peltier effect also similar function can be written in there, you all know that. And the Thomson effect is also related to the Thomson coefficient, but they are not actually independent. They're all related together by the common Kelvin relationship. And so for a single material, for a single thermoelectric material, a Peltier coefficient is equivalent to or is almost equal to the Seebeck coefficient multiplied by its temperature. And if you using a thermocouple, then of course then the factors of like Peltier coefficient for both of the materials come in. So Peltier effect can be then expressed as the like the function of both those two materials in the thermocouple and the current flowing through it, and its Seebeck effect exactly. So basically, the point of showing this is that like a material or like a thermocouple, if you're using it, if it can be used for thermoelectric power generation, then it can, on the other hand, due to the Peltier effect present in there, it can be also suitable for thermoelectric generation, refrigeration. But what material can be used exactly for which purpose is basically depends on at what temperature you want to use that material and what is the exactly the power requirement that is needed from that material itself. So from that concept, we have thermoelectric generators. So ideally, a thermoelectric generators, if it's a solid inorganic thermoelectric generator, then we have two ceramic plates, and then we have this N and P type material because we need an electron flow. Of course, we need both N and P type material all connected together electrically in series and thermally in parallel. Then the current will flow from the N-type material to the P-type material and through load resistance, whatever load resistance we are connecting outside. So this ideally an equivalent circuit, if you see a voltage source, thermoelectric module, thermoelectric generator can be seen as a voltage source. And the internal resistance here comes from the contact junctions and the leads that is connected in that, and of course they are electrically in series, so there are also some kind of internal resistance from the series resistance that is there. And but the output current will go to the load resistance, the external load that will run through the power through the power that is generated through this voltage source. So thermoelectric generators as a whole is very much usable in many different areas, and the applications can range from household to space. So basically we can have thermoelectric watch where you can fix it with a thermoelectric module which can sense or which can use the body temperature difference to run the watch, because we know we don't need much energy to run a watch, right? So also the thermoelectric coolers, small coolers are available in the market. It's expensive, but I'm sure that in next 10-20 years, the way the research is going, it will not be expensive anymore. And the most usable area for thermoelectric is in automobiles, as I have already mentioned that there is a lot of heat wasted from the exhaust itself. So cooling car seats by thermoelectric devices is important, where the Peltier effect has been used, and the energy that is being extracted here can power up the devices within the car itself, the small scale electronics inside the car. So General Motors is one company, and also many other Tesla, we know that it's completely run by thermoelectric modules. So these are some of the main areas here. And the thermoelectric generators, radioisotope thermoelectric generators, has been long used in Cassini probe. I mean, that is due to the radioisotopes that is present there. So the heat difference, so there is a thermoelectric module at the pole end. So there, and the radioisotope always generates the heat due to the breakdown, due to the nuclear reaction there. So that runs the Cassini probe because it is basically running pretty far from the sun, and that is where you cannot really use solar power. So thermoelectric generators have been widely used in Cassini spacecraft, and it's been running for a long time now. So basically, it is the same thing that I have shown here. It's a thermoelectric battery we can think about thermoelectric as a thermoelectric battery source. So if you think about the Seebeck voltage, if it's a battery, if it's a power generation, it is going to do. So and we have N and P type material. So voltage, Seebeck voltage is a function of this Seebeck coefficient and multiplied by its temperature gradient that is being maintained across the P and N junction. Then the current we can definitely write as from the Ohmic law. We can write as like this Seebeck coefficient multiplied by this temperature gradient, and this R will be the load resistance and the internal resistance together. And from this, using this and this equation, we can then derive the voltage itself, and the power delivered will be VI. So basically it will be a multiplication of this I and V, where this S is here, it's a kind of ratio between the load resistance and the internal resistance. So that is the where we need the, if you have, or we need the maximum power output in from a thermoelectric module, a thermoelectric battery is sometimes is mentioned as. Then we have to have the load resistance and the internal resistance of the same order, or at least equal or of the same order in that process, in that range. Thermal energy conversion efficiency for this thermoelectric module is actually pretty low. If you think about Carnot efficiency is the energy output divided by the energy input. Here energy output will be the power delivered to the load, which I had showed in the earlier slide, and the input will be the heat flux absorbed at the hot junction. So, and the heat flux actually is dependent on the Joule heat, the Peltier heat, and the heat conduction in the material also, because we are thinking about like it's a conductor, so it will also conduct heat through the phonons itself. So that's the reason why we need low thermal conductivity in the material. If it has a high thermal conductivity, there will be substantial amount of heat conduction in the material as well. So from that we can derive actually the Carnot efficiency for a thermoelectric material, which is related to a factor called ZT, and ZT is kind of power factor or efficiency unit for any thermoelectric material. And as this graph shows, that it is not exactly possible to go to like a ZT of infinite quantity, right? And even if you go to 40% Carnot efficiency is like probably the maximum Carnot efficiency that you can get. And ZT, so before when the thermoelectric research started, improving on the ZT value was kind of a passion, because everyone was trying to kind of make more and more ZT value material which can be used for thermoelectric applications. But then they saw that it's actually not possible to go beyond a certain value, because it's against the principle of physics. So definitely we cannot really, even if you try hard, your material will not behave that way. So definitely we have a limit here how efficient we can make a thermoelectric device. And as I said, ZT is a figure of merit, which is dependent on the Seebeck coefficient. Square of the Seebeck coefficient is the electrical conductivity of a material, and the factor of the heat conduction, which is also a contribution from the lattice thermal conductivity and the electronic thermal conductivity. So we can actually, we cannot really take care of the electronic thermal conductivity because the property of the material, but we can definitely take care of the lattice thermal conductivity, because by changing the size of the material, by making it in different form, film, bulk, we can change the lattice thermal conductivity a lot. So as this factor shows that if you go from insulator, which has a very low charge carrier concentration, to metallic side, the Seebeck coefficient will decrease definitely towards the metals, because it's more in the higher insulator side. On the other hand, the insulators don't have much of the electrical conductivity. It is most for the metals. So we have like a place here for finding good thermoelectric materials, and people are trying hard to kind of focus around these low band gap semiconductor areas to find the next generation of thermoelectric materials and can be useful, that can have like, that can show an efficient ZT value. And for the thermal conductivity itself is the same thing. For the electronic thermal conductivity is almost same for all these materials, particularly for the metals. Actually, it's very high because of the electronic number of electrons it has there. Lattice thermal conductivity is something that we can play with, not the electrical thermal conductivity, but still semiconductor region, low bandgap semiconductor region is where we should shoot for any thermoelectric material to see. The latest thermoelectric research, this is not called exactly latest, this is in 2019, and even before that 2009 people have started thermoelectric research. So several thermoelectric materials, particularly the inorganic thermoelectric materials, have been shown to operate to kind of, it can operate at different temperatures. And depending on the use, I mean, at what temperature you are going to use your material, you can choose different material. You can take out, choose N and P type, particular N and P type thermoelectric material. You can pair them up and you can make a thermoelectric module. So that research is something has a great deal of limitations also, because up to a certain point it's the playing of the elements that is in there. So it is not going to a bigger direction. Then research started in improving the thermal this property, this ZT value, by going into the nano dimension, where you can play with this phonon scattering, because the phonons are going to come and will kind of get reflected from the, or scattered from the grain surface, nano grain surface. And if you can reduce phonon scattering, you can reduce the lattice thermal conductivity, thereby you can increase the ZT. And also by doing energy filtering, because if the high energy carriers can pass through your grains and the low energy carriers will be stuck, so there is an inherent development of or increase in the voltage throughout the material. So through going through the nano dimensions also, you can kind of try to enhance the ZT. That was in the time of 2000s, and I will say 2002, 2010 or 11 or 2015. Then started a particular different direction of research, is that we can see that we cannot really go to a different at a higher ZT even if we are trying hard. There's so much limitations with the material. But whatever we have, can we do it in some way? Can we use it in different ways so that we can use it in different areas? We don't need to kind of have a power generation, but can we use it somehow that we can use it everywhere? So then started the areas of flexible and shape conformable thermoelectric modules. So it started with the inorganic materials itself, mixing with and making them like small like structures, so that they can be scaled, like flexibility can be enhanced due to that. And this is a very good example of how these inorganic materials can be used as paints, so that you can use it on different kind of like surfaces, not only as a thermoelectric module I have shown you, which is a rigid structure. So that was the year 2016. But then another area started to explore in, which is in the conducting polymer thermoelectric modules. And conducting polymer thermoelectric modules so far have been the greatest push in this thermoelectric research, where now the polymer chemists came into this region. Before it was a physicist, then the material chemists, solid state material scientists. Now the polymer chemists came in this research, where they started looking into different conducting polymers, which may be also having thermal properties. But the good part of this is polymer thermoelectrics, polymer materials have already low thermal conductivity, and the cost is very low. So even if you are making an inefficient thermoelectric module, let's say its power factor doesn't go beyond like 0.4 or even like 0.2 ZT, still it's usable because it's so low cost, and you can actually use it everywhere. You can, here as it shows that you can actually wrap it on every surface. You can make it a roll and use it as a paste. You can just put it everywhere on the road. And you can use that as like a cup warmer or something. So many different exposures have been started when the conducting polymer thermoelectric module research started. And in this direction, in my lab, thermoelectric research is going on, where Bhargav and Shurojit is working on this, both inorganic and polymer thermoelectric materials. So Bhargav has been he's a physics background student. He has set up like a Seebeck measurement system using the differential method, where we can measure it using like a very cheap parts, I can say. So it is very usable to kind of measure films, materials on any substrate. It doesn't have to be like a rigid substrate, so we can measure it on like a flexible substrate also. And so he first calibrated it, and the calibration actually was pretty good with the standard values that are available in the market. And recently we started looking into P.PSS and its composite, which is a very standard thermoelectric polymer, P-type polymer, and then mixing it with graphene, it showed that how it enhanced the property. The manuscript is in preparation now. It has enhanced the property with the graphene and P.PSS composite. And we are also searching. So one thing is that P-type polymer, P-type organic compounds for thermoelectric materials are pretty much well studied. But people don't really report N-type organic thermoelectric material because of its stability. Because when it's electron rich, it can actually react with the outside environment, and it is very unstable. So recently what we started is like one of our professors, faculty is my colleague. He is an expert in the supramolecules. It's not exactly polymer. So he gave me some molecules to study, which he believed can have N-type conductivity, and we were really happy to see that it has got some N-type conductivity, but it is not very high. So at this point, I cannot say that it's a promising thermoelectric material, but we are trying to enhance the conductivity, electrical conductivity of this material. The Seebeck coefficient of this material is pretty high, is about like 237 microvolt per Kelvin, and it varies with the different kind of, because it's an organic supramolecule. So the way that it kind of does the pi bonding in different kind of a solvent is different. So it can vary with different solvents that we are using, but then as its conductivity is low, we are trying to enhance the conductivity by introducing some inorganic thermoelectric material in that, like graphene, as well as on carbon nanotubes, as well as we are trying to have a polymer composite, like copolymer kind of composite, so that we can enhance the conductivity of the system. In that way, we'll have like a stable P-type and N-type legs, as we say, for the thermoelectric material. Thereby we can easily kind of paint or print like a circuit of thermoelectric module using these two materials. And the future use of the flexible thermoelectric technology is mainly in the wearable sensors. And flexible thermoelectric films are everywhere. We can use as sensors, wearable electronics, to scavenge body heat. That's a main interest for the future health technology also. Of course, there are other areas that I have shown, but this is somewhere where there is a great potential of using this polymer biodegradable material as sensors and wearable electronics. So that brings me, I've taken a lot of time here, but I would like to kind of go to the next part of my talk. So how much time do I have actually?
You have half an hour. That is 30 minutes.
Yeah, with 30 minutes, I'll definitely finish.
Yeah, 20 minutes or 15.
Okay, fine.
15 to 20 minutes you can. 10 minutes would be for interaction.
Sure. Thank you very much. And second part of that I want to say, actually I took a lot of time for the thermoelectric research. When I start talking, I want to talk more and more. That's my problem. And when in the second part of the thing that energy harvesting research that or I want to show here is like mechanical. So mechanical has different contributions from, one is like electrostatic, electromagnetic, magnetic. There is triboelectric, which is an interesting area which I wanted to show, but there's time limitation. So I will just focus on the piezoelectric material, how these piezoelectric materials can be used for mechanical and vibrational micro energy harvesting. So the energy conversion pathway for this piezoelectric or the vibrational energy harvesting is again the same way. We scavenge we have an environmental excitation energy, which is a vibrational energy in that case, or mechanical energy. Then you go from there you have like the electrical energy generated through the transduction, and here the transduction is through the triboelectric or the piezoelectric material or the ferroelectric material, or even the dielectric materials can be there. So that part is depending on what are the use of, on how much electricity you want to generate out of that particular device, and then the electrical energy output through the power conditioning. But on each and every step also there is some losses through this energy conversion pathway. So there is electrical loss when you are converting into electricity and then power conditioning it, then there is electrical loss when you are trying to store it, there is electrical loss, and here when you are trying to convert it from mechanical energy to the electrical energy, you have mechanical to electrical.
You're not audible right now. Hello, that's frozen, it seems.
Yeah, okay.
Just now I can hear. Now we can hear.
Okay, sorry.
Now you're
okay, sorry about that. There might be internet problem, but I could hear you actually.
Okay.
Okay. Anyways, so yeah, sorry. Can you hear me now?
Yes.
Yes, thanks. So going ahead, so this piezoelectric or the vibrational energy harvesters can be used in many usable ways. Like one is can be like piezo sidewalk, which is normally used in many places in South Korea also. The concept of piezo tree is where you have that wind energy that can kind of vibrate the this kind of piezoelectric or piezoelectric materials or any kind of vibrational materials, and that can generate the electricity. There is bountiful of kind of usable area in at the boundary of the ocean, and where you can have this kind of piezoelectric sensors, cantilever kind of a sensors and harvesters sunken, and that can generate the electricity and that can power up. There can be thousands can be lined up like that, and that can have like a coastal power through this kind of piezoelectric thing. And recently in UK it has been approved and has been used. There a long time this piezoelectric shoe has been used by the athletes, and of course Bolt is someone which have recently taken out this power cells out of this piezoelectric MEMS generator. But there are others also like piezoelectric nano generators. I will talk about nano generators later on, which is the recent market that is coming up. And one major usable area for this energy harvesters, particularly vibration energy harvesters, are in medical field, where implantable devices due to these vibration energies can be harvested and can be used in many biomedical applications. But main material that can be used for vibration and energy harvesting is a piezoelectric material, and the piezoelectricity, as you are from physics, I'm not going through the detail of this. There can be two effects. One is piezoelectric effect, another one is converse piezoelectric effect. Piezoelectric effect is where you're putting a pressure through your material and you can generate the electricity. And on the other hand, the converse piezoelectric effect is like when you are having like a voltage difference, and you can actually cause the deformation of your crystal lattices when electric charges are being displaced. So broadly, piezoelectric crystals are a class of dielectric materials, which is a 32 class of materials, 32 crystal classes. And piezoelectric crystals, we can see there are 20 type of crystals of piezoelectric materials. So if you are searching for piezoelectric crystals, definitely you are bound to look into these 20 type of crystal structures. And out of these 20 type of crystal structures, 10 are ferroelectric, very precisely, and these ferroelectric materials are mainly used for memory devices, but they are also very good piezoelectrics. Another 10 crystals are for pyroelectricity. So for the piezoelectric materials, if you're searching, definitely this 20 type of crystals we will be looking. Of course, since they are dielectric materials, so mostly all piezoelectric materials are insulators, unlike the thermoelectric materials, which are low band depth semiconductors and conductors. So piezoelectric materials, the piezoelectricity definitely comes from the absence of the center of symmetry. So if you have a symmetrical crystal, if you have a body-centered cubic structure like NaCl, that will not be piezoelectric. So we normally look for non-centrosymmetric unit cells, unit crystals. It can be perovskite, but has to be non-centrosymmetric crystal structure, where due to the pressure difference or due to the stress, you can actually displace the dipoles inside your material. So you can generate the dipoles, you can change the center of symmetry, you can generate a dipole. So you can press it or you can stretch it, whatever way we can put the this stress in the material. So basically, if you have a random dipole moments, if you're pressing it, it will align and it will give you a positive voltage. If you're releasing it, it will give you a negative voltage. So the signal will come out as like an AC output upon pressing and releasing. That's what we look for into the piezoelectric energy harvesters. And all because like piezoelectric materials actually follow is a third type of tensor, and it's like a strain in the system is there, and we always have like this D3-3 polarization generated in the 3 direction that gives you the perfect stress applied in the vertical direction. But if you're pressing a material, depending on like we cannot really see which direction we are pressing in experiment, right? So in that case, we can have other components also where the polarization can exist, mainly into the D33, D31 and D15 polarization, but D15 is for the shear stress when you have in a material. So that's how the piezoelectric materials, when we choose, we normally go through these parameters to find out the best piezoelectric material to start with for the experiment. And if it's a ferroelectric material, as I showed, it belongs to 10 crystal classes, then of course its piezoelectricity should be pretty high. Then upon polling means you can apply a voltage up to a certain temperature, which is the Curie temperature, after which it becomes paraelectric. So up to the point it is ferroelectric, you can put like a DC field. You can apply a DC field, you can pole the material, and then when you release the poling, release the field, then you can have a remnant polarization left, but still there are some orientation in that. So that's where the piezoelectricity also comes from the ferroelectric material as well. So this is how the piezoelectric and ferroelectric materials can be used for that. And if I come to the device part now, the piezoelectric transducer can be of 2 different types. One is like cantilevered harvester, where mainly it is stuck to the base of like in the a kind of a stuck base, and then actually we have also a proof of mass, so we can actually squeeze the material from top or in a longitudinal direction as well. Then mainly we measure the D33 mode as the when we are using it a harvester model, in the harvester model. But that is how normally in commercial actually piezo transducers are used, where they use it as like a cantilevered harvester. But in other cases, many other cases, we can have, other than the cantilever, we can also have stacks. Here we can see that it's fixed to the base, then you have dynamic excitation, which is in a certain direction, and the direction can be chosen which direction you are actually vibrating it or you are putting pressure. And it can also be dynamic excitation. So basically we are always putting pressure in that, at the same time is generating voltage, you are using that voltage, so it's basically used as a sensor. So cantilevers mode or stacking mode can be used for piezoelectric energy harvesters, and it's a simple way that if one piezoelectric energy harvester can give you microwatt level of power, if you have a stacking of several piezoelectric transducer or energy harvester energy harvester, then you can actually linearly increase the power from that particular device. And that is for the inorganic material. Now next generation of piezoelectric energy harvesting have also gone to this organic based piezoelectrics, and the main interest in this that you can have a flexibility in that, and the polymers are robust, they're cheap, they are biocompatible in many cases, and many standard piezoelectric or state-of-the-art piezoelectric energy harvester, which is also like a ferroelectric polymer, is kind of PVDF, and you can have a copolymer of that, or you can extend the structure of that in many different other ways. Also nylons. recently, we have shown that like nylons, this odd number of nylons have also this unequal chains here we can see, and that's where the dipole moments come in. And since it's nylons, it has a very big application in variables, and that's it's more promising here. And piezoelectric energy harvesters, nano generators have been started to be in radar since 2006 by Zedel Wang, who is the main contributor in this nano generator field, mainly piezoelectric nano generator, have started to show that how inorganic, he started using zinc oxide nanowire arrays to show that how it can generate electricity. And this kind of nanowire arrays can be used for many kind of variable things. And from there, barium titanate have been shown, lead zirconium titanate have been shown, but recently lead zirconium titanate have not been very popular because of the presence of lead. So in 2017, we have also shown that nylon nanowire arrays can give you considerable amount of open circuit voltage and short circuit current when you vibrate it at different frequencies, and depending on the frequency, you can enhance the amplitude of this current and voltage. And this way, the research direction in ISIS in my group, where the Shubhankar and Swadesh actually are involved in, we have set up like a vibrational energy harvester, where we can prepare like a sample, a material, any material which we think actually is usable. Mainly we are, since Shubhankar is a chemist actually, so he's working on making different inorganic non-centrosymmetric material which have not been explored for energy harvesting, and also like a new ferroelectric material. So we started seeing their piezoelectric energy harvesting properties as well. So we calibrated the system. We saw that it is very much in the range of what is commercially available. And in my group, actually, I tried my students, particularly the physics-based students, they have to set up a system of their own, a small system, but still they have to, so that we can use it for different energy harvesting research. So this is how actually Swadesh was doing. Actually, if you're tapping on like material, this is made up of zinc stannate in PDMS. That how can you, by tapping, you can get a considerable amount of voltage out of that. But this is just like initial thing that we have shown. So with that, that brings me to the end of my talk here. So the future of micro energy harvesting through the piezoelectric material actually is just doesn't stop with piezoelectric. So then the piezoelectric material can be extended with piezophotonics, optoelectronics if you include in that. Then piezomechanics, if we are including piezoelectricity and mechanics, biomechanics in that. So this realm of its research, realm of its application can be enhanced more and more. And that brings me to the same picture that I have shown before, that mainly the interest for the future energy harvesting is to use it for medical needs, for your day-to-day life, and for IoT devices. So where the applications or requirement of energy is pretty low, you don't really need very high amount of energy. And keeping in this space, India also have, Indian government have also started looking into the micro energy harvesting to attain the SDG goals that I have shown in the very first slides. And the mission is to taking stock of this Indian smart city mission. Tata, Reliance, and Indian Oil, actually they have started looking at the energy harvesters, actually this small scale energy harvesters, and the outside stakeholders like Siemens, ABB, they're pretty much into it. And Ministry of Urban Affairs have started looking for fundings where they can look into the energy harvesters from different sources, scavenged energy sources. And with these, I would like to end my talk here. So the load bearers for my lab particularly are the students, and I cannot thank them enough for the hard work they have given to kind of run the lab. I have got really small time because of the repeated lockdown, but I'm really thankful to them, all my students, to have like an energetic a kind of healthy attitude towards the research that we are doing. And of course, it cannot end without funding from DST SERB for my Ramanujan Fellowship, where it gave considerable amount of starting fund, starting research. and the SARPO research grant that I've been granted recently. My collaborators, Professor Shurit Ghosh, who is an expert in supramolecular chemistry. He is a big name in the shot in this area. Ranita actually is also looking into the thermoelectric materials. She is in BARC, and Shohini is in the University of Cambridge, where we routinely do collaboration on various measurement systems, particularly the PFM that we are doing. And definitely the facilities that I have been getting from the central instrument facilities in ISIS and my departmental facilities and the facilities created with the Ramanujan grant. So thank you very much. Thank you for bearing with me for such a long time. I don't, so over to you, Vishal.
So the floor is open for the questions. If the students have any questions, please post it or am I audible?
Yeah,
yes,
I can hear you.
Okay. The question: Can incineration?
Actually, your voice is too much echoing. I cannot really understand. Sorry. Hello, can you hear me?
Just one second.
Can you hear me?
Yeah, I can hear you. Hello, can you hear me?
Yes.
Yeah. Thanks.
So the question is, video. On. Okay. Can incineration produce enough energy?
What? Sorry.
Can incineration? I think it's burning. Is it?
Yeah, burning. Yes.
Incineration. Incineration produce enough energy.
Burning of what? I'm sorry, I could not understand.
Maybe waste product or
incineration is waste product. Yeah.
Okay.
Means like, burning of burning of
waste
something like that, or waste.
Yeah, burning of waste products or all those things.
Incinerator we have not. By waste.
Okay. Of course, yeah. I mean, when you are burning something, you are generating heat. So with the thermoelectric model, if it's not in open atmosphere, of course you can scavenge that. If it's in a bio waste like incubator, it's a routine practice that you can have a thermoelectric module actually at the exhaust that you can use to scavenge that heat, and that you can store in a battery, small scale battery, and that you can use it later on. So wherever there is thermal gradient, of course you can use it. It has to be a considerable thermal gradient, minimum 4 to 6 degrees centigrade.
So the maximum efficiency that you can have is of the Carnot engine, is it?
Yes, it runs as a Carnot engine, of course.
There is another question. What are the difficulty in implementing piezoelectric energy in India? Okay, what are the difficulties in implementing piezoelectric sources of energy in India?
Stakeholders means like the revenues that can be generated out of that, of course. If you have greater energy resource, I mean sources, of course the renewables, and in India we know that solar, it is very much into the focus in the solar. So right now India have started looking into the energy harvesting through piezoelectric material, but you cannot really have that much amount of energy from a piezoelectric material. So definitely the companies have to come forward sorry.
I'm sorry. Please, we have even tried in our college piezoelectric. We get piezo cells from the market.
Okay.
1 rupee, 1.5 rupees, and we try to generate electricity. But then what we get is very, very less. The voltage is just
yes, but you can stack them. Actually, that's what we do. Because if you, let's say, like if you have to show that it's running on LED, of course, like a small transducer, you can get like a transducer available in the market, like PZT transducer normally. They are based on lead zirconium titanate, and that's we have tested our system with. But you can, if you want to have a considerable amount of power generated from the transducer, you have to stack them together. And that's what I mentioned initially, that actually it's not large scale of energy that we're looking for. We are looking into the nanowatt level of energy. So it means like what you are trying to run through that energy makes a whole lot of difference actually. Is the biomedical, that's why the flexible electronics and biomedics are there, the potential stakeholders, potential buyers for this market. And that's in India, unfortunately, have not gone to that point yet. But if you go to South Korea, if you go to Japan, and of course in many other European countries, they are very much focused on this kind of energy harvesting research also, and the market is growing. But there has been initiative. India just started in 2020 actually these things. So the goal is to 2030. So hopefully there will be some kind of area coming up in by 2030.
Along with piezoelectric cell, there is another branch. What is another thing you said? No, along with piezo cells, piezoelectric.
Tribo. Tribo actually, on the other hand, is much more efficient than piezoelectric because it happens to be that you are using the static charges, surface charges from the material. The piezoelectric, the charges are from the inherent material. Yeah, when we are measuring the piezoelectric charges, or basically in the tribo we measure the charge, but in the piezoelectric we measure the voltage. So when we are trying to measure the piezo voltage, we get rid of the triboelectric charges. Otherwise, the noise comes out to be, it comes out to be around like hundreds of volts. Okay. That's something. But actually, tribo is a very good source of making this kind of small scale of energies. But you have to store it somehow. That is the thing.
And what about those tidal energy plants that are coming up?
That was in UK board, and through the coastal lines. What you were saying?
Yes.
Yeah. So they had put, this is a kind of a cantilever kind of attachment. They are like flapping. So the surface, they put it like in a place where the surf is very high. So the wave energy is actually hitting your flaps all the time. So that creates a vibration, and they put a line of these things along the coast, which is a huge kilometer areas, hundreds of kilometers. So that can generate the power required for the lighthouse and so on. And for navigation as well.
Any more questions here?
I'll ask maybe. Please. Just one more question. Regarding the piezoelectric cells that you said, what is the aging effect of that? Matlab, do they last long or frequently we have to replace them?
Okay, so that depends on the material itself. Because along with the piezo, because it's a vibration energy, so it's a mechanical robustness of the material is definitely a factor here. Okay, so if it depends on the robustness of the materials, if it's a polymer material, of course, I'm not thinking of using it somewhere where it is constantly going through some vibrational force, because that can wear off the polymer layer very easily. So when you are using it for outdoor use, so you have to choose like a ceramic piezoelectric material, not a polymer one. But for the biomedical devices, for the biocompatible polymers are needed, not the inorganic ones. So that's where this thing can. So depending on what kind of material use, its robustness, that is one factor. That is called that is a part of the materials engineering actually. They check the robustness of this material through the PFM, through the AFM, sorry, and the QNM. I'm sorry, is it okay? I mean, did you get the answer of your question?
Yes.
Okay. But itself, the commercial one, the PZT and so on, the lead zirconium titanate and any kind of perovskite oxides, actually, they're pretty hard because they're oxide materials, and they're quite good in enduring stress. This was for the students. I don't know if the students got any message out of it. But ISIS, actually, the SIES department is, I mean, the School of SIES is pretty new, but it includes, it inducts students from different backgrounds. So if they want, they can definitely check out the academic program there for the PhD and masters. I can't hear you.
Okay. Yeah. Are there any more questions there from the students? You can post it, or you can unmute yourself and say it out loud.
This is Saturday evening. If I was a student, I would not be there. Sorry. And yeah, it's a whole day long. So I can understand.
They were eagerly waiting. Yeah. No, I just. So I guess.
Yeah. For who is giving? Aisha?
Huh? No, Famida.
Famida.
So shall I ask Famida to give a vote of thanks?
I don't need a vote of thanks. Thank you.
It is our.
No, thank you. That's a very big formality. It's okay.
Such an awesome session on harvesting microenergies, paving science, and technology of sustainable future. I would like to thank you for introducing us to an interesting concept for all our participants present today. The session was indeed insightful. I must say a big thanks to the Department of Physics, faculty members, our respected teachers, and all the speakers for providing us an opportunity to be a part of this amazing webinar. I would like to thank each and everyone present here for sparing their valuable time and making this webinar a great success.
Ma'am, when you come to Bombay, you come to SIES.
Sure. Sure. Well, the corona has to subside.
Yeah. Yes.
There is no device that I can take and go there as of now.
Yes.
Yeah, definitely. Thank you, sir. Thank you for extending.
Now I call upon Professor Kiran Nabar to give vote of thanks. Entire session program.
Actually, there is the voice. Mute कर. Mute किया. नहीं, voice. Mic. Speaker also. Okay. Okay. So, good afternoon, everyone. Good evening, almost. So, it's a very nice. I'm Kiran Nabar from Physics Department, and on behalf of SIES College and our Physics Department, pressing vote of thanks. It's a very nice day for us in SIES history and also in our Physics Department history. On one day, 4 eminent speakers we could invite, and they readily agreed, and then we had a nice day interaction with the students, and students community is also very happy, and they were all very eagerly waiting for this day. Before I formally place vote of thanks, just one thing I would like to mention, that this webinar we are conducting in the memory of our beloved teacher, late Pratibha P. And since morning we have mentioned so many things about her, and that is endless actually. One can speak on speaking, but one thing is very special about her is this kind of activities, especially. She used to be very enthusiastic to conduct this kind of activities, and every year we used to have workshops, seminars. Once the students complete their exams and become free, we used to utilize that time to conducting lab sessions, workshops, lectures, and she used to take always lead in that. So I must mention that. And one more thing I must mention is nowadays people say that physics is something like students are not interested because they get dragged towards professional courses like engineering, medicine, etc., computer. But here I would like to mention on behalf of our department that in 2019, we had enrollment of 25 students in physics TY-BSc. In 2020, it was 35 students. And in 2021, it is almost touching 50 students. So we are very successful in attracting students towards the physics subject, and of course the credit goes to mainly to our all senior teachers, and Pratibha P is one of them who has inculcated what you can say is good practices, healthy practices in the department, and I think that is why we are able to attract a good number of students in physics. So finally, I would like to thank first SIES management. They always back us, support us in all these kind of activities. So we must thank SIES management for allowing us to hold this seminar. We thank our beloved principal, because she always encourages us and provides all kind of help whenever we go to approach her. So we thank Principal Madam, and we must thank all our speakers, Dr. Sujit Manna, Dr. Pratap Rai Chaudhary, Dr. Tanmay Das, and Dr. Anuja Datta. In spite of their busy schedule, they readily agreed, and they had nice sessions for us, our students, and therefore we must thank them, and we look forward for same similar cooperation in future too. We can have many more such activities in future. I must thank Dr. Vishal Dev, the convener, and his team for taking efforts to make this program a success. I must thank the whole department, all the colleagues in the department, because they have been working since last almost 15 days. And very, very important is the participants, because any event doesn't become successful until participants. So we are very grateful to our participants for participating with a large number in this activity. And with this, once again, I thank all of you. And I think we will conclude the session. So I think we will, with this, we will end the meeting. Thank you all. That's it.
Thank you. Yeah. Thank you, Kiran. Thank you, Kiran. Thank you, everybody. Thanks. Okay.